Space, the ultimate frontier of human exploration and scientific discovery. For centuries, we've looked up at the stars, wondering about our place in the vast universe. Today, however, cutting-edge technology and groundbreaking research are finally beginning to reveal the mysteries that have long eluded us. Yet with each new discovery, even deeper questions emerge, questions that push us further into the unknown. One of the most captivating and perplexing phenomena to capture the imagination of scientists is the mysterious hexagonal storm at Saturn's North Pole. First discovered by the Voyager spacecraft in the 1980s, this massive storm spans an astonishing 20,000 miles, making it larger than many of Earth's most powerful storms. At first glance, the storm's almost perfect geometric shape seemed too symmetrical to be a natural occurrence, sparking years of speculation and theoretical investigations. Some even wondered if it could be the result of some alien force. After decades of study, scientists have uncovered the natural forces that give rise to this strange hexagon. Saturn's atmosphere, unlike Earth's, is a dynamic and extreme environment where jet streams move at incredible speeds over vast distances. This creates standing wave patterns, which manifest as tight geometric shapes like the hexagon. These waves behave differently than the more amorphous storm formations we're used to seeing on Earth. One key factor in the formation of this extraordinary storm is a phenomenon known as Rossby waves. On Earth, these waves are responsible for influencing large-scale weather patterns and ocean currents, but on Saturn, their effects are amplified due to the planet's unique composition. With its lower density and gaseous atmosphere, Saturn allows these waves to interact across much greater distances with far less friction. At Saturn's North Pole, the jet stream speeds along at an astonishing 200 miles per hour, a force that stabilizes the formation of the hexagon. But that's not the only contributor. Temperature gradients within the storm also play a crucial role. The interior of the hexagon is warmer than its outer edges, creating shifts in atmospheric pressure that help to maintain its sharp, defined boundaries. By combining the sheer speed of Saturn's jet streams, the planetary wave patterns, and the temperature differences, we get the awe-inspiring, perfectly shaped hexagonal storm that continues to baffle scientists and delight stargazers alike. Venus, another mysterious neighbor in our solar system, has captivated scientists with its odd and backward rotation. Unlike most planets, which rotate from west to east, Venus spins in the opposite direction, east to west, completing one full rotation every 243 Earth days. This retrograde rotation has puzzled researchers for years, and many have tried to figure out why this strange phenomenon occurs. The leading hypothesis suggests that Venus was once struck by massive cosmic impacts during its early formation. These colossal collisions may have been powerful enough to reverse its rotation and alter its speed, setting it on its current slow and retrograde path. But the story doesn't end there. Venus's thick carbon dioxide-rich atmosphere creates intense atmospheric tides, which generate friction between the planet's surface and the overlying gases. Over billions of years, this friction may have contributed to the gradual shift in Venus's rotation. Additionally, gravitational interactions with the Sun, combined with tidal forces, might have played a cumulative role, further altering the planet's spin. With computer models supporting these theories, it seems that a combination of catastrophic impacts in Venus's early years and long-term atmospheric dynamics have conspired to make Venus one of the most fascinating and enigmatic planets in our solar system. These mysterious phenomena, from Saturn's perfect hexagon to Venus's retrograde rotation, remind us that even in the age of advanced exploration, the universe still has secrets waiting to be uncovered. As we continue our journey to explore these cosmic wonders, the answers we find will surely open new doors to even greater questions, pushing the boundaries of what we know and sparking the curiosity of future generations. Jupiter's upper atmosphere is an astonishing enigma, with temperatures soaring to an intense 900-degree Fahrenheit, far exceeding what scientists had expected for a planet that sits nearly 500 million miles away from the Sun. For years, this puzzling anomaly has confounded researchers. Traditional thinking suggested that a planet so distant from the Sun should experience much cooler atmospheric conditions, with solar radiation being too weak to cause such extreme warmth. Yet as new studies emerge, the answer to this riddle is beginning to take shape, and it's far more complex than anyone anticipated. Recent discoveries have pointed to Jupiter's powerful auroras as a primary culprit in this heat anomaly. The planet's magnetic field, an incredible 20,000 times stronger than Earth's, plays a crucial role in this process. When charged particles from the Sun collide with Jupiter's dense atmosphere, they generate spectacular auroras, much like the northern and southern lights on Earth. However, these auroras are not just dazzling light displays. They are heat engines. The high-energy particles precipitating into the atmosphere transfer their kinetic energy into thermal energy, essentially heating up the upper layers of Jupiter's atmosphere. This is a key factor in the extreme temperatures scientists have measured. Furthermore, Jupiter's rapid rotation accelerates the distribution of this heat across the planet. With a full rotation taking only about 10 hours, the planet's atmosphere is constantly churning, spreading the heat more evenly and amplifying its effects. But it doesn't end there. Additional research suggests that gravity waves, ripples in the atmosphere caused by turbulent airflows, may also play a significant role in the heat transfer. These waves act like a conveyor belt, carrying energy from the planet's lower layers up to the upper atmosphere. When they break apart, they release even more energy into the upper atmosphere, contributing to the sizzling conditions that have baffled scientists for so long. This combination of auroral heating and gravity waves working in concert helps explain the extreme and unexpected warmth of Jupiter's upper atmosphere. Uranus, on the other hand, offers a whole different mystery. Uniquely tilted at an angle of approximately 98 degrees, it rotates in a way that no other planet in our solar system does. Instead of spinning on an upright axis like the rest of the planets, Uranus essentially rolls on its side as it orbits the Sun, creating one of the most puzzling planetary orientations known. So what caused this strange tilt? The leading hypothesis to explain Uranus's dramatic tilt points to cataclysmic collisions during its formation. Early in the planet's history, it's believed that one or more massive objects collided with Uranus, imparting enough angular momentum to send the planet spinning sideways. A key theory suggests that a protoplanet about the size of Earth crashed into Uranus at an oblique angle, tipping it over. The impact was likely so immense that it not only altered the planet's tilt, but also caused significant changes to its internal structure, including its core and mantle. This collision could have even influenced Uranus's magnetic field, which is strangely off-center and tilted in relation to its axis of rotation. Computer models and simulations have confirmed the plausibility of this dramatic event, showing that a giant impact could indeed account for the unusual tilt of the planet. This tilt has far-reaching consequences, most notably in Uranus's seasonal cycles. Because of its extreme orientation, each of its poles experiences about 42 years of continuous sunlight, followed by 42 years of complete darkness. This prolonged exposure and deprivation result in wild atmospheric phenomena as the planet's atmosphere responds to the extreme changes in light and temperature. It's a stark reminder of how cosmic collisions have shaped the planets in our solar system, giving Uranus its strikingly unusual axial orientation and fascinating seasonal cycles. And then there is Saturn, home to one of the most captivating features in the solar system, its iconic rings. However, these rings aren't as static as they once appeared. In the 1980s, when Voyager first captured images of Saturn's rings, scientists were stunned by the discovery of dark radial streaks, or spokes, that seemed to shift and move over time. This unexpected phenomenon led many to question the traditional view of Saturn's rings as solid and unchanging. The investigation into these enigmatic spokes took on new life with the arrival of the Cassini spacecraft, which provided more detailed images and data. Scientists soon realized that the spokes are not made of solid material, but rather are the result of electrical interactions between the ring particles and Saturn's powerful magnetic field. These particles, energized by the planet's magnetosphere, align in specific patterns, creating the striking radial features that change and evolve as they move across the rings. The spokes, though subtle, are a testament to the dynamic processes that shape Saturn's ring system, challenging our understanding of what these stunning features are and how they behave over time. Through these investigations, we learned that the planets of our solar system are not static or predictable. Each of them, from Jupiter's scorching atmosphere to Uranus's tilted spin and Saturn's shifting rings, presents a unique puzzle, shaped by cosmic forces beyond our comprehension. These planetary mysteries continue to captivate astronomers and ignite a thirst for knowledge, urging us to look deeper into the complexities of our cosmic neighbors. It appears that the remarkable phenomena of Saturn's rings and the mysteries surrounding Mercury and Mars have long captured the fascination of scientists and astronomers. These celestial enigmas present us with unique clues to the early solar system and its formation, offering deep insights into the forces that shaped our cosmic neighborhood. Saturn's rings are home to one of the most intriguing and mysterious phenomena in the solar system, the ethereal spokes. These striking, ghostly features that sweep across the planet's icy rings appear to result from complex interactions between Saturn's powerful magnetic field and the tiny particles that make up the rings. These particles, predominantly composed of water ice, become electrically charged through ultraviolet sunlight or frictional interactions within the rings. When exposed to Saturn's powerful magnetosphere, these charged particles are pulled upward, suspended above the plane of the rings. This magnetic interaction forces them out of their normal orbits, aligning them along Saturn's magnetic field lines, which gives rise to the spoke-like structures. This phenomenon, while mesmerizing, is also strikingly similar to the way iron filings align along magnetic field lines in a simple classroom experiment, but on a cosmic scale. However, what makes Saturn's spokes even more fascinating is their seasonal nature. The visibility of these spokes changes dramatically as Saturn orbits the Sun. They are most prominent during the planet's equinoxes, when the rings are aligned edge-on to the Sun. During these periods, increased solar activity enhances the charging of the ring particles, making the spokes even more visible. As the angle of sunlight shifts with Saturn's seasons, the formation and visibility of these spokes fluctuate, providing a visual reminder of the dynamic relationship between solar radiation, ring dynamics, and Saturn's immense magnetic field. Moving beyond the gas giants, Mercury, the smallest planet in our solar system, holds its own mysteries. One of the most fascinating aspects of Mercury is its disproportionately large iron core, which makes up around 85% of its radius. This oversized core has long baffled scientists, prompting several hypotheses to explain its unusual structure. The planet's proximity to the Sun was once thought to be the key factor in its formation. The intense heat close to the Sun would have caused lighter materials to evaporate or be swept away by solar winds, leaving behind a dense, metal-rich body. However, this theory alone doesn't fully explain the enormous size of Mercury's core. To resolve this puzzle, scientists have increasingly turned to the theory of catastrophic impacts. They suggest that during the chaotic early days of the solar system, Mercury may have experienced one or more colossal collisions with other protoplanetary bodies. These impacts would have stripped away much of the planet's silicate mantle, leaving behind a massive iron-rich core. Simulations of such collisions support this idea, indicating that a massive impact could have created the observed core-to-mantle ratio. Moreover, recent studies of Mercury's magnetic field lend further weight to this hypothesis. The strength and behavior of the magnetic field point to vigorous core dynamics consistent with a large molten iron core. Thus, Mercury's unique internal structure appears to be the result of a combination of its close proximity to the Sun and the catastrophic impacts that reshaped its composition. Mars, often called the Red Planet, has its own share of peculiarities, particularly when it comes to its two small moons, Phobos and Deimos. These odd, irregularly shaped moons have long fascinated astronomers who have debated their origins since their discovery in the 19th century. Unlike Earth's large and spherical moon, Phobos and Deimos are much smaller, measuring only about 14 miles and 8 miles in diameter, respectively. Their bizarre, lumpy shapes have led scientists to propose two primary hypotheses regarding their formation. The first hypothesis suggests that Phobos and Deimos are captured asteroids from the asteroid belt, located between Mars and Jupiter. These moons bear a striking resemblance to a class of dark, carbon-rich asteroids known as C-type asteroids, which are common in this region. According to this theory, gravitational interactions and collisions within the asteroid belt may have ejected these asteroids from their original orbits, sending them on a collision course with Mars. Once in the vicinity of Mars, the planet's gravity would have captured them, locking them into their current orbits. This capture event would account for their irregular shapes and their stark differences in origin compared to Mars itself. The other hypothesis suggests that the moons could have formed in place from debris left behind by ancient collisions involving Mars. While this theory is less widely accepted, it remains an interesting possibility that adds to the mystery of Mars' companions. As we continue to explore the vastness of our solar system, Saturn, Mercury, and Mars provide compelling case studies of the dynamic forces at work in shaping the planets and moons around us. Whether it's the fleeting beauty of Saturn's spokes, the puzzle of Mercury's oversized iron core, or the strange origins of Mars's moons, each discovery offers a glimpse into the violent and ever-changing history of our cosmic neighborhood. These celestial wonders remind us that even in the far reaches of space, the forces that govern the universe are complex, beautiful, and awe-inspiring. The second hypothesis regarding the formation of Mars's moons, Phobos and Deimos, points to a dramatic event in the planet's ancient history, a colossal impact. In this scenario, a massive object, perhaps a comet or a large asteroid, struck Mars with incredible force, sending a cloud of debris into space. Over time, the debris would have clumped together, eventually forming the two moons. This theory gains significant support from sophisticated computer simulations that demonstrate the feasibility of such an event. These simulations suggest that the impact could have produced moons with the distinct characteristics we observe in Phobos and Deimos today. What strengthens this theory even further is the striking resemblance of the moon's surface features to fragmented rubble pile structures, a known hallmark of celestial bodies formed from the remnants of a catastrophic collision. Phobos and Deimos, in their current state, appear to be loosely held together by their own gravity, much like a collection of debris from a larger body. This rubble pile structure is supported by ongoing observations and data from various space missions. One of the most exciting of these missions is Japan's Martian Moons Exploration, MMX mission, which is set to land on Phobos and bring back samples to Earth. These samples will offer crucial insights into the moon's composition, potentially unlocking the secrets of their origins. Are they captured asteroids, or are they the remnants of an ancient, catastrophic impact? Regardless of their origin, Phobos and Deimos remain enigmatic symbols of Mars's tumultuous past and a reflection of the broader complexities in our solar system's formation. Meanwhile, in another corner of our solar system, Pluto's iconic heart-shaped region known as Tombaugh Regio has captured the public's imagination. First revealed in breathtaking detail by NASA's New Horizons spacecraft in 2015, this striking feature is more than just a captivating visual. It offers a window into Pluto's geological and atmospheric processes. Tombaugh Regio, named in honor of Clyde Tombaugh, the astronomer who discovered Pluto in 1930, holds clues to the dwarf planet's ancient history and ongoing transformations. The left lobe of this heart, Sputnik Planitia, is a vast icy plain primarily composed of nitrogen, methane, and carbon monoxide ices. Scientists believe it was formed by a colossal impact early in Pluto's history, carving out a massive depression on the surface. This event, which occurred billions of years ago, set the stage for the processes we observe today. Over time, the region has been shaped by cryovolcanism, the eruption of icy material rather than molten rock, and the gradual accumulation of volatile ices. This has led to the smooth reflective surface we see today. Perhaps most fascinating is the nitrogen ice within Sputnik Planitia. It is particularly susceptible to sublimation and deposition, processes that actively renew the surface. Similar to convection currents in Earth's mantle, the nitrogen ice warms, rises, cools, and sinks again, creating polygonal patterns in the region. These movements suggest a dynamic and active interior, providing evidence of ongoing geological activity beneath the icy crust. Models also suggest that Sputnik Planitia may play a role in balancing Pluto's orientation. Its mass, located near Pluto's equator, could influence the planet's spin axis, contributing to the current tilt of the dwarf planet. This active geological reshaping, powered by internal heat, possibly from radioactive decay, provides a glimpse into the complex and dynamic nature of Pluto. Tombaugh Regio, with its rich history and ongoing processes, stands as one of the most geologically fascinating regions in our solar system. Far beyond Pluto, Neptune's largest moon, Triton, presents one of the most dynamic and intriguing surfaces in the solar system. Known for its active geysers, Triton is a world of extremes. These geysers, first discovered by Voyager 2 in 1989, shoot plumes of nitrogen gas mixed with dark carbon-rich compounds several miles into the moon's thin atmosphere. The origin of these geysers lies in Triton's unique combination of cryovolcanism and solar heating. Triton's icy surface, coated predominantly with nitrogen, lies under incredibly cold temperatures, averaging around -391 degrees Fahrenheit. Beneath this frozen exterior, there is a complex mix of other ices and possibly even a subsurface ocean, suggesting that Triton's geology may be far more complex than initially thought. Seasonal heating from the distant sun is believed to drive the geysers, causing volatile ices beneath the surface to erupt in spectacular fashion. The combination of these factors makes Triton an intriguing world full of mystery and activity, and one of the most geologically active bodies in the outer solar system. Despite its minimal intensity at Triton's orbit, approximately 2.7 billion miles from Earth, Triton, Neptune's largest moon, reveals a striking example of geologic activity that challenges our understanding of icy worlds. During Triton's summer, the faint sunlight that reaches the distant moon penetrates its thin nitrogen ice layer. This minimal warmth causes the surface to heat up slightly, and the energy that's trapped beneath the ice leads to the sublimation of nitrogen, transforming it directly from solid to gas. This process results in a dramatic buildup of pressure beneath Triton's icy surface, creating conditions ripe for geological eruption. As the pressure continues to rise, it finds its escape through weak spots in the ice, triggering geysers that burst into the cold, thin atmosphere, spewing dark particles and nitrogen gas into the void. This dynamic phenomenon offers a unique glimpse into the forces at work beneath Triton's surface. Observations support this theory, as the geysers are most prominent in the sunlit regions of the southern hemisphere, where solar heating is most intense. These eruptions can reach impressive heights of up to 5 miles, and the plumes are swept away by Triton's winds, leaving behind dark streaks across the surface of the moon. While these geysers are undoubtedly a captivating sight for any astronomer or space enthusiast, their significance runs much deeper. They provide vital clues about the internal composition and structure of Triton, suggesting the presence of volatile materials and possibly even liquid reservoirs hidden beneath its icy crust. These geysers, fueled by the moon's tenuous relationship with solar energy, reveal that Triton is not a lifeless world, but one that remains geologically active, driven by forces reminiscent of volcanic activity on Earth, albeit on a much colder scale. The eruptions also raise intriguing questions about the potential for extraterrestrial geologic activity in the far reaches of the solar system, positioning Triton as a focal point for both scientific inquiry and speculation about the geologic potential of moons far beyond our own planet. Meanwhile, the Sun, whose corona, the outermost layer of its atmosphere, has long been a subject of mystery, continues to baffle scientists due to its extreme temperatures. These temperatures soar to an astonishing 1 to 3 million degrees Fahrenheit, a staggering contrast to the Sun's relatively cooler surface, or photosphere, which sits at about 10,000 degrees Fahrenheit. This paradoxical temperature disparity is known as the coronal heating problem, and has been a central puzzle for solar physicists for decades. The challenge lies in explaining how the corona can be so much hotter than the surface of the Sun, where you'd intuitively expect the hottest region to be located. Through years of research, however, scientists have identified several potential mechanisms that might explain this phenomenon. One of the leading theories is magnetic reconnection. The Sun's magnetic field is highly dynamic, constantly twisting and tangling due to the motion of solar plasma. When these twisted magnetic lines snap and reconnect, they release vast amounts of energy, which can superheat the surrounding plasma to incredibly high temperatures. This sudden release of energy is similar to a cosmic rubber band being snapped, where stored magnetic energy is converted into heat. This process not only heats the corona, but also contributes to explosive events like solar flares, further intensifying the corona's temperature. In addition to magnetic reconnection, wave heating plays a crucial role in the coronal heating puzzle. Two main types of waves, acoustic waves and alpha waves, are believed to carry energy from the sun's interior to its outer atmosphere. Alpha waves are generated by the turbulent motions in the sun's convection zone and travel along magnetic field lines, delivering energy to the corona. As these waves move, they dissipate their energy in the form of heat, much like the way ocean waves release energy onto the shore. Acoustic waves, which are pressure waves created by turbulence within the sun's interior, also contribute to the heating, though their impact is considered less significant compared to the alpha waves. Together, magnetic reconnection and wave heating offer a plausible explanation for the sun's blazing corona, but the precise mechanisms behind this process are still actively studied. These dynamic forces within the sun's magnetic field and plasma offer a natural laboratory for exploring extreme physical conditions, providing invaluable insights that not only enhance our understanding of the sun, but also inform our knowledge of other stellar phenomena across the universe. The mystery of the sun's corona is just one of many cosmic puzzles that continue to challenge and inspire scientific discovery, offering new avenues for understanding the fundamental processes that govern our universe. The quest to discover Earth-like planets in the vastness of the universe has taken an exciting turn in recent decades. Thanks to remarkable advancements in space telescopes and observational techniques, our ability to detect distant worlds has improved significantly. As we continue to collect more data, it becomes increasingly clear that Earth-like planets might be far more common than we initially believed. One of the pivotal instruments in this ongoing search has been the Kepler Space Telescope, which operated from 2009 to 2018. Throughout its mission, Kepler identified thousands of exoplanets orbiting distant stars. From Kepler's groundbreaking discoveries, scientists now estimate that there may be as many as 40 billion Earth-sized planets within the habitable zones of Sun-like and red dwarf stars in the Milky Way alone. The habitable zone, often referred to as the Goldilocks zone, is the region around a star where conditions are just right for liquid water to exist, not too hot and not too cold. This is an essential factor, as liquid water is a fundamental requirement for life as we know it. Kepler's findings were nothing short of astonishing, revealing a rich diversity of potentially habitable planets that could harbor conditions conducive to life. These exoplanets display a variety of characteristics, from rocky terrains similar to Earth's to vast water worlds and planets enveloped by thick, dense atmospheres. These discoveries have paved the way for future missions that promise to take our understanding of these distant worlds to even greater heights. The Transiting Exoplanet Survey Satellite, TESS, launched in 2018, is conducting an extensive survey of the nearest and brightest stars, with the potential to uncover thousands more exoplanets. Meanwhile, the James Webb Space Telescope, with its powerful instruments, will enable scientists to study the atmospheres of these far-off planets in unprecedented detail. By analyzing these atmospheres, Webb will be able to detect biosignatures such as oxygen, methane, and water vapor, key indicators that could suggest the presence of life. Together, these missions are transforming our understanding of how common Earth-like planets might be and providing critical insights into their potential to support life. Where Earth-like planets once seemed rare, current evidence points to the possibility that they could be far more abundant in the universe than we previously thought. As we continue to refine our estimates with ongoing research, we come ever closer to answering one of humanity's most profound questions. Are we alone in the universe, or are we part of a vast, populated cosmic landscape? As we delve deeper into the possibilities, we encounter fascinating scenarios, such as life on a tidally locked planet. These planets, which are locked in orbit with one side perpetually facing their parent star, would experience extreme environments. On one side, perpetual daylight would scorch the surface with intense heat, while the other side remains in a constant state of darkness and cold. The stark temperature differences could range from searing heat to freezing cold, creating a set of unique challenges for any potential life forms. The most likely place for life to thrive on a tidally locked planet would be the narrow band along the Terminator line, the twilight zone where night meets day. Here, temperatures would be more moderate, offering a habitable environment away from the intense heat of the star-facing side and the bone-chilling cold of the dark side. In this region, plants and photosynthetic organisms could flourish, adapting to the low light conditions while utilizing steady, indirect sunlight. Liquid water, if present, might accumulate in this zone, providing a crucial resource for sustaining life. On the star-facing side of the planet, life would have to adapt to the relentless exposure to starlight. Organisms here might evolve extraordinary adaptations to survive extreme heat and radiation, such as thick reflective coatings or the ability to burrow underground. On the night side, life forms would have to endure near-freezing or sub-freezing temperatures. Much like the extremophiles on Earth, organisms that thrive in polar regions or at the bottom of the ocean, life forms here might rely on chemosynthesis rather than photosynthesis, deriving energy from chemical reactions in the absence of light. Human habitation on a tidally locked planet would present a unique set of challenges. Settlements would most likely be located along the habitable Terminator line, where conditions are more favorable. Advanced technology would be essential to manage the extreme temperature variations, with systems designed to regulate temperature and conserve resources. Harnessing sustainable energy, perhaps by exploiting the contrast between the light and dark sides of the planet, would be vital for ensuring a livable environment. The wind patterns created by the temperature disparity would also require careful consideration when designing settlements. As we continue to push the boundaries of space exploration, our understanding of exoplanets and their potential for harboring life will only grow. Each new mission, each new discovery brings us one step closer to answering the most profound questions about our place in the universe. Will we one day find a twin of Earth teeming with life, or perhaps a world that is as alien as it is familiar? The answers lie somewhere out there, waiting to be discovered. These speculative scenarios highlight the resilience and adaptability required for life to thrive under such extraordinary conditions. Hot Jupiters, a fascinating class of exoplanets, captivate scientists with their colossal size and their unexpectedly close orbits around their parent stars. These gas giants are comparable in size to Jupiter, yet they orbit so near to their stars that some complete a full orbit in just a few days. This proximity to their stars and their enormous dimensions make hot Jupiters stand out in the exoplanet field, sparking numerous theories about their origins and migration. One widely accepted theory is the migration hypothesis. This suggests that hot Jupiters form much farther from their parent stars, in the colder regions of the protoplanetary disk where temperatures are low enough for ices to condense. Here, they coalesce into massive cores, much like how Jupiter formed in our solar system. These distant areas allow for the accumulation of vast amounts of gas and dust, eventually giving rise to giant planets. But after their formation, these gas giants interact with the surrounding material in the protoplanetary disk. This leads to exchanges of angular momentum, pushing the planet inward toward the star. Known as disk-driven migration, this process reshapes the planet's orbit and brings it into close proximity to its star. However, this isn't the only explanation. Another theory suggests that gravitational interactions with other planets or planetary embryos can alter a hot Jupiter's orbit. In a young, dynamically unstable planetary system, massive bodies can scatter one another through close encounters. This process, called planet-planet scattering, can result in a giant planet being flung into an eccentric orbit. Over time, the tidal forces exerted by the star can circularize the orbit, ultimately pulling the planet into a stable, tight orbit near the star. Sometimes, these interactions also involve what are called Calliope oscillations, where the gravitational influence of a third body causes periodic oscillations in the inclination and eccentricity of the planet's orbit. These oscillations can further fuel the inward migration of the planet. These migration processes explain the unexpected presence of hot Jupiters in stark contrast to the traditional planetary formation model, which has long been based on our solar system's structure. Observations of young star systems have provided evidence for both types of migration. enhancing our understanding of these fascinating mechanisms. Instruments like the Kepler Space Telescope and future missions such as the James Webb Space Telescope can continue to gather data, offering new insights into how planets find their place in the cosmos. The study of hot Jupiters does not just improve our knowledge of planetary formation and migration. It challenges and refines existing models in planetary science, expanding the boundaries of what we know about the universe. The universe is home to a myriad of bizarre and extreme exoplanets, each one defying our expectations and expanding our understanding of planetary diversity. Among the most extreme is one of the hottest known exoplanets, Kelt 9b. Located around 670 light-years away, Kelt 9b is a gas giant that completes an orbit every 5 days. It is so close to its star that its dayside temperatures soar to an astonishing 7,800 degrees Fahrenheit, hotter than some stars. This extreme heat causes its atmosphere to evaporate, creating a tail of vaporized metals and molecules that trails behind it like a comet. On the other end of the temperature spectrum lies Ogle 2005 BLG 39b, a cold and distant world discovered via gravitational microlensing. About 20,000 light-years away, this exoplanet orbits far from its host star, with surface temperatures hovering around -400 degrees Fahrenheit. Such extreme cold suggests that the surface is likely covered in frozen hydrogen and methane, potentially hiding a subsurface ocean kept liquid by the planet's internal heat. Equally extraordinary are the densest exoplanets, such as Kepler 10b, located around 560 light-years away in the constellation Draco. Kepler 10b is an ultra-dense, rocky planet with a density almost twice that of Earth. Initially, scientists believed it to be an oversized version of Mercury due to its extreme density. This hinted at a metallic composition, much like the innermost planet in our solar system, further deepening the mystery of exoplanetary diversity. In exploring these planets, we not only witness the extremes of temperature, composition, and orbit, but also gain invaluable insights into the processes that govern planetary formation and evolution. Each discovery, each new exoplanet contributes to a grander understanding of the cosmos, one that continues to challenge, surprise, and awe us as we look deeper into the universe's mysteries. In the vast expanse of the universe, Kepler 10b presents a mesmerizing and extreme example of a hostile world. Its day side reaches scorching temperatures of up to 3,600 degrees Fahrenheit, a blistering heat so intense that it likely causes oceans of molten rock to flow across its surface. But Kepler 10b is not an isolated anomaly. In fact, it belongs to a broader category of rogue planets, free-floating worlds that drift aimlessly through the dark stretches of interstellar space. Unlike planets that orbit stars, these rogue planets lack the stabilizing influence of a nearby star's heat and light. As a result, their temperatures can vary dramatically depending on the internal heat sources they retain. Some, like the exoplanet CFBD 2049-403, maintain a temperate 400 degrees Fahrenheit, likely sustained by their own internal processes rather than the warmth of a distant star. Among the many extraordinary exoplanets discovered, one that stands out is WASP-12b, an example of a hot Jupiter. This planet undergoes a fascinating and violent process of tidal disruption. Tightly locked in its orbit, it is so close to its host star that the star's immense gravitational pull has distorted the planet into an egg-like shape. Temperatures on this planet exceed 4,000 degrees Fahrenheit, and its atmosphere is being gradually stripped away by the relentless pull of the star. A stream of material trails behind WASP-12b, absorbed into the very heart of the star itself. This cosmic cataclysm challenges our conventional understanding of planetary formation and habitability, demonstrating the extreme and unpredictable variety of worlds that exist beyond our solar system. Each discovery of such worlds opens new chapters in our understanding of the universe and the immense possibilities that lie beyond our reach. These strange and distant planets defy our expectations, revealing a cosmic diversity that was once thought impossible. The more we learn, the more we realize just how much remains to be uncovered in the vast expanse of our galaxy. Among these revelations are the discoveries of planets within binary star systems, systems where two stars orbit a common center. Despite the complex gravitational dynamics at play, planets do indeed form within these systems, providing a striking challenge to our traditional models of planetary formation. In a binary system, planets often form in protoplanetary disks, dense regions filled with gas, dust, and other materials surrounding one or both of the stars. Here, the gravitational interactions between the two stars create a more complicated, yet not impossible, environment for planetary creation. This cosmic ballet of forces influences how the particles within the disk collide and coalesce, slowly building into planetesimals and eventually full-fledged planets. Research, particularly involving advanced simulations, has revealed that planets within binary star systems generally form in two main configurations. In circumbinary systems, planets orbit both stars in a wide, stable path, typically located beyond the chaotic gravitational influences of the stars themselves. On the other hand, in circumstellar systems, a planet may orbit just one of the two stars, while the second star orbits at a greater distance. The dual star influence is a significant factor during the formative stages of these planets, often leading to unique and dynamic orbital characteristics that distinguish them from their single-star counterparts. Recent findings, such as those from the Kepler Space Telescope, have confirmed the existence of several such planets. These discoveries underscore the incredible versatility of nature in creating worlds, even in the complex gravitational environments of binary star systems. This proves that, no matter how complicated the cosmic forces at play, planetary formation remains a robust and adaptable process. As we venture deeper into the study of exoplanets, one area of particular interest is the study of their atmospheres. By analyzing the light that filters through or reflects off an exoplanet's atmosphere, scientists can gain crucial insights into the planet's composition and dynamics. This, in turn, opens the door to exploring the broader question of habitability, whether these distant worlds could support life as we know it. The study of exoplanet atmospheres has the potential to transform our understanding of the universe, revealing not only the conditions necessary for life, but also the many ways in which life might emerge beyond the confines of Earth. These discoveries are just the beginning. As our technology advances, we are likely to uncover even more extraordinary exoplanets, worlds that challenge our imagination and deepen our understanding of the cosmos. With each new discovery, we move closer to answering one of humanity's most profound questions. Are we alone in the universe? Through groundbreaking techniques such as spectroscopy, scientists can peer into the very fabric of distant worlds, unlocking secrets hidden in the light that reaches us from the farthest corners of the universe. By analyzing the faint signals from exoplanet atmospheres, they detect the presence of various molecules, including water vapor, methane, carbon dioxide, and even oxygen. These molecular signatures provide a window into a planet's atmospheric chemistry, revealing vital information about its weather patterns, geological activity, and even its potential for harboring life. These atmospheric compositions tell a compelling story about the planet's origins and evolutionary history. For example, an abundance of hydrogen and helium might indicate the presence of a gas giant like Jupiter, while the discovery of oxygen and water could suggest a more Earth-like environment, one that might, in theory, support life. Furthermore, scientists are beginning to observe how these atmospheres evolve over time. Changes in the atmosphere's composition can signal phenomena such as volcanic eruptions, seasonal shifts, or the influence of external factors like stellar radiation. This wealth of atmospheric data doesn't just enrich our understanding of the planets themselves, but also refines our models of planetary formation, guiding our search for potentially habitable worlds, worlds that might one day be known as super-Earths or mini-Neptunes. These intermediate-sized planets, those that are larger than Earth but smaller than Neptune, have become an intriguing subject of study. Super-Earths, rocky planets that are up to 10 times the mass of Earth, offer critical insights into planetary formation. These planets often form early in a star system's history, inside a protoplanetary disk, a dense, rotating cloud of gas and dust surrounding a young star. Within these disks, dust particles collide, stick together, and eventually form planetesimals, the building blocks of planets. Super-Earths undergo rapid growth as material accumulates, often before the gaseous components of the protoplanetary disk dissipate. According to the core accretion model, these planets gradually build up a solid core, which can then attract gas from the surrounding disk, if the planet is massive enough. However, they are typically too small to evolve into gas giants. On the other hand, mini-Neptunes, characterized by their thick, extended atmospheres of hydrogen and helium surrounding a solid core, might follow a similar path of growth, but manage to capture a more substantial gaseous envelope. These planets may form in the colder outer regions of the protoplanetary disk, where gas accretion is more efficient, or they might migrate inward toward the star after their formation. Observations from the Kepler Space Telescope and other recent missions have shown that these intermediate planets are among the most common types found in our galaxy. Interestingly, these types of planets do not exist in our own solar system, adding another layer of complexity to our understanding of planetary formation. The diversity of exoplanets points to a rich and varied array of planetary systems, each with unique formation mechanisms and evolutionary pathways. The search for a true Earth 2.0 has become a defining focus of modern astronomy. Scientists are honing in on planets that are either Earth-sized or slightly larger, located within the habitable zone of their parent stars, the so-called Goldilocks zone. This is the sweet spot where conditions are just right, not too hot, not too cold, and where liquid water could exist on the planet's surface, an essential ingredient for life as we know it. This quest to find another Earth has captured the public's imagination, with the potential to reshape our understanding of the universe and our place within it. The discovery of an Earth-like exoplanet, with its potential for liquid water, would not just be a scientific breakthrough. It could be the key to answering one of humanity's most profound questions: are we alone in the universe? Through these efforts, we are steadily unraveling the mysteries of our galaxy, piece by piece. From detecting the molecular signatures of distant exoplanets to the ongoing study of planetary systems, scientists are gaining a deeper understanding of how planets form, evolve, and potentially support life. Every new discovery brings us closer to finding answers that could change the course of human history, offering a glimpse into the vast possibilities that lie beyond our home world. In the vast expanse of space, the discovery of new planets beyond our solar system has taken a remarkable leap forward, thanks to advancements in telescope technology. Instruments like the Kepler Space Telescope and its successor, the Transiting Exoplanet Survey Satellite, TESS, have radically transformed our ability to detect exoplanets. These sophisticated telescopes detect the dimming of a star's light caused by a planet crossing in front of it, a phenomenon known as a transit. This breakthrough has led to an explosion in the number of identified exoplanets, with many of these newly discovered worlds showing promise in terms of their potential to harbor life. Among the most exciting discoveries are planets like Kepler 186f and Proxima Centauri b, both of which sit within their respective habitable zones. These zones are the regions around stars where conditions may be just right for liquid water to exist on a planet's surface, an essential ingredient for life as we know it. But the true challenge lies in going beyond the identification of these promising candidates. The next frontier in exoplanet exploration is to study their atmospheres in greater detail to understand their true potential for habitability. With the help of groundbreaking instruments such as the James Webb Space Telescope and upcoming missions like the European Space Agency's Ariel spacecraft, scientists are poised to study the atmospheric compositions of these distant worlds with unprecedented precision. These missions will analyze the gases in these planets' atmospheres, looking for biosignatures such as oxygen, methane, and other organic molecules that could suggest the presence of life. While we have yet to discover an exact Earth analog, the accelerating pace of these discoveries, paired with technological advancements, means that finding a second Earth is no longer a distant dream, but a very real and attainable goal in the near future. At the same time, the universe offers more than just planets that orbit stars. There exists a fascinating class of celestial bodies known as rogue planets. These planets drift freely through the galaxy, not bound to any star, and are among the most mysterious objects in the cosmos. Rogue planets can form in various ways. One leading hypothesis is that they are born in the protoplanetary disks around young stars, much like regular planets. However, gravitational interactions with other planets or passing stars can destabilize their orbits, sending them adrift into interstellar space. Another theory suggests that rogue planets could form independently from the collapse of gas and dust clouds in space, similar to how stars form, but without the mass necessary to initiate nuclear fusion. These rogue planets, in essence, represent the remnants of a failed star formation. As these planets drift through the void of space, they evolve in isolation, far from the warmth and radiation of any nearby star. This absence of stellar energy means that their surfaces can be incredibly cold, possibly even frozen. But there's a twist. Rogue planets could still harbor life in the form of subsurface oceans. Internal heat, generated by radioactive decay or residual warmth from their initial formation, could provide the energy necessary to maintain liquid water beneath the icy crusts. This opens up fascinating possibilities for isolated ecosystems that could thrive in the extreme conditions of these wandering planets. Thanks to improvements in detection technology, including gravitational microlensing techniques and advanced infrared surveys, we are beginning to identify more rogue planets. Each new discovery adds to our understanding of the chaotic processes that shape planetary systems, offering a glimpse into the hidden corners of the universe where life might exist in the most unexpected places. Another exciting avenue of exploration is the study of super-Earths, planets that are larger and more massive than Earth but still maintain a rocky composition. Standing on the surface of a super-Earth would be a profoundly unique experience, as the planet's greater mass would exert a much stronger gravitational pull than what we feel on Earth. Every movement, every step, even every heartbeat would require more energy. The gravity on these planets could range from slightly stronger to several times more intense than Earth's, depending on the planet's exact size and mass. This increased gravity could result in fascinating changes in the planet's environment, affecting everything from the formation of landscapes to the biological adaptations of any life forms that may call it home. The discovery of super-Earths and rogue planets, combined with the potential for finding habitable exoplanets, marks an exciting era in our understanding of the universe. The advancements in space exploration and detection technologies are bringing us closer than ever to uncovering the hidden worlds that could harbor life. As we continue to push the boundaries of what we know, one thing is clear: the universe is full of mysteries, and we are only just beginning to scratch the surface. Imagine stepping onto a planet that is dramatically different from Earth. This is the world of a super-Earth. The gravity on such a planet would be far stronger than what we experience, making everything from walking to jumping a real challenge. You'd feel a constant pull that would weigh you down, drastically reducing your ability to move quickly or leap into the air. This gravity would not only impact how you move, but also how you live, shaping everything from the way you build structures to the way you perform daily activities. Habitats would be designed to accommodate the weight and the constant gravitational force, perhaps requiring reinforced buildings and transportation systems that can handle the added stress. Beyond the gravity, the atmosphere of a super-Earth might offer intriguing differences. A planet with a larger, more massive core could have retained a thicker atmosphere, possibly filled with gases like hydrogen and helium. These gases would significantly affect the air pressure, making it thicker and potentially harder to breathe. Coupled with this, the climate could be more extreme. If the super-Earth has a robust magnetic field, it might protect the surface from harmful cosmic radiation, creating a shield that could support life in some form. However, the thick atmosphere might also lead to powerful storms and dense cloud formations that could change the way light and heat are distributed across the planet, making the environment seem alien and unpredictable. If this super-Earth happens to lie within the habitable zone of its star, liquid water would likely exist, dramatically altering its surface. Oceans, rivers, and lush vegetation might cover large areas, fostering an ecosystem that's completely different from anything Earth has known. The landscape would also be shaped by the planet's extreme geological forces. Increased gravity would prevent mountains from rising as high as they do on Earth. Instead, you'd find shorter, more compact mountain ranges, as the weight of the rock layers would cause them to collapse before they could soar to towering heights. The planet's surface would likely feature diverse terrain, immense plains, deep, dramatic canyons, and broad plateaus, shaped by the planet's intense internal heat and tectonic activity. Standing on the surface of a super-Earth would be a constant reminder of its immense gravitational pull. The sights and experiences would challenge your perception of what a planet could be, offering a vision of a world that redefines our understanding of life and the forces that shape it. But while a super-Earth is a fascinating thought experiment, there is another profound mystery in the cosmos that continues to puzzle scientists: dark energy. This elusive force makes up about 70% of the universe's total energy content, and it is believed to be driving the accelerated expansion of the universe. Unlike dark matter, which pulls objects together with gravity, dark energy does the opposite. It pushes regions of space apart. Despite its influence on the universe, its exact nature remains one of the greatest unknowns in modern cosmology. Dark energy was first suggested by Albert Einstein in his equations of general relativity, though it wasn't until the late 1990s that astronomers realized the true scale of its impact. They were observing distant supernovae and found that these stellar explosions were dimmer than expected, meaning they were farther away than initially thought. This discovery led to the realization that the expansion of the universe wasn't slowing down, as was previously believed. Instead, it was accelerating. This unexpected behavior suggested the presence of a repulsive force, dark energy, that is pushing the universe apart. The presence of dark energy is not just an abstract concept, it affects the very structure of the cosmos. It plays a key role in the formation of galaxies and galaxy clusters and has profound implications for the future of the universe. If dark energy continues to dominate, it could lead to a scenario known as the Big Freeze, where galaxies drift so far apart that stars run out of fuel and can no longer form new stars. The universe would eventually become a cold, dark, and sparse place, devoid of the light and warmth that we currently experience. There are many theoretical models attempting to describe dark energy. One such model is quintessence, which proposes that dark energy is not a constant, but a dynamic field that changes over time. Other theories suggest that the laws of gravity may behave differently on large cosmic scales. To explore these ideas, upcoming missions like the Euclid Space Telescope and the Wide Field Infrared Survey Telescope, WTFIF-IRST, are set to map the distribution of galaxies and test the predictions about cosmic acceleration. These missions hope to bring us closer to unraveling the mysteries of dark energy, helping us understand one of the most profound aspects of the universe and the forces that govern its fate. These groundbreaking studies not only provide profound insights into the mysterious nature of dark energy, but also revolutionize our understanding of fundamental physics and the very fate of the universe. They shed new light on the complexities of the cosmos, revealing a grand and intricate tapestry that continues to evolve at every scale. The cosmic structures we observe today, especially galaxy clusters, are the epitome of the universe's dynamism and the key to unlocking its most elusive secrets. These massive gravitationally bound systems, made up of hundreds or even thousands of galaxies, vast quantities of hot gas, and an immense amount of dark matter, are all held together by the invisible hand of gravity. Their study not only opens doors to understanding the evolution of galaxies, but also offers a deeper look into the mechanisms shaping the very fabric of our universe. At the core of this discovery lies the story of galaxy clusters, which traces back to the early universe. In the wake of the Big Bang, the cosmic microwave background, an ancient relic of radiation, left behind small fluctuations in matter density. As the universe expanded and cooled, these fluctuations began to amplify under the influence of gravity. This process created pockets of higher matter concentration, which, over billions of years, drew in surrounding dark matter and gas. Dark matter, the invisible yet dominant mass component of the universe, played a pivotal role, acting as the framework or scaffolding upon which galaxy clusters would later form. Over time, smaller cosmic structures merged through a process known as hierarchical clustering. Essentially, smaller galaxy groups and protoclusters combined to form larger, more massive clusters, gradually assembling into the colossal structures we observe today. As galaxies within these clusters collided and merged, their interactions were not merely a matter of proximity. they were also shaping the cluster's development in significant ways. This process altered the galaxy's shapes and triggered bursts of star formation, contributing to the ongoing evolution of these cosmic giants. One of the key features of galaxy clusters is the intracluster medium, a hot X-ray emitting gas that can reach temperatures as high as 100 million degrees Kelvin. This gas results from the kinetic energy of gas particles being converted into thermal energy as they collapse into the gravitational potential well of the cluster. But galaxy clusters are not static entities. They are constantly evolving through dynamic processes and interactions. These colossal systems also experience cosmic collisions and gravitational interactions that can lead to phenomena such as gravitational lensing. In these events, the immense mass of the galaxy cluster bends the light from galaxies situated far behind it, creating a cosmic magnifying glass effect. Gravitational lensing offers scientists a unique opportunity to map the distribution of dark matter, a task that would otherwise be nearly impossible. By studying these lensing effects, we not only gain insight into the structure of galaxy clusters, but also uncover vital clues about the rate at which these clusters evolve. Advancements in astronomical technology, such as those offered by the Hubble Space Telescope and the Chandra X-ray Observatory, have significantly enhanced our ability to explore these distant phenomena. Moreover, with the impending arrival of next-generation instruments like the James Webb Space Telescope, our understanding of galaxy clusters and their role in cosmological structure formation is poised for even greater refinement. These observatories and their cutting-edge instruments continue to push the boundaries of our knowledge, offering valuable information that helps scientists unlock the deepest mysteries of the universe. At the heart of these observations lies a grand cosmic structure known as the cosmic web. This vast network of interconnected galaxies, galaxy clusters, and dark matter extends across the entire universe, forming an intricate framework shaped by the gravitational influence of dark matter and the expansion of the cosmos. The cosmic web is not just a theoretical construct, it's a direct consequence of the primordial density fluctuations imprinted on the cosmic microwave background in the aftermath of the Big Bang. These early density variations, though small, served as the seeds for the grand cosmic architecture we see today. In the earliest stages of the universe, these small variations in the distribution of matter led to the formation of areas with higher and lower concentrations of mass. Dark matter, which constitutes about 85% of the universe's mass, began to clump together in response to these fluctuations. Over time, gravity magnified these initial perturbations, drawing even more matter into denser regions. This gradual process created a web-like structure, with high-density regions connected by elongated filaments of dark and ordinary matter, and vast empty voids in between. As gravity continued its relentless pull, gas and dust followed the dark matter's lead, resulting in the formation of galaxies and galaxy clusters along these cosmic filaments. The intersections of these filaments, known as nodes, became the hotspots for galaxy and cluster formation, where multiple filaments converge, creating regions of exceptionally high density. These nodes serve as the cosmic hubs of the universe, interconnected by the cosmic web's filamentary strands. Modern astronomical surveys and simulations have provided unprecedented clarity on the structure of the cosmic web. The Sloan Digital Sky Survey, along with simulations like the Millennium Simulation, have generated detailed maps that confirm the cosmic web's filamentary nature. These findings have revolutionized our understanding of the universe's large-scale structure and evolution, offering critical insights into the nature of dark matter, dark energy, and the forces shaping the cosmos. As scientists continue to explore these colossal cosmic structures, they unlock ever deeper insights into the nature of our universe. Each new discovery pushes the boundaries of human knowledge and brings us one step closer to understanding the fate of all cosmic structures, from the smallest galaxies to the largest galaxy clusters. The universe, as revealed through these studies, is an endlessly fascinating and dynamic entity, one that continues to evolve, challenge our perceptions, and inspire awe. These studies reveal a profound truth. The texture of the cosmic web plays a crucial role in shaping the formation of galaxies and other cosmic structures. This intricate web of filaments and voids profoundly influences the dynamics and distribution of matter in the universe. As our observational tools and computational models improve, we will uncover even deeper insights into the complex mechanisms that drive this grand cosmic tapestry. The cosmic web is not merely an abstract concept, it is the very blueprint of the universe. Spanning across vast expanses, it consists of dark matter, galaxies, and intergalactic gas woven together by gravitational forces. At its heart lies an awe-inspiring feature: the cosmic voids. These voids, which stretch across tens to hundreds of millions of light years, are vast regions of space where matter is surprisingly sparse. Yet these emptinesses are far from being lifeless. Instead, they offer a unique lens into the forces that have shaped the universe since its birth. Cosmic voids emerge as natural consequences of the gravitational evolution of matter, a process that traces its roots back to the Big Bang. In the early universe, tiny fluctuations in density gave rise to regions of higher and lower matter density. Over billions of years, the force of gravity amplified these differences. High-density regions began pulling in more mass, leading to the formation of galaxies and galaxy clusters, while low-density areas remained largely empty, eventually evolving into the vast voids we observe today. These voids are not entirely devoid of matter, but they are strikingly less populated than the denser regions of the universe. Within them, galaxies are rare, isolated, and often small, dim, and irregular in shape, quite the contrast to their counterparts in dense galaxy clusters. While these voids may appear desolate, they serve as invaluable natural laboratories for understanding the universe's broader dynamics. Their relatively simple environments, devoid of the intense gravitational complexities found in galaxy clusters, make them ideal for studying dark energy and its effects on the universe's expansion. The dynamics of galaxies within these voids provide us with a treasure trove of data on how large-scale cosmic structures evolve. With the advancement of projects such as the Dark Energy Survey and the Illustra simulation, we are piecing together the cosmic puzzle of void formation and their vital role in the universe's grand scheme. Even more awe-inspiring are the largest structures in the cosmos, the colossal formations that stretch across unimaginable distances, often spanning hundreds of millions of light years. These structures, galaxy clusters, superclusters, filaments of the cosmic web, and vast cosmic voids, form the backbone of the universe. Among them, superclusters stand out as some of the largest structures we have discovered. These gigantic conglomerates of galaxy clusters are bound together by gravity, creating vast networks of galaxies. A prime example is the Laniakea supercluster, which extends over 500 million light years and contains around 100,000 galaxies, including our own Milky Way. But the most awe-inspiring structure known to us is the Hercules Corona Borealis Great Wall, currently considered the largest known structure in the observable universe. This incredible cosmic wall, composed of galaxies, stretches an astounding 10 billion light years, challenging and expanding our understanding of cosmic scale and structure. These superclusters, interconnected by dark matter and intergalactic gas filaments, form the nodes and connections of the cosmic web. The filaments themselves are immense, often stretching hundreds of millions of light years. They act as the spine of the cosmic skeleton, guiding the formation and distribution of galaxies. At the same time, the vast voids punctuate the web, empty spaces that make up a significant portion of the universe's volume. Together, these structures offer crucial insights into the formation and evolution of the cosmos, helping astronomers piece together the distribution of dark matter and the influence of dark energy on the accelerated expansion of the universe. As our surveys continue and our understanding deepens, the grand scale of the universe and its intricate structures will undoubtedly keep unfolding before our eyes. Through future research and cutting-edge simulations, we will continue to reveal the hidden forces that drive the cosmos, revealing just how much there is yet to learn about the universe we inhabit. In recent years, the advancement of telescopic technology and computational simulations has enabled scientists to explore and map the vast structures of the universe with unprecedented detail. These innovations have opened the door to a deeper understanding of the cosmos, revealing the delicate interplay of forces that shape the universe on its grandest scales. The study of these massive cosmic structures not only enhances our knowledge of the fundamental principles of cosmology, but also illuminates the intricate forces that govern the universe's ultimate destiny. At the forefront of these discoveries are galactic superclusters, massive cosmic structures that are the largest coherent formations known to humanity. They represent a grand network, interwoven by gravitational forces and the expansive reach of cosmic expansion. These colossal formations, made up of multiple galaxy clusters and hundreds of thousands of individual galaxies, are connected by the threads of the cosmic web. These vast filaments form an intricate and interconnected network that spans billions of light years across the universe. While superclusters can be separated by immense distances, their gravitational influence reaches far beyond their visible boundaries. This subtle but powerful gravitational pull extends to neighboring structures, influencing their motion and the very fabric of space itself. What makes the interaction between superclusters so fascinating is the timescale over which these forces play out. Over the course of billions of years, superclusters engage in a slow yet monumental dance, shaping the motion and distribution of galaxies and dark matter. This interaction, sometimes referred to as peculiar velocity, refers to the movement of galaxies relative to the general expansion of the universe. Galaxies are drawn towards regions of high gravitational density, often leading to the formation of phenomena like the Great Attractor, a mysterious anomaly in space that pulls galaxies, including our own Milky Way, towards it. This movement serves as a powerful reminder that even in the vastness of space, everything is connected by invisible forces, pulling us all in one direction. The Great Attractor, a gravitational anomaly located within the Laniakea supercluster, is one of the most intriguing aspects of this cosmic phenomenon. Discovered in the late 20th century, it exerts an enormous gravitational force, pulling thousands of galaxies, including the Milky Way, towards it at speeds exceeding 600 kilometers per second. This peculiar motion, which occurs alongside the general expansion of the universe, suggests that an immense mass concentration exists in this region of space. However, the true nature of the Great Attractor has remained elusive for decades, primarily due to its location in the so-called zone of avoidance. This area of the sky is heavily obscured by the galactic plane of our Milky Way, making it difficult to observe using traditional optical telescopes. Yet, despite these challenges, astronomers have managed to peer through the galactic dust using sophisticated observations in various wavelengths, including X-rays and radio waves. These cutting-edge techniques have shed light on the complex structure hidden in the Great Attractor's gravitational grip. It is now understood that the Great Attractor is not a single point of mass, but rather a vast conglomeration of galaxy clusters, with the Norma cluster, Abell 3627, being one of the most prominent members. The Great Attractor is also part of an even larger cosmic structure, the Shapley supercluster, one of the densest and most massive regions in the nearby universe. This immense concentration of mass exerts its influence on the local group of galaxies, pulling them inwards, and also impacts the motion of other neighboring superclusters. As we continue to study these massive structures, both through observation and computational modeling, our understanding of the universe's large-scale architecture is rapidly evolving. Advanced surveys like the Sloan Digital Sky Survey and the Illustris TNG project are helping scientists unravel the complexities of these galactic giants, offering a glimpse into the forces at work that shape the cosmic web. These studies not only inform us of the dynamics of superclusters and galaxy clusters, but also provide valuable insights into the very nature of cosmic evolution. By mapping the motions and distributions of these structures, astronomers are painting a more complete picture of the universe's intricate history, one that spans billions of years and reveals the vast, interconnected forces that continue to shape the universe's destiny. Through these observations and simulations, we are beginning to see the universe not just as a vast, empty expanse, but as a dynamic, ever-evolving network with galaxies and superclusters locked in a complex, gravitationally driven dance that spans the eons. The cosmic web, with its filaments and voids, offers a stunning picture of how the universe is organized and how it continues to evolve, offering scientists new questions to explore and mysteries to unravel. Ultimately, these discoveries offer us a deeper understanding of the universe's past, present, and future, providing a profound glimpse into the forces that govern our existence and the cosmos as a whole. In the vastness of the universe, the study of gravitational forces at the largest scales enhances our understanding of the complex forces that shape the cosmos. It uncovers the intricacies of gravitational interactions that extend across unimaginable distances, offering insight into the distribution of both visible and unseen matter. As technology advances and observational surveys continue, astronomers are progressively revealing hidden aspects of this captivating cosmic mystery, piecing together a more comprehensive picture of the universe's grand design. A central element in this exploration is the role of dark matter halos, which are essential in the formation and evolution of galaxies. Acting as invisible scaffolding, these halos support the construction of galaxies by facilitating the collection and concentration of ordinary matter such as gas and dust. Dark matter makes up approximately 85% of the total mass in the universe, and its gravitational influence is critical for pulling together the ordinary matter needed to form stars and galaxies. Without these dark matter halos, the universe's ordinary matter would be too sparse to clump together and create the dense structures required for galaxies to emerge. The story of galaxy formation begins shortly after the Big Bang, when small fluctuations in the density of dark matter gave rise to gravitational wells. Over time, these fluctuations grew into clumps, which then attracted more mass, forming increasingly larger dark matter halos. As these halos merged, their combined gravitational pull helped shape the large-scale structure of the cosmos. The dark matter halos eventually created deep gravitational wells, pulling in ordinary matter. Once this matter fell into these halos, it began to cool and contract, leading to the formation of rotating disks of gas, precursors to the birth of stars and galaxies. The relationship between dark matter and ordinary matter is crucial at every stage of galaxy formation. From the gathering of gas to the processes that regulate star formation, dark matter halos govern the formation of galaxies. Cooling mechanisms in gas and feedback from phenomena such as supernovae and active galactic nuclei, AGN, further influence the growth of galaxies. However, the overarching gravitational framework is provided by the dark matter halo, which acts as the cosmic architect of galactic evolution. Beyond the initial formation of galaxies, dark matter halos continue to shape the dynamics and structure of galaxies. For instance, the rotation curves of spiral galaxies, plots that track the rotational velocities of stars at various distances from the galaxy's center, remain flat at large distances. This flatness defies expectations, as visible matter alone would cause a decline in rotational speed. The solution to this mystery lies in the presence of a dark matter halo surrounding the galaxy, exerting additional gravitational pull that accounts for the unexpected rotational behavior. Advanced simulations, such as those produced by the Eagle project, alongside observational data from instruments like the Hubble Space Telescope and the upcoming James Webb Space Telescope, are shedding light on the profound influence of dark matter halos. These studies not only deepen our understanding of galaxy formation, but also provide critical clues about the elusive nature of dark matter, one of the most fundamental puzzles in modern astrophysics. One of the most groundbreaking concepts in cosmology is cosmic inflation, a theory proposing that the universe expanded at an incredibly rapid rate immediately following the Big Bang. This expansion occurred in a fraction of a second, from roughly 10 to the power of negative 36 to 10 to the power of negative 32 seconds after the birth of the universe. The rapid inflationary phase increased the universe's size by a factor of at least 10 to the power of 26, smoothing out any initial irregularities and setting the stage for the large-scale structure we observe today. The theory of inflation was first introduced by physicist Alan Guth in the early 1980s to address several unresolved issues in cosmology, including the horizon problem, the flatness problem, and the absence of magnetic monopoles. At the heart of this theory is the hypothesized inflaton field, a high-energy field responsible for the exponential expansion of spacetime. Initially, in a metastable, high-energy state, the decay of the inflaton field released immense amounts of energy, causing spacetime to stretch at an unimaginable rate. This rapid expansion stretched quantum fluctuations in the inflaton field to macroscopic scales, laying the groundwork for the large-scale structures that we now see in the universe, such as galaxies and clusters of galaxies. These stretched quantum fluctuations are observed today as anisotropies in the cosmic microwave background, CMB, offering vital evidence of the early universe's behavior. As we continue to explore these cosmic phenomena, our understanding of the universe deepens. The intricate dance between dark matter and ordinary matter, along with the rapid expansion during cosmic inflation, provides the foundation for the universe's vast and intricate structure. With each new discovery, we get one step closer to unlocking the secrets of the cosmos. In the vast and uncharted depths of space, the universe has unfolded in ways that continually astonish and intrigue scientists. One of the most transformative events in its history was the Big Bang, a moment so profound that it marked the birth of everything we know: space, time, and matter. However, the tale doesn't stop there. After the Big Bang, there came the era of cosmic inflation, a period of rapid exponential expansion that altered the universe's fabric forever. As this inflationary phase came to an end, it transitioned the universe into the hot and dense state that we recognize as the aftermath of the Big Bang. The inflaton field, which was responsible for driving this rapid expansion, settled into its lowest energy state. In doing so, it decayed into particles and radiation, creating the fundamental ingredients necessary for the formation of atomic nuclei. This phenomenon set the stage for nuclear synthesis, where the first atomic elements were forged, and from there, the universe began its journey toward the formation of stars and galaxies. The rapid inflation also had a far-reaching consequence. It ensured that the observable universe, as we see it today, appears remarkably uniform and isotropic, meaning it looks the same in every direction. This homogeneity resolved a long-standing problem in cosmology, known as the horizon problem, which posed the question of how distant regions of space could have the same temperature and properties despite being far apart. Inflation answered this by stretching the universe so rapidly that distant regions of space were once in causal contact before inflation stretched them apart. The evidence for this radical theory, cosmic inflation, lies in the detailed measurements of the cosmic microwave background, CMB, the faint glow that marks the afterglow of the Big Bang. Missions such as the Cosmic Background Explorer, COBE, Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite have provided invaluable insights. These observations have revealed a nearly uniform early universe with slight temperature fluctuations in perfect alignment with the predictions made by inflation theory. And the story doesn't end there. As we push the boundaries of science, upcoming research aims to detect primordial gravitational waves, ripples in spacetime that may offer even more direct evidence of inflation, making the narrative of our universe's birth even more compelling. But the universe's mysterious makeup doesn't end with inflation. The presence of dark matter, an unseen substance that accounts for most of the universe's mass, continues to intrigue scientists. Unlike regular matter, dark matter doesn't emit, absorb, or reflect light, making it nearly impossible to detect directly. Yet, its presence can be inferred through its gravitational effects on visible matter. One of the most powerful methods of observing dark matter comes from the study of galaxy rotation curves. If we measure how fast stars at the outskirts of galaxies move, we find that they travel much faster than predicted by the visible mass alone. This discrepancy suggests the presence of dark matter, which accounts for approximately 85% of the universe's total mass. Another breakthrough tool is gravitational lensing. Here, dark matter's effects are detected by observing how it bends the light from distant stars and galaxies, a phenomenon predicted by Einstein's theory of general relativity. This bending of light acts as a cosmic magnifying glass, allowing scientists to map out the distribution of dark matter across vast distances. These maps have revealed a striking cosmic network, a cosmic web where dark matter forms a scaffolding for galaxy formation. These hidden structures, although invisible, can be traced through the tiny distortions they cause in the light traveling from the farthest reaches of the cosmos, offering a window into the unseen. Among the most fascinating celestial objects in this mysterious universe are magnetars, a type of neutron star. These incredible entities are born from the collapse of massive stars after they have exhausted their nuclear fuel. During this cataclysmic event, known as a supernova, the core of the star collapses into an incredibly dense neutron star, made primarily of neutrons. In some cases, this collapse is so rapid and intense that the magnetic fields of the star are amplified exponentially. Initially, the magnetic field may not be exceptional, but as the core shrinks to just 12 miles in diameter, the field lines are packed into an extraordinarily small space. In certain models, it's believed that this intense magnetic field is further strengthened through a process known as dynamo action, which occurs in the fluid and highly conductive interior of the newborn neutron star. These forces generate electric currents that amplify the magnetic field to unimaginable levels, reaching up to 1 quadrillion Gauss, or 1 trillion times stronger than Earth's magnetic field. After this intense birth phase, the magnetic field stabilizes but remains staggeringly powerful. This immense power occasionally triggers seismic activity on the magnetar's crust, unleashing bursts of X-rays and gamma rays. These bursts can outshine entire galaxies for brief moments, offering a celestial spectacle that captures the imagination of astronomers and casual observers alike. Fast radio bursts, FRBs, represent one of the most enigmatic and mysterious phenomena in modern astrophysics. These sudden, high-energy bursts of radio waves last only a few milliseconds, yet they carry an immense amount of energy. The origin of FRBs has puzzled scientists since their discovery, with numerous theories attempting to explain their origins. Some hypothesize that they might be linked to the collapse of massive stars, while others propose that magnetars could be the source. Regardless of their origin, FRBs remain one of the greatest unsolved mysteries in the universe, further fueling the quest for understanding the complex and dynamic cosmos in which we live. Each of these cosmic phenomena, from inflation to dark matter, magnetars to fast radio bursts, offers a glimpse into the vast and intricate workings of the universe. With each new discovery, we move closer to unraveling the mysteries that have shaped the cosmos, uncovering more of the secrets that lie in the vast, starry expanse. In the vast expanse of the universe, one leading hypothesis suggests that fast radio bursts, FRBs, those mysterious and incredibly intense bursts of energy, are created by highly magnetized and rapidly rotating neutron stars known as magnetars. During the active phases of these extraordinary objects, magnetars can release unimaginable amounts of energy. This energy often comes from catastrophic events like starquakes or magnetic reconnection events, which are so violent that they can produce intense radio emissions. These emissions, traveling vast distances, are what we observe as fast radio bursts, flashing briefly but powerfully across our instruments here on Earth. However, there are alternative theories that offer even more intriguing possibilities. Some scientists propose that these enigmatic bursts could stem from catastrophic cosmic events, such as the collision of neutron stars or the collapse of a massive star into a black hole. These cataclysmic events, capable of unleashing an immense amount of energy, could certainly produce the powerful radio signals we detect. With such incredible power on display, it's no wonder these bursts illuminate our instruments and spark such curiosity. Even more fascinating are theories that delve into the realm of the unknown, proposing exotic origins. Could the interactions between pulsars and their surrounding environments be at play? Or perhaps, could advanced extraterrestrial technologies be responsible for these bursts, hinting at alien civilizations? While these ideas remain speculative, they open the door to exciting possibilities. Regardless of their origin, each detected FRB brings us one step closer to unraveling this cosmic mystery. It is more than just the pursuit of knowledge. It is a reflection of human curiosity, of our relentless drive to understand the universe. These radio bursts not only demonstrate the extreme and often violent conditions of our universe, but also highlight the ingenuity of human exploration, ever determined to unlock the secrets of the cosmos. Now, consider the incredible survival of a star through a supernova explosion. This dramatic event is a testament to the intricate dynamics that govern stellar evolution. Not all stars meet their end in total destruction during these cataclysmic explosions. Some manage to survive, leaving behind a remnant core. Depending on the mass of the star that exploded, this remnant can evolve into one of two incredible objects: a neutron star, or a black hole. For stars of lower mass, the resulting remnant is typically a neutron star, a dense, city-sized object made almost entirely of neutrons. This occurs when the core collapses under immense gravity, packing its matter so tightly that it can no longer collapse further. The force of neutron degeneracy pressure provides just enough resistance to prevent further collapse, resulting in this fascinating stellar remnant. In contrast, for stars that begin their lives with exceptionally high mass, the core's collapse continues, ultimately forming a black hole. Once the remnant's gravitational pull becomes so intense that not even light can escape, the black hole is born. It is here, at the event horizon, where the laws of physics as we know them break down, and where mysteries of space-time continue to confound our understanding. Interestingly, the formation of these stellar remnants is often influenced by binary star systems. When one star in such a system undergoes a supernova, it can impulsively send its companion star flying into space. The surviving star might remain in orbit around the newly formed neutron star or black hole, or it could become a runaway star, traveling alone through the cosmos. This dynamic process not only demonstrates the incredible power of these stellar explosions, but also shows the resilience of some stars, leaving behind objects that continue to captivate astronomers, offering us clues about the profound processes of cosmic evolution. Meanwhile, the pulsations of variable stars like Cepheids and RR Lyrae stars offer yet another window into the complexity of stellar behavior. These stars undergo rhythmic oscillations driven by a delicate balance between pressure and gravity within their interiors. One of the primary mechanisms responsible for these pulsations is known as the kappa mechanism. During this process, the star's outer layers become partially ionized, which in turn increases their opacity. This causes heat to become trapped, causing the outer layers to expand. As the star expands, the opacity decreases, allowing the heat to escape and leading to the cooling and contraction of the star's outer layers. This cyclic compression and expansion results in the pulsations we observe. For certain types of variable stars, such as Cepheids, these pulsations are influenced by a deep layer heating effect. In Cepheids, the ionization of helium plays a critical role. When helium is singly ionized, it absorbs energy, causing the star's outer layers to swell. As these layers expand and cool, the helium recombines, releasing energy, which then drives the outer layers to contract again. This cycle of heating and cooling is what powers the rhythmic pulsations observed in these stars, creating a predictable pattern of expansion and contraction. These pulsations are not mere curiosities. They are crucial tools for astronomers. By studying the period and luminosity of pulsating stars, scientists can accurately calculate their distance from Earth. This measurement, in turn, allows for a much clearer understanding of the scale of the universe, helping astronomers to map the structure of our Milky Way galaxy and beyond. Through this process, variable stars become vital instruments in our quest to understand the cosmos on a deeper level. In the fascinating world of binary star systems, mass exchange occurs through a complex and dynamic process, largely driven by the gravitational interactions between the stars. One of the most significant ways this mass exchange happens is through a phenomenon known as Roche lobe overflow. When one star in a binary system grows large enough, it expands to fill its Roche lobe, the region around a star where material is gravitationally bound to that star. During its red giant phase, this expansion can lead to material being transferred from the larger star to its companion. This interaction significantly affects the evolution of both stars, potentially altering their fates in the process. Each of these cosmic phenomena, from magnetars and FRBs to supernovae and binary systems, provides us with a piece of the puzzle of how our universe operates. As we continue to study these objects, we inch closer to unraveling the profound mysteries that lie beyond our planet, opening new frontiers in both astronomy and the human spirit of discovery. In the vast cosmic dance of stars, interactions within binary systems play a pivotal role in shaping the evolution of both stars involved. When one star overflows its Roche lobe, a boundary defined by the gravitational influence of its companion, material can spill over and transfer to the second star. This process can have profound effects on both stars. The recipient star often experiences a rejuvenation, gaining fresh vitality and shining brighter than ever. Meanwhile, the donor star is stripped down to its core, experiencing a dramatic loss of mass. In certain cases, this interaction is so intense that it transforms the stars in unexpected ways, altering their evolution in ways we can't always predict. Additionally, a mechanism known as stellar wind accretion adds another layer of complexity to this cosmic exchange. In this process, mass transfer occurs through winds emitted from the surface of the more evolved star. These winds are captured by the gravitational field of the companion star, especially if the stars are close to each other. Unlike Roche lobe overflow, which is often dramatic and violent, stellar wind accretion is a slower and more subtle process. While it might not create immediate fireworks in the way Roche lobe overflow does, its effects on the stars involved can still be profound. Such interactions not only shape the evolutionary paths of these binary stars, but also create phenomena like X-ray binaries. In X-ray binaries, a compact object such as a neutron star or black hole accretes mass from its companion, producing powerful X-rays as the matter is consumed. Among the most intriguing and mysterious outcomes of stellar interactions are blue stragglers, stars that appear anomalously young, hot, and bright compared to other stars in the same stellar population. These enigmatic objects are most commonly found in globular clusters, where dense environments foster interactions that wouldn't be seen in more isolated settings. According to standard stellar evolution models, stars of similar mass should age at similar rates, but blue stragglers defy this prediction, appearing as though they are much younger and more vigorous than their neighbors. Several theories attempt to explain the origins of these unusual stars, with two main mechanisms standing out: stellar collisions and mass transfer in binary systems. In the dense confines of globular clusters, where stars are packed closely together, the chance of a direct collision or merger increases dramatically. When two stars collide, they may merge into a single larger star, an event that produces a rejuvenated star that burns hotter and appears bluer than its peers. This merger effectively resets the star's evolutionary clock, making it seem like a youthful, vibrant object despite its actual age. On the other hand, mass transfer in binary systems offers another potential explanation. In these systems, one star may overflow its Roche lobe and transfer mass to its companion, invigorating it with newfound energy. The recipient star becomes hotter and brighter, slowing its own aging process and creating the illusion of a rejuvenated younger star, one that now fits the profile of a blue straggler. Taken together, these processes, collisional rejuvenation and mass transfer, form a robust framework for understanding blue stragglers. These stars appear to defy the conventional wisdom of stellar aging, standing out as remarkable exceptions in the broader stellar population. As a result, they remain a fascinating subject of study in stellar astrophysics. Moving on to another captivating class of celestial objects, brown dwarfs are often described as the missing link between planets and stars. These intriguing objects form in a similar manner to stars, originating in the dense regions of molecular clouds. As these clouds collapse under their own gravity, smaller clumps form and contract, heating up their cores in the process. However, unlike stars, brown dwarfs do not accumulate enough mass to ignite sustained hydrogen fusion. The threshold for star formation is typically around 75 times the mass of Jupiter, and brown dwarfs fall short of this critical mass, preventing them from undergoing the nuclear fusion that powers stars. Instead, brown dwarfs embark on a fascinating journey of gradual cooling and contraction. Though they may briefly ignite deuterium fusion in their early stages, this process is short-lived and insufficient to provide a sustained energy output. Over time, brown dwarfs fade, emitting light primarily in the infrared spectrum. Their atmospheres, similar to those of gas giant planets, can exhibit complex weather patterns, including cloud bands and storms. Despite their lack of sustained nuclear fusion, brown dwarfs occupy an important place in our understanding of celestial objects, offering valuable insights into both planetary and stellar formation processes. These objects serve as a bridge between the two, revealing a unique perspective on the diverse array of celestial bodies that populate our universe. From the rejuvenating forces of mass transfer to the mysterious cooling of brown dwarfs, the cosmos never ceases to amaze us with its complexity and wonders. In the vast expanse of the universe, one of the most extraordinary phenomena that capture the imagination of scientists and astronomers alike is the gamma ray burst, GRB. These bursts of gamma rays, which are the most powerful explosions known to humanity, are often triggered by the cataclysmic death of massive stars. But how do these bursts occur? What forces are at play in these extreme cosmic events? When a star far more massive than our Sun runs out of fuel, it no longer has the energy to support its outer layers. As a result, the star's core collapses, triggering an event of astronomical proportions. This collapse can lead to what is known as a hypernova, an incredibly violent type of supernova. As the core implodes, it can form a rapidly spinning black hole or a highly magnetic neutron star, also referred to as a magnetar. This is where the true spectacle begins. The intense gravitational forces combined with the rapid rotation of these objects drive matter into highly energetic jets, which pierce through the star's outer layers. These jets can accelerate particles to nearly the speed of light, creating violent collisions that release vast amounts of gamma rays. If the jets are aligned with Earth, we observe a gamma ray burst. These bursts can last anywhere from milliseconds to several minutes, creating an enormous flash of gamma rays that is followed by an afterglow visible in multiple wavelengths, including X-rays, optical light, and even radio waves. The afterglow occurs as the jet interacts with the interstellar medium, revealing the tremendous forces at play in these events. In addition to the explosive death of stars, gamma ray bursts can also be triggered by the collision of compact stellar remnants in binary systems. This includes violent mergers, such as those between two neutron stars or a neutron star and a black hole. These collisions, though different from the collapse of a star, also produce incredibly energetic jets of particles. The interaction between extreme gravitational and magnetic forces creates a spectacular release of gamma rays, adding to the mystery and grandeur of these cosmic phenomena. Whether triggered by the death of a massive star or the catastrophic collision of compact objects, gamma ray bursts are a testament to the universe's raw power and its ability to generate incomprehensible amounts of energy. Equally fascinating are the neutron stars, remnants of stars that have undergone a supernova explosion. When the core of a massive star collapses, it forms a neutron star, which is incredibly dense, often containing more mass than the Sun, but within a sphere just 12 miles across. The collapse causes the star to spin at incredibly high speeds, sometimes hundreds of times per second, conserving angular momentum. The magnetic field of the collapsing star also amplifies to extraordinary strengths, up to 1 trillion times stronger than Earth's own magnetic field. This magnetic field channels charged particles to the poles of the neutron star, accelerating them to relativistic speeds. As a result, these high-energy particles emit electromagnetic radiation, which can include radio waves, X-rays, and gamma rays. However, the magnetic poles are not aligned with the star's rotation axis. As the neutron star spins, the beams of radiation sweep across the sky like a cosmic lighthouse. When one of these beams points toward Earth, we detect a pulse of radiation each time the beam crosses our line of sight. This produces the periodic signals that we observe as pulses. The regularity of these pulses is astounding, and some neutron stars, known as pulsars, act as some of the most precise cosmic clocks in existence. These pulses have been invaluable in advancing our understanding of the universe. They are used for testing the limits of general relativity, probing the interstellar medium, and even detecting gravitational waves. Pulsars thus provide a glimpse into the extreme environments that exist at the end of a massive star's life cycle, where precision and violence collide. On the other side of the star spectrum, we have the hypergiants. These massive, luminous stars, among the largest in the universe, are characterized by their extreme brightness. Their size, high temperatures, and rapid rates of fusion make them shining beacons in the night sky. Hypergiants typically have masses ranging from tens to more than 100 times that of our Sun, triggering intense nuclear fusion reactions in their cores. These reactions generate enormous amounts of energy, which radiates outward to sustain the star's structure. The gravitational pressure at the core of these massive stars facilitates these intense fusion reactions. while their surface temperatures often soar into the tens of thousands of degrees Kelvin. This high temperature results in the emission of an immense amount of light, particularly in the ultraviolet spectrum. Consequently, hypergiants are not only bright, but also extraordinarily hot, contributing to their extreme luminosity. In addition, their enormous radii enhance their brightness even further, making them some of the most awe-inspiring objects in the cosmos. From the explosive death of massive stars to the merger of compact remnants, from the rhythmic pulses of neutron stars to the blistering light of hypergiants, the universe is home to phenomena that push the boundaries of our understanding. These incredible cosmic events are not just beautiful to behold, but they also offer us the keys to unraveling the mysteries of the universe. In the vast expanse of the cosmos, the Stefan Boltzmann law reveals a profound connection between the energy emitted by a star, its surface area, and its temperature. This law tells us that the luminosity of a star, essentially how much energy it radiates, is directly proportional to both its surface area and the fourth power of its surface temperature. When applied to massive stars, particularly hypergiants, this equation helps explain why they emit such colossal amounts of energy, far surpassing their intrinsic properties. Hypergiants, the titans of the starry sky, exhibit remarkable behaviors that push the boundaries of our understanding of stellar life cycles. These colossal stars often experience dramatic mass loss through intense stellar winds, driven by the very radiation pressure they generate. These winds are not just a gentle breeze. They are immense outflows of gas that can carry vast amounts of material away from the star. As this gas escapes, it can form extended luminous shells surrounding the star, often intensifying its brightness. The complex interplay between the star's radiation and the expelled gas, manifesting through phenomena like shocks and recombination, further amplifies its luminosity, creating a breathtaking spectacle of light that makes hypergiants some of the most dazzling and powerful objects visible in the night sky. Despite their awe-inspiring brilliance, hypergiants have relatively short lifespans on the cosmic scale, burning through their fuel at an incredibly rapid pace. Moving from the dazzling lights of hypergiants to the mysterious shadows of the universe, the formation of supermassive black holes, SMBHs, in the centers of galaxies remains one of the most captivating and perplexing subjects of astrophysical research. These behemoths, often possessing masses millions to billions of times that of our Sun, seem to defy the standard processes of stellar evolution. One leading theory suggests that SMBHs form from the direct collapse of massive gas clouds in the early universe. Unlike typical stars, which form through a gradual process of nuclear fusion and gravitational collapse, these gas clouds could be dense enough to collapse directly into a black hole, skipping the star stage entirely. This phenomenon could set the stage for the black hole to grow and accrete more mass over time. Another possible formation path involves the merger of intermediate mass black holes, which are remnants of massive stars or smaller black holes found in dense star clusters. Over time, gravitational interactions and dynamical friction would cause these intermediate mass black holes to spiral toward the center of their galaxy, where they would eventually merge into a more massive black hole. This process of hierarchical merging could explain the immense sizes of the supermassive black holes found in the hearts of today's largest galaxies. During active galactic nuclei, AGN phases, these SMBHs can consume vast amounts of gas, dust, and other cosmic matter, emitting an extraordinary amount of energy. Often observed as quasars, these emissions provide crucial insight into the growth and evolution of these enigmatic objects. Galaxy mergers also contribute significantly to the growth of SMBHs. When two galaxies collide, their central black holes can spiral toward each other, eventually merging into a single, much larger supermassive black hole. This merging process not only combines the masses of the two black holes, but also triggers the accretion of additional gas and stars, fueling further growth. Understanding the role of SMBHs in galaxy evolution is key to comprehending how galaxies form, develop, and interact with one another. The influence of these immense objects is profound, shaping the star formation processes, dynamics, and matter distribution across the universe. The intricate nature of supermassive black holes reveals the complex dance of gravity and matter taking place over cosmic timescales. Yet, despite all we've learned, these objects still hold many secrets. One of the greatest mysteries in modern theoretical physics revolves around what happens to information that falls into a black hole. This issue, often called the black hole information paradox, challenges the very foundations of physics. According to classical general relativity, any matter or information crossing a black hole's event horizon is lost forever, swallowed up and irretrievably trapped within. The only observable qualities of a black hole are its mass, electric charge, and angular momentum, a principle known as the no-hair theorem. However, this classical view collides with the principles of quantum mechanics, which demand that information be conserved and not destroyed. This conflict has sparked extensive theoretical work as scientists strive to reconcile general relativity with quantum mechanics. One breakthrough came from Stephen Hawking, whose work revealed that black holes can emit radiation due to quantum effects near the event horizon. This radiation, now known as Hawking radiation, has become a central piece of the puzzle, offering a potential pathway to understanding how information might escape a black hole and whether the paradox can ever be resolved. As we continue to explore the universe's most extraordinary phenomena, the study of hypergiants, supermassive black holes, and the fundamental principles that govern them offers us a deeper understanding of the forces shaping our cosmos. These majestic, powerful, and mysterious objects challenge us to think beyond our current knowledge, pushing the boundaries of science and inviting us to gaze into the heart of the universe itself. In the vast and mysterious depths of space, black holes are among the most enigmatic objects in the universe. While these cosmic giants are known for their insatiable gravitational pull, drawing everything within their reach, they also present an intriguing puzzle for scientists. One of the most perplexing issues revolves around the fate of the information that falls into them. As black holes slowly lose mass and eventually evaporate due to Hawking radiation, a question arises. Does the information that once resided inside the black hole vanish along with it? Various theories have been proposed to solve this conundrum, but none have provided a definitive answer. One intriguing suggestion is that the information might be encoded in the very Hawking radiation emitted by the black hole. However, this concept is controversial because it raises concerns about how such encoding could occur without violating fundamental principles of quantum mechanics. Another potential solution is the theory of black hole complementarity. This theory posits that information is both reflected at the event horizon and passes through it, yet no observer can detect a violation of information preservation. This suggests that the event horizon acts as a kind of boundary where information can be encoded in a way that maintains consistency with quantum laws. A more speculative idea, the firewall hypothesis, introduces the notion of an energetic barrier at the event horizon that would destroy incoming information. While this theory offers an interesting perspective, it also challenges the established principles of physics, particularly those related to the smooth nature of the event horizon. Despite these efforts, the black hole information paradox remains unresolved. It stands as a tantalizing intersection where the fundamental laws of quantum mechanics and general relativity collide. Finding a solution to this paradox could unlock the secrets of the universe, potentially offering a path toward a unified theory of quantum gravity that bridges the gap between these two pillars of physics. Equally fascinating is the evolution of binary black hole systems, which dance through the cosmos in a dramatic interplay of gravitational forces. These systems typically form when two black holes, often the remnants of massive stars, come together in a binary configuration. Such systems can also emerge through dynamic interactions within dense star clusters, where black holes may gravitationally capture each other. Once a binary black hole system is in place, its evolution is dictated by the emission of gravitational waves, as predicted by Einstein's theory of general relativity. These waves, which ripple through the fabric of space-time, carry away energy and momentum from the system, causing the black holes to spiral toward each other over time. This process is gradual, unfolding over millions to billions of years. depending on the initial separation and masses of the black holes. As the black holes orbit each other, their loss of energy and angular momentum accelerates, leading them into tighter and faster spirals. Eventually, when the black holes come within a few hundred kilometers of each other, the emission of gravitational waves becomes incredibly intense. This final phase of inspiral culminates in the merger of the two black holes, a cataclysmic event that produces an immense burst of gravitational waves. These waves, detectable by advanced instruments like the Laser Interferometer Gravitational Wave Observatory, LIGO, and Virgo, have opened up a new frontier in astronomical observation. Through these detections, scientists can study black hole collisions in unparalleled detail, gaining insights into the properties of these enigmatic objects. After the merger, the newly formed black hole enters a ring-down phase, where residual energy is radiated away in the form of gravitational waves. Eventually, the black hole settles into a stable, rotating state. The entire process, from binary formation to merger and ring-down, offers crucial insights into the extreme behavior of gravity, revealing the complexities of black hole physics and the history of stellar evolution. Amid these cosmic phenomena, quasars shine as some of the most luminous objects in the universe. Powered by the intense activity within the cores of galaxies, quasars are fueled by supermassive black holes. As gas, dust, and other material fall into the gravitational well of these black holes, they don't simply fall straight in. Instead, they spiral inwards, forming an accretion disk. The friction within this disk heats the material to such extreme temperatures that the gravitational energy is converted into electromagnetic radiation. This process generates a stunning array of emissions, including visible light, ultraviolet light, and X-rays, making quasars some of the brightest objects in the universe. In this dance of cosmic forces, from the mysteries of black holes to the brilliant eruptions of quasars, the universe reveals its most awe-inspiring phenomena. Each discovery brings us closer to understanding the nature of reality itself, pushing the boundaries of our knowledge and uncovering the fundamental forces that shape the cosmos. The process begins when an accretion disk forms around a supermassive black hole. As material in the disk spirals inward, it is drawn closer and closer due to the immense gravitational forces at play. These forces, combined with intense friction and frequent collisions between particles, generate extraordinary heat, causing the disk to glow with a brilliant light. A portion of the gravitational energy from the infalling material is converted into radiation, further intensifying the brightness. In addition to the radiant energy, the powerful magnetic fields near the black hole channel some of this hot gas into relativistic jets. These jets, shooting outward at nearly the speed of light, travel perpendicularly to the accretion disk and emit vast amounts of radiation across the entire electromagnetic spectrum. The sheer volume of material being pulled into the black hole at such a rapid pace allows quasars to achieve a luminosity greater than that of entire galaxies. In fact, a single quasar can shine brighter than all the stars in its host galaxy combined. Despite the staggering distances that often separate us from these cosmic powerhouses, sometimes billions of light years, their extraordinary brightness makes them visible to us, even from such great distances. This visibility makes quasars invaluable tools for studying the early universe. Their intense luminosity is not just a spectacle. It provides crucial insights into the mechanisms of energy conversion occurring near supermassive black holes. These processes, in turn, help us understand both black hole physics and the evolution of galaxies. At the same time, intermediate mass black holes, those with masses between 100 and 100,000 times that of our Sun, present a unique cosmic puzzle. While stellar mass black holes form from the collapse of massive stars, and supermassive black holes are typically found at the centers of galaxies, the origin of these intermediate mass black holes is still largely unclear. One hypothesis suggests that they may form through the merging of smaller black holes and neutron stars in densely packed stellar environments, such as globular clusters. In these crowded regions, gravitational interactions between stellar remnants could lead to frequent collisions and mergers, gradually building up a black hole of intermediate mass. Another theory proposes that intermediate mass black holes might be the remnants of the first stars, known as population 3 stars, that existed in the early universe. These primordial stars were massive and devoid of heavier elements. Upon their collapse, they could have directly formed black holes with masses exceeding that of typical stellar mass black holes, skipping over some evolutionary stages. Furthermore, gas accretion in young, dense star clusters might fuel the growth of these black holes over time. Indirect evidence for the existence of these elusive objects comes from X-ray emissions and gravitational wave detections. However, despite these hints, direct observation and confirmation remain a significant challenge. Equally fascinating are primordial black holes, which are theoretical remnants from the early universe. Unlike the black holes formed from stellar collapse, primordial black holes are thought to have formed shortly after the Big Bang, just 1 second later, due to extreme density fluctuations in the young cosmos. Depending on the nature and timing of these density peaks, primordial black holes could range in mass from tiny subatomic scales to thousands of times the mass of our Sun. Some theories even suggest that these primordial black holes could be a key component of dark matter. What makes primordial black holes particularly intriguing is their potential role in various cosmic phenomena. Smaller primordial black holes, with masses roughly equivalent to that of a mountain, may have evaporated by now due to Hawking radiation. This process, theorized by physicist Stephen Hawking, predicts that black holes emit radiation and gradually lose mass over time. If any of these small black holes are still evaporating today, they could potentially be detectable through bursts of high-energy gamma rays. On the other hand, larger primordial black holes that did not completely evaporate might still be lurking in the universe. These could influence the structure of the cosmos and may be indirectly observed through their gravitational effects. For instance, the gravity of these black holes could distort the light from stars behind them, creating phenomena such as microlensing events. Thus, whether it is the astonishing energy output of quasars, the mysterious formation of intermediate mass black holes, or the enigmatic role of primordial black holes in the cosmos, the study of black holes continues to unlock profound mysteries of the universe, reshaping our understanding of the fundamental forces and events that govern everything from the tiniest particles to the grandest cosmic structures. In this vast cosmos, few phenomena are as perplexing and captivating as primordial black holes. Their potential to exist in a broad spectrum of masses and behaviors showcases their elusive yet tantalizing nature. Our pursuit of understanding the universe constantly brings us face to face with these enigmatic objects. Black holes, with their immense gravitational power, have a profound and unique impact on the very fabric of time itself, especially in their immediate surroundings. This phenomenon, known as gravitational time dilation, was predicted by Albert Einstein's groundbreaking theory of general relativity. In essence, the stronger the gravitational field, the more time slows down when viewed from a weaker gravitational field. As one approaches a black hole, this effect becomes increasingly intense, and the closer you get, the more pronounced it becomes. Imagine an astronaut drifting toward a black hole. To a distant observer, the astronaut's clock would appear to tick slower and slower as they approach the event horizon, the boundary beyond which not even light can escape the black hole's pull. If the astronaut were to remain motionless just outside this event horizon, time would almost come to a halt for them, from the perspective of someone far away. However, the astronaut would experience time as normal, no change to their own sense of reality. But looking outward, the universe would appear to speed up. Years of cosmic events could seem to unfold in mere moments. This disparity in time perception isn't just a theoretical idea, it carries real implications for astrophysics and space travel. Black holes provide a natural laboratory where we can test our understanding of gravity and the fabric of space-time itself. In fact, the intense time dilation near black holes offers a unique vantage point for observing matter's behavior in extreme conditions. Take the accretion disks, for instance. These swirling disks of matter moving at incredible speeds. Observations of their behavior provide tangible evidence for relativistic effects, reaffirming Einstein's predictions. These disks, formed as matter spirals toward a black hole, are not only luminous but extraordinarily hot due to the conversion of gravitational potential energy into heat and electromagnetic radiation. Yet the true spectacle occurs when this interaction gives rise to the creation of energetic jets, some of the most powerful and mystifying phenomena in the universe. These jets can stretch across tens of thousands of light years, originating from the complex interplay of forces within the accretion disk around a black hole. But the formation of these jets isn't a simple matter of matter falling into a black hole. The key lies in the magnetic fields generated by the influng material. These magnetic fields twist and coil due to the rotational energy of the black hole and the accretion disk, setting the stage for the formation of narrow, focused beams of energy. Through a process known as the Blandford-Znajek mechanism, energy is extracted from the rotating black hole and transferred to these magnetic fields. This results in the acceleration of particles at nearly the speed of light, forming jets that shoot out along the black hole's rotational axis. These jets are not just energetic marvels, but they also interact with the interstellar medium, creating shock waves that further accelerate particles. This interaction results in high-energy emissions that can be detected across a wide range of wavelengths, from radio waves to gamma rays. The influence of these jets is far-reaching. Despite the black hole at their center being compact and small, their effect on the surrounding galaxy is immense. These jets can shape the environment, affecting star formation and altering the distribution of matter within the galaxy. Thus, even though black holes themselves are relatively tiny in comparison to the vast universe around them, their power reaches across immense distances, demonstrating the raw, untamed energy these objects command. One of the most remarkable achievements in the study of black holes is the detection of gravitational waves from black hole mergers. This endeavor relies on the most sensitive and sophisticated scientific instruments ever designed, the Laser Interferometer Gravitational Wave Observatory, LIGO, and its counterpart, the Virgo Observatory. Gravitational waves, predicted by Einstein's theory of general relativity, are ripples in the very fabric of space-time itself, caused by the violent interactions between massive objects like colliding black holes. These ripples can be detected by LIGO and Virgo, allowing scientists to observe events that would otherwise remain hidden, providing a new, groundbreaking way to study the universe. The intricate dance between these cosmic giants, the black holes, their accretion disks, their jets, and the gravitational waves they produce, reveals a universe far more complex and powerful than we once imagined. Each discovery, whether it's time dilation or gravitational waves, brings us one step closer to unlocking the secrets of these awe-inspiring cosmic entities. Through continued observation and experimentation, we will continue to peel back the layers of the universe's most enigmatic phenomena, uncovering the hidden forces that govern the fabric of reality itself. When massive objects, like black holes, spiral toward each other and ultimately merge, they generate waves that ripple through the very fabric of space-time. These waves travel outward at the speed of light, distorting everything in their path as they stretch and compress the space around them. It's a cosmic dance that holds the power to unveil some of the most profound secrets of our universe. Gravitational waves are the name of these ripples, and their discovery has opened a new window into understanding the most violent and energetic events in the cosmos. Gravitational waves are detected by observatories such as LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo, which use cutting-edge interferometry technology. This process, which may sound complex, involves two long arms, each several kilometers in length, arranged in an L shape. A laser beam is split into two, with each beam traveling down one arm, reflecting off mirrors at the ends and then recombining at the starting point. Under normal conditions, these beams are set up in such a way that when they come back together, they cancel each other out. But when a gravitational wave passes through the detectors, something remarkable happens. It slightly alters the lengths of the arms. One gets compressed while the other stretches. This tiny change in distance on the scale of 1/10,000th of the diameter of a proton causes a shift in the laser pattern, creating a detectable signal. The precision needed to detect such minute changes is staggering. To achieve this level of sensitivity, the observatories must operate in extreme conditions, using advanced vibration isolation systems to eliminate any external noise or interference. In September 2015, LIGO made its groundbreaking first detection, confirming the merger of two black holes located about 1.3 billion light-years away. The recorded waveform matched the predictions made by general relativity, perfectly illustrating the black holes spiraling toward each other, merging, and then entering the final ring-down phase as they coalesced into a single, more massive black hole. This discovery marked the dawn of a new era in astrophysics, allowing us to study cosmic events not through traditional electromagnetic signals like light, but through the medium of gravitational waves. Since that first detection, numerous additional mergers have been observed, offering new insights into the frequency and characteristics of black hole mergers. Each new observation brings us closer to understanding the inner workings of these extreme cosmic phenomena. But what about objects that are the complete opposite of black holes? Enter the theoretical concept of white holes. While black holes are regions of space where nothing can escape once it crosses the event horizon, white holes are proposed as regions where nothing can enter, yet matter and energy are ejected outward. These objects are mathematically possible according to the equations of general relativity, but as of now, there is no physical evidence to support their existence. They remain confined to the realm of theoretical physics and speculation. The idea of a white hole is as mind-boggling as it sounds. If you were to encounter one, the experience would be drastically different from falling into a black hole. As you approached a white hole, you would be bombarded with a violent outpouring of energy and particles, ejected at nearly the speed of light. This barrage would create an environment so hostile that any form of matter, including a human, would be unable to get close enough to investigate further. But let's assume, for a moment, that you managed to survive this lethal onslaught and reach the event horizon of the white hole. Once there, the laws of physics would dictate that you couldn't enter. In fact, you would be repelled from the event horizon, unable to get any closer. If white holes were ever to be observed, it would create an extraordinary enigma tied deeply to the very nature of space-time itself. Some physicists speculate that white holes could be connected to black holes through wormholes, creating tunnel-like passages across the universe. This speculative idea brings forth captivating possibilities. What if white holes were observable during high-energy cosmic events? Or perhaps, what if they are more common than we think, but remain hidden from our current detection methods? The study of such extreme and speculative objects pushes the boundaries of our understanding, encouraging us to challenge and reconsider the fundamental laws of nature. The universe is full of mysteries, and the theoretical and observable phenomena like black holes, white holes, and gravitational waves remind us of how much there still is to discover. These cosmic anomalies force us to rethink the laws of physics and ponder the deeper intricacies of space-time, urging us to keep exploring the unknown, no matter how mind-bending it may seem. In the vast expanse of space, certain cosmic mysteries stand out, capturing the attention of both scientists and the general public alike. Among these enigmas is Tabby's star, officially known as K-C 84628552, which has confounded astronomers since its discovery. Its most puzzling feature is the unpredictable dimming of its light, an anomaly that sets it apart from all other known stars. This strange phenomenon was first noticed by citizen scientists analyzing data from NASA's Kepler Space Telescope. As they sifted through the telescope's readings, they detected irregular, substantial dips in the star's brightness, dips that ranged up to a staggering 20% in intensity. These dips, unlike the gradual dimming caused by planets passing in front of a star, a process known as a transit, were highly erratic and lacked a predictable pattern. For years, this has sparked wild speculation and led to a variety of theories. One prominent idea suggests that an uneven cloud of dust could be orbiting the star, with particles of varying sizes intermittently blocking the star's light. The irregularity of these dimming events may be a result of how the dust moves in and out of the star's line of sight, causing fluctuations in the amount of light we receive. Another possibility is that a disrupted cometary family, possibly caused by a gravitational encounter, is passing through the star system. As this cloud of comets moves in front of the star, it would intermittently block its light, creating a similar pattern of unpredictable dimming. But the mystery doesn't end there. Some theories go even further, suggesting the presence of a disintegrated planet or moon, with fragments from this celestial body scattering around the star and causing the irregular dips in brightness. Even more outlandish is the idea that Tabby's star could be surrounded by an alien megastructure, such as a Dyson sphere, designed to harness the star's energy. While this hypothesis has fascinated many, it remains speculative, with no direct evidence to support the existence of such a structure. Despite the many theories, astronomers continue to monitor Tabby's star, striving to unravel this cosmic mystery and better understand the forces at play. Beyond the mystery of Tabby's star, there's another astronomical wonder that has long intrigued scientists: the phenomenon of hypervelocity stars. These rogue stars are speeding through space at mind-boggling velocities, often exceeding 1 million miles per hour. Hypervelocity stars owe their extraordinary speeds to some of the most powerful gravitational engines in the universe. Many of them originate in the heart of our galaxy, near the supermassive black hole known as Sagittarius A. This black hole, located about 26,000 light-years from Earth, has a mass equivalent to 4 million suns. Its immense gravity is powerful enough to accelerate stars to velocities far beyond what we typically observe in the cosmos. One leading explanation for the creation of hypervelocity stars involves binary star systems that venture too close to Sagittarius A. As the two stars orbit one another, the black hole's gravitational force can cause a dramatic disruption, ejecting one of the stars at incredibly high speeds. The other star, caught in the black hole's gravity, is pulled in. This slingshot effect sends the remaining star rocketing outward, propelling it across the Milky Way at extraordinary speeds. Another mechanism for the creation of hypervelocity stars involves dense star clusters. In these crowded environments, stars can engage in close gravitational interactions, where one member of a binary system can gain an additional burst of velocity through complex gravitational encounters. This interaction can fling one star out of the cluster, sending it into a path that takes it hurtling across the galaxy. Whether through the slingshot effect of a supermassive black hole or interactions within star clusters, hypervelocity stars offer a fascinating window into the chaotic processes shaping our galaxy. Lastly, we turn to another star with peculiar behavior, the Baggian star, also known as WTF star. Its name comes from the "where's the flux" phenomenon that has puzzled astronomers with its erratic and unpredictable dimming patterns. Unlike other stars, whose changes in brightness can often be traced to regular causes like transiting planets or eclipsing companions, Baggian stars' dips in luminosity are far more erratic. These mysterious changes have left scientists scrambling for answers. One leading theory is that a complex cloud of dust particles is orbiting the star. The particles, which vary in size and density, create uneven dimming events as they intermittently block the star's light. Some researchers suggest that this dust could be the result of a disintegrating cometary family, with comets transitioning into an uneven dust cloud as they break apart. Adding another layer of intrigue, infrared observations have revealed that the star emits less heat than expected, suggesting that solid objects like asteroids or planetary debris may not be the culprits behind the dimming. This discovery has led many scientists to favor the dust hypothesis. Moreover, the star's occasional brightening could be the result of cometic fragments clearing out or moving into positions that allow more light to escape. As astronomers continue to observe and study the Baggian star, it remains one of the most compelling and mysterious objects in the cosmos, urging further investigation into the processes that drive stellar behavior. These celestial wonders, Tabby's star, hypervelocity stars, and the Baggian star, remind us that our universe is filled with unexplainable phenomena that defy our understanding. The search for answers continues, and with every new observation, we move a step closer to unraveling the secrets of the cosmos. Whether it's dust clouds orbiting distant stars, rogue stars racing through space, or the unexplained dimming of far-off suns, one thing is certain: the universe is far more mysterious and awe-inspiring than we could have ever imagined. The complex dance between orbital mechanics and the absorption of light by dust grains creates a dynamic and ever-evolving scenario. In this delicate interplay, the Boggian star sometimes bursts with unexpected brightness before gradually dimming again, providing astronomers with a challenge in understanding the fluctuations of its luminosity. Despite all the progress in the study of these phenomena, the Boggian star remains an enigma in the skies. Its unpredictable behavior continues to puzzle scientists, prompting them to explore new theories and hypotheses to explain its fluctuating brightness. Every discovery brings more questions, as this celestial body refuses to reveal its secrets easily, keeping researchers on their toes as they attempt to piece together the complex puzzle of its nature. On another front, the discovery of galaxies that appear to be devoid of dark matter has intrigued astronomers, as dark matter is traditionally considered an essential element for the formation and stability of galaxies. Dark matter, a mysterious and unseen substance, is believed to make up approximately 85% of the universe's total mass. It provides the gravitational framework necessary for galaxies to form and hold together. The sudden revelation of galaxies seemingly lacking this crucial ingredient forces scientists to reevaluate their understanding of galactic structure and evolution. Take, for instance, the galaxy NGC 1552 DF2, first observed in 2018. This galaxy's peculiar nature has sparked a wave of discussions and debates. Unlike any galaxy we've encountered before, NGC 1552 DF2 seems to have no visible dark matter. Its discovery has led to the formulation of several intriguing theories. One possible explanation centers around the role of baryonic matter, ordinary matter such as gas and stars. These components might interact in ways that mimic the effects of dark matter. Gravitational interactions with neighboring galaxies or high-velocity collisions might have caused these regular matter components to clump together, leaving behind a galaxy that appears deficient in dark matter. Another hypothesis suggests that NGC 1552 DF2 and possibly other galaxies like it may have formed in dense galaxy clusters. The intense gravitational forces within these clusters could strip away the outer dark matter halo of smaller galaxies, leaving behind a dark matter-poor remnant. Even further, interactions between galaxies, particularly tidal forces from close encounters, could expel dark matter while retaining the baryonic core. This could explain the dynamics observed in such galaxies, where the movement of stars and gas does not require the presence of additional dark matter. These groundbreaking findings push the boundaries of our current models of galaxy formation and dark matter distribution. As scientists continue to study these anomalies, our understanding of the cosmos expands, challenging previously held beliefs about the fundamental structure of galaxies and the universe itself. The study of dark matter deficient galaxies remains one of the most exciting and rapidly evolving frontiers in modern astrophysics, offering new avenues of discovery with each new observation. One of the most remarkable astronomical events in recent years has been the arrival of Oumuamua, the first known interstellar object to pass through our solar system. Discovered in October 2017 by astronomers using the Pan-STARRS 1 telescope in Hawaii, Oumuamua captured the attention of both scientists and the public alike. Its cigar-shaped appearance, approximately 10 times longer than it is wide, was unlike any object previously observed within our solar system. Initially classified as a comet, Oumuamua displayed no signs of typical cometary activity, such as the glowing coma or tail formed by sublimating ice as it approaches the sun. This lack of expected behavior led to a re-evaluation, and it was reclassified as an asteroid. However, the object's trajectory and velocity through the solar system defied easy explanation. As Oumuamua sped away from the sun, it exhibited an acceleration that couldn't be fully explained by gravitational forces alone. This mysterious acceleration sparked numerous theories, each attempting to account for the anomaly. One leading hypothesis suggested that the acceleration could be caused by outgassing, where jets of gas are expelled from the object's surface due to solar heating. Yet, despite this theory's initial appeal, the absence of detectable gas or dust particles during its passage made this explanation less likely. Another possibility posited that Oumuamua might be a fragment of a much larger object that was torn apart by gravitational forces. This fragmentation could explain its elongated shape and the peculiar behavior observed as it traveled through the solar system. Some more speculative theories even suggested that Oumuamua could be an artificial object, perhaps a probe sent by an advanced alien civilization. However, this remains a highly speculative notion with no substantial evidence to support such a claim. The arrival of Oumuamua has highlighted the need for further observations of interstellar visitors. These celestial travelers, so distant and mysterious, challenge our understanding of the universe and offer a glimpse into the vast unknowns that lie beyond our solar system. Scientists eagerly anticipate the next interstellar object to pass through our cosmic neighborhood, hoping that it might hold more clues about the origins of these enigmatic travelers, and perhaps even more about the secrets of the universe itself. In the vastness of our solar system, one of the most intriguing phenomena to arise from the passage of Oumuamua has been the discovery of subsurface oceans on certain moons and planets. These hidden liquid seas, tucked away beneath icy exteriors, spark deep curiosity about the conditions required to sustain water in a liquid state, despite the freezing temperatures on the surface. Moons like Europa, Enceladus, and Titan stand out as prime examples. Beneath their frozen crusts, vast oceans lurk, and understanding how they remain in liquid form offers us profound insight into planetary science. Take Europa, for instance, one of Jupiter's moons. The intense gravity of Jupiter exerts massive tidal forces on Europa, causing the moon to flex as it orbits the giant planet. This constant stretching and squeezing create friction within the moon's interior, generating heat, a process known as tidal heating. This heat prevents the water beneath Europa's icy surface from freezing completely, keeping it in a liquid state despite the extreme cold. Such tidal forces offer us an elegant solution to the mystery of how liquid water could exist beneath a solid shell of ice. Enceladus, a smaller moon of Saturn, offers a similar spectacle. Its icy surface is punctuated by cryovolcanoes that eject jets of water vapor and organic compounds, suggesting the presence of a subsurface ocean. These eruptions are fueled by tidal interactions between Enceladus, Saturn, and other moons within the system. The moon's internal heat, generated by the decay of radioactive elements within its rocky core, further supports the persistence of liquid water beneath the surface. The combination of tidal forces and radioactive decay creates a perfect environment for maintaining a subsurface ocean that may harbor the potential for life. On Titan, Saturn's largest moon, the situation takes on a slightly different form. Titan's thick atmosphere, composed primarily of nitrogen and methane, plays a crucial role in regulating the temperature. The moon's dense atmosphere creates a strong greenhouse effect, trapping heat and preventing the surface from becoming too cold. This atmospheric warmth helps sustain a subsurface ocean which lies beneath Titan's icy crust. Unlike the tidal forces driving Europa and Enceladus, Titan's ocean is protected by the moon's atmosphere, making it an entirely different yet equally fascinating environment for potential life to thrive. These subsurface oceans are not merely scientific curiosities, they hold the promise of discovering extraterrestrial life. Enclosed from the harsh conditions of the surface, these liquid water environments could harbor microbial life or even more complex organisms. Missions like the Europa Clipper and Enceladus Life Finder are designed to explore these moons further, probing the depths of their icy shells to uncover the secrets hidden beneath. The search for life beyond Earth is no longer confined to distant exoplanets. It may lie in the oceans of these icy moons waiting to be discovered. Meanwhile, another mystery has captivated astronomers: the enigmatic flashes of light observed on the moon's surface, known as transient lunar phenomena, TLP. For centuries, these mysterious events have puzzled scientists. They range from brief bright spots to colorful glows, sometimes lasting only seconds, at other times a few minutes. Although the causes remain unclear, several theories have emerged, drawing on recent observations and research. One of the leading theories revolves around meteoroid impacts. When small meteoroids or cosmic debris collide with the moon's surface at high speeds, they release vast amounts of energy, producing flashes of light that can be seen from Earth. Unlike Earth, the moon lacks an atmosphere to burn up these incoming objects, leading to frequent and unobstructed impacts. These collisions can create visible bursts of light, which are often the most noticeable form of TLP. Another possible cause of these flashes is lunar outgassing. This process involves the release of gases from beneath the moon's surface, potentially triggered by tidal stresses from the gravitational pull of Earth. As these gases escape into the vacuum of space, they may interact with lunar dust or even fluoresce on their own, generating temporary flashes of light. This theory adds another layer of mystery to the phenomenon. A third explanation involves electrostatic phenomena. The moon's surface is covered by a fine layer of electrostatically charged dust. Solar radiation or solar wind can disturb these particles, causing them to levitate or shift position. As these charged dust particles move, they can reflect sunlight in unpredictable ways, creating brief, glimmering flashes of light. This could explain some of the transient phenomena observed on the lunar surface. While no single explanation can account for all observed TLP events, ongoing lunar missions are working to shed more light on the mystery. Lunar orbiters, equipped with high-resolution cameras and spectrometers, continue to monitor and record these occurrences. With more data, scientists aim to better understand the dynamic processes at work on the moon's surface, enriching our knowledge of its geologic and impact activity. Lastly, stars that defy the models of stellar evolution present a thrilling challenge to astrophysics. These enigmatic stars challenge our understanding of how stars live and die, forcing scientists to rethink and refine their theories of stellar evolution. These strange, rebellious stars don't fit into the neat categories established by previous models, offering new avenues of exploration into the heart of astrophysical science. In conclusion, whether it's the mysterious subsurface oceans of Europa, Enceladus and Titan, the puzzling flashes on the moon, or the stars that refuse to obey established rules, our exploration of the cosmos reveals new and exciting mysteries with each discovery. These phenomena not only challenge our current understanding, but also inspire us to ask deeper questions about the nature of life, the universe, and everything that lies within it. In the vast expanse of the universe, we find numerous mysteries that challenge conventional models of stellar evolution. One of the most intriguing of these anomalies is the presence of blue straggler stars within globular clusters. According to traditional models of stellar life cycles, stars within these dense clusters are expected to be old, red, and nearing the end of their existence. However, blue stragglers contradict this expectation. They shine brighter, burn hotter, and appear younger than their neighbors, standing out as clear anomalies in these ancient systems. The leading explanation for blue stragglers revolves around the idea of stellar collisions or mergers in these densely populated environments. In the crowded surroundings of globular clusters, close encounters between stars happen frequently, leading to dramatic interactions. When two stars collide or merge, they can form a single, more massive star. This newly formed star burns much hotter and bluer, giving it the appearance of being rejuvenated, thus seeming much younger than the average star in the cluster. This hypothesis not only accounts for the blue stragglers themselves, but also opens up new avenues for understanding the processes that shape star clusters. Another fascinating mystery involves the existence of ultramassive, highly luminous stars, known as Wolf-Rayet stars. These stars defy the typical models of stellar evolution, as they seem to be in the late stages of their life cycles, having lost most of their outer hydrogen layers. What remains are their hotter helium-burning cores, which shine with an intensity far beyond typical stars. The mechanism behind such extensive mass loss is thought to be driven by intense stellar winds. These winds are propelled by the extreme luminosity and surface temperatures of the stars, expelling material at rates thousands of times greater than ordinary stars. This process drastically alters the structure and eventual evolution of these stars, pushing them toward a destiny that current models are struggling to explain. Moreover, certain stars, known as carbon-enriched metal-poor stars, further challenge our understanding of stellar formation. These stars contain unusually high levels of carbon compared to other heavy elements. Their presence raises questions about the early stages of nucleosynthesis, the process by which elements are formed in stars. The carbon in these stars hints at more complex, poorly understood processes in the formation of the universe's first stars. These discoveries reveal the diversity and unpredictability of stellar evolution prompting astronomers to rethink established theories and consider alternative paths of stellar life cycles. As observational technology advances and data resolution improves, these stellar anomalies will continue to be a focal point of study. They force astronomers to refine existing models of stellar evolution and stretch the boundaries of our understanding of the cosmos. Each new discovery about these extraordinary stars propels us forward in the quest to unlock the mysteries of the universe, offering new insights into the dynamic and often surprising processes that govern the birth, life, and death of stars. On a more terrestrial level, our own planet's atmosphere contains its own set of intriguing mysteries. The thermosphere, one of the outermost layers of Earth's atmosphere, experiences significant and often perplexing temperature variations. This layer, which stretches from about 50 miles to several hundred miles above the Earth's surface, is subject to temperature fluctuations that range from roughly 500 degrees Fahrenheit to over 2,000 degrees Fahrenheit. These dramatic changes in temperature have puzzled scientists for years, as they appear to be driven by several dynamic factors, many of which are influenced by solar activity, geomagnetic storms, and interactions between charged particles and atmospheric gases. The primary driver of temperature changes in the thermosphere is solar activity. The sun's ultraviolet radiation and X-rays play a crucial role in heating the thermosphere. During periods of high solar activity, such as solar flares and coronal mass ejections, there is a surge of high-energy radiation that reaches the Earth's atmosphere. This influx of energy ionizes the sparse gases in the thermosphere, causing them to move more energetically and heat up. In contrast, during periods of low solar activity, the reduced radiation results in a cooler thermosphere. Geomagnetic storms also significantly influence the thermosphere's temperature. These storms occur when solar wind and solar energetic particles interact with Earth's magnetic field. This interaction directs charged particles toward the polar regions, where they enter the atmosphere and generate auroras. This process injects significant amounts of energy into the thermosphere, leading to localized heating. Additionally, the complex dynamics between atmospheric gases and charged particles further contribute to temperature fluctuations. As particles in the ionosphere collide with gas molecules, they transfer energy, causing the gases to heat up and further influencing the overall temperature. These fluctuations in the thermosphere's temperature are not just a scientific curiosity. They have real-world implications. For example, changes in the thermosphere's temperature can directly affect satellite orbits, which can have a profound impact on communication systems, GPS, and other technologies. As observational technology continues to improve and climate models become more sophisticated, scientists are working to understand the full scope of these temperature variations. With better predictive models, we may be able to mitigate the impacts of thermospheric temperature swings, allowing us to protect our technological infrastructure and gain deeper insights into the complexities of Earth's atmosphere. Both stellar anomalies and atmospheric phenomena underscore the unpredictable and often mind-boggling nature of the universe. They challenge our existing knowledge, compelling us to keep asking deeper questions, exploring new possibilities, and revising our understanding of the forces that shape our world. As our observational tools continue to evolve, so too will our ability to unravel the mysteries of the cosmos and the atmosphere, expanding our knowledge of the universe and our place within it. The intricate, enduring spiral structures of galaxies present one of the most captivating puzzles in modern astronomy. These grand, sweeping arms that stretch across the cosmos have fascinated astronomers for decades. They are not static features. Rather, they are dynamic, constantly evolving patterns of stars, gas, and dark matter. The persistence of these spiral arms, some of which have lasted billions of years, hinges on the delicate interplay of gravitational forces and hydrodynamic processes. One of the leading theories attempting to explain how these spiral arms are maintained over such immense timescales is the density wave theory. This theory proposes that spiral arms are not permanent, fixed structures composed of the same stars and gas. Instead, they are regions of higher density that move through the galaxy, like traffic jams on a cosmic scale. Just as cars move in and out of traffic jams, stars and gas in these spiral arms flow in and out of the denser regions. As they enter these dense areas, they slow down and compress, causing the formation of new stars. This process intensifies star formation, making the spiral arms more pronounced and vibrant. The density wave moving through the galactic disk perpetuates the spiral structure over time. However, the density wave theory is just one piece of the puzzle. Gravitational interactions within the galaxy, as well as with nearby galaxies, also play a crucial role in sustaining these spiral structures. Gravitational torques and resonance effects amplify the spiral arm features, ensuring their persistence. Additionally, bars within galaxies' elongated central structures can also drive the formation and maintenance of spiral arms. The gravitational influence of these bars can induce spiral density waves in the galactic disk, reinforcing the spiral shape further. An often overlooked but critical component in the formation and stability of these structures is dark matter. Though invisible, dark matter constitutes a substantial portion of a galaxy's mass. Surrounding the galaxy in a massive halo, dark matter provides essential gravitational stability, helping to sustain the galaxy's rotation curve. This stabilization effect ensures that the spiral structure remains intact, even over the course of billions of years. Without dark matter, the galaxy would lose its balance, and the spiral arms could begin to dissipate. To fully understand these complex processes, astronomers rely on advanced computer simulations and cutting-edge observational technologies. These tools allow scientists to model the intricate interactions between stars, gas, dark matter, and gravitational forces. They can simulate the movement and evolution of spiral arms, providing insights into the forces at play. Ongoing research continues to explore these mechanisms, with the goal of uncovering the detailed orchestration that allows spiral galaxies to retain their iconic structures. This research not only deepens our understanding of galaxies, but also enriches our broader cosmological narrative, shedding light on the fundamental forces that govern the universe. While the study of galaxies' spiral structures pushes the boundaries of our understanding, human space exploration faces its own set of formidable challenges, particularly when it comes to protecting astronauts from cosmic radiation. Cosmic radiation, composed of high-energy charged particles from the sun and beyond, presents one of the most significant health risks during long-duration space missions. This radiation can cause a range of serious health problems, including an increased risk of cancer, damage to the central nervous system, and even acute radiation sickness. As space agencies plan missions to Mars and beyond, the need to develop effective strategies to protect astronauts from cosmic radiation is critical. One potential solution lies in shielding materials. Traditional spacecraft materials like aluminum provide some degree of protection, but they are far from sufficient for long-duration missions. Researchers are now turning to more advanced materials to offer enhanced protection. Polyethylene, for example, is a promising candidate because it contains hydrogen atoms, which are particularly efficient at blocking particle radiation. In addition to polyethylene, other materials such as high-density polymers and hydrogen-rich substances like borated polyethylene are also being tested for their shielding properties. These materials show great potential in absorbing or deflecting the harmful radiation that astronauts would encounter on long journeys through deep space. These advancements are vital for ensuring the safety and health of astronauts as they venture farther into the cosmos than ever before. As research continues, the development of effective shielding materials may prove to be the key to ensuring that human exploration of Mars and beyond is both safe and sustainable. In the pursuit of safeguarding astronauts during deep space missions, innovative and versatile shielding materials are being explored. Water, often regarded as a promising resource for life support, is emerging as a dual-purpose solution. Not only can it serve as a vital necessity for astronauts, ensuring hydration and enabling other life support functions, but it can also act as an effective radiation shield. With its high hydrogen content, water proves to be an excellent protective barrier against harmful radiation, making it an invaluable asset. Engineers are exploring the idea of placing water tanks around crew habitats, where they can function as a protective shield, reducing the harmful effects of radiation exposure during long-duration missions. But the use of water isn't limited to this. Engineers are also investigating the potential to repurpose waste materials generated by the spacecraft itself transforming them into additional layers of shielding. By maximizing resource utilization in space, we not only improve the safety of astronauts, but also ensure the sustainability of space missions. This creative use of in-situ resources represents a leap forward in the way we approach space travel, minimizing the need for extensive resupply missions from Earth. Yet, radiation protection goes beyond simple passive shielding. Building on the protective principles that Earth's magnetosphere provides, scientists are now exploring the possibility of creating artificial magnetic fields around spacecraft. This concept draws inspiration from the Earth's natural defense against cosmic radiation, which shields the planet from high-energy charged particles. Creating similar fields around spacecraft could offer a viable way to deflect these charged particles by providing another layer of protection for astronauts. Similarly, electrostatic shielding is another innovative approach under investigation. By repelling charged particles through carefully managed electric fields, this technology could serve as an additional line of defense for astronauts, ensuring that the radiation environment within the spacecraft remains as safe as possible. However, developing these protective technologies requires constant refinement and innovative thinking, as space's unpredictable radiation environment presents complex challenges for scientists and engineers alike. In addition to physical shielding, advanced monitoring systems are essential for astronaut safety. Real-time radiation detection and forecasting systems are being developed to provide early warnings of increased radiation levels, particularly during solar events such as solar flares. By alerting astronauts to these dangerous spikes in radiation, they can take refuge in specially designed storm shelters, areas of the spacecraft fortified with enhanced shielding. These shelters can offer crucial protection during solar particle events, which pose a significant risk to astronauts' health. However, it's not just physical protection that is being developed. Pharmacological countermeasures are also playing a key role in the ongoing battle against radiation. Scientists are exploring the potential of radioprotective drugs that could mitigate the biological effects of radiation exposure. These drugs aim to protect astronauts' cells from radiation-induced damage, reducing the long-term health risks associated with prolonged exposure to cosmic radiation. In this way, a combination of materials, innovative shielding technologies, real-time monitoring, and medical solutions are paving the way towards safer, more sustainable space exploration. The challenges of human space exploration are growing more complex as we venture farther into the cosmos. One of the most pressing goals is to establish a permanent base on Mars, an endeavor that will require overcoming a myriad of challenges. Mars, with its thin atmosphere composed primarily of carbon dioxide, offers little protection from the harmful radiation that permeates space. As a result, creating habitats capable of shielding settlers from both radiation and extreme temperature fluctuations will be essential. Temperatures on Mars can range from a temperate 70 degrees Celsius to a bone-chilling 100 degrees Fahrenheit below zero, presenting a serious challenge for maintaining a livable environment for humans. Adding to these challenges are the frequent dust storms on Mars, which can last for weeks, reducing visibility and potentially damaging both human systems and equipment. These storms, which can envelop the entire planet, pose a unique threat to both the safety of astronauts and the functionality of vital systems required for survival. To ensure that Mars colonization is even remotely feasible, innovative engineering solutions will be necessary to create robust habitats capable of withstanding such harsh environmental conditions. Another major hurdle is the extraction and management of essential resources. While water is known to exist on Mars, it is primarily in the form of ice and may also be present in subsurface reservoirs. To make this water usable, it must be extracted, processed, and recycled efficiently. The technology to accomplish this, such as water electrolysis, must be perfected to ensure a reliable and sustainable water supply for astronauts. Oxygen production presents a similar challenge. While oxygen is crucial for breathing and can also be used as a fuel source for spacecraft, it will need to be produced locally on Mars. One of the most promising methods is the electrolysis of water, which breaks down water molecules into hydrogen and oxygen. Another possibility involves the conversion of carbon dioxide from Mars's atmosphere into oxygen through chemical processes. Food production is another significant challenge. Martian soil contains toxic perchlorates, which would make it dangerous for growing crops directly in the soil. Therefore, developing methods to treat the soil or implementing advanced hydroponic or aeroponic systems within controlled environments will be key to growing food on Mars. These systems, which do not rely on soil, could provide an efficient way to grow crops in a sustainable manner, ensuring that future Martian settlers have access to a steady food supply. The immense distance between Earth and Mars, averaging about 140 million miles, presents its own set of obstacles. Communication with Earth becomes complicated due to a delay that can be as long as 24 minutes for a round trip. This delay makes real-time conversations impossible and necessitates the development of highly autonomous systems to handle critical functions, ensuring that missions can proceed smoothly without constant reliance on Earth-based guidance. By developing technologies in these diverse areas, radiation protection, resource management, food production, and autonomous systems, humanity is taking bold steps toward not only reaching Mars, but also establishing a permanent human presence there. The challenges are immense, but with determination, innovation, and collaboration, these barriers will be overcome, allowing for the next great leap in human exploration. Resupply missions to Mars would be both infrequent and costly, demanding a level of self-sufficiency that has never been required of humans before. Settlers on Mars would need to rely heavily on local resources to survive, which brings us to a critical concept for long-term sustainability: in situ resource utilization. This method involves extracting and using Martian materials for essential needs such as creating building materials, tools, and even fuel. It's not just a matter of convenience, it's essential to human survival on the red planet. The challenges aren't just logistical, they're also physiological. Mars's gravity is only about 38% of Earth's, and this difference can wreak havoc on the human body over time. Reduced gravity can cause a loss of muscle and bone density, disrupt cardiovascular function, and pose long-term health risks. This, compounded by the microgravity environment experienced during the journey, means astronauts will need ongoing medical interventions, regular exercise regimens, and constant monitoring of their physical health to maintain long-term well-being. The human body will face immense pressure from all directions, and the consequences of not addressing these issues could be catastrophic. However, the physical challenges are not the only hurdles. The psychological toll of living in such a hostile, isolated environment is another critical factor. Astronauts will be confined to a small space with limited interaction and will live on a planet that is inhospitable to life. The constant stress of knowing how far they are from Earth, the small crew sizes, and the weight of their responsibilities will create an intense psychological burden. Extended missions will require constant mental health support, as well as the development of strategies to combat the emotional and psychological strains of isolation. Given the broad range of challenges that human missions to Mars will face, international collaboration is essential. These efforts cannot be accomplished by any one country or organization alone. There needs to be sustained investment in research and technology development across multiple disciplines, from medicine to engineering, from agriculture to communication. Testing in low Earth orbit habitats and lunar missions will be critical for building the knowledge necessary for success. Mars is the next frontier, but getting there, and thriving once we do, requires meticulous planning and continuous improvement based on trial and error. The efficiency of interplanetary travel itself is another area of great focus. Advancing propulsion technology, improving resource management, and optimizing spacecraft design will be pivotal in reducing the time, cost, and risks associated with traveling between planets. Spacecraft travel distances in space that are unimaginable by everyday standards, and even a slight improvement in speed or fuel efficiency can cut down on months or even years of travel. Traditional chemical rockets, while effective for launching payloads out of Earth's gravity, are not sufficient for the long-term, high-speed journeys necessary for interplanetary missions. To solve this, new technologies are being developed to propel spacecraft much more efficiently. One of the most promising is electric propulsion, specifically ion thrusters. These engines utilize electricity, often generated by solar panels, to ionize propellants like xenon and expel them at high velocities. While these thrusters don't offer the immediate thrust of chemical rockets, they are far more fuel efficient, making it possible for spacecraft to reach higher speeds over long periods of time. Another breakthrough propulsion technology that could drastically cut down on travel time to Mars is nuclear thermal propulsion. This technology uses a nuclear reactor to heat a propellant, such as hydrogen, to extremely high temperatures. The heated gas is then expelled rapidly to generate thrust. This method provides much greater efficiency than chemical rockets, drastically reducing the time it would take to reach Mars and other planets. Even further advances like nuclear electric propulsion, which combines nuclear thermal energy with electric propulsion, could take interplanetary travel to new heights. Equally important as propulsion is resource management. In situ resource utilization is not just a nice to have, it's vital for sustainability on Mars. By utilizing materials already available on the planet, such as water ice, astronauts could produce their own fuel, water, oxygen, and even building materials. This process drastically reduces the mass and costs of missions, as it reduces the need to bring everything from Earth. For instance, extracting water ice from Mars or the Moon and converting it into hydrogen and oxygen could provide both life support and rocket fuel. This, in turn, could drastically reduce launch costs and make the possibility of long-term missions much more feasible. To support these missions, spacecraft design itself must undergo significant advancements. By using lighter materials such as advanced composites and alloys, spacecraft can be made less massive, which improves their fuel efficiency. Modular spacecraft design is another revolutionary concept which allows spacecraft to be assembled in space. This not only reduces the mass of the rocket itself, but also allows for greater versatility and reusability of space habitats and vehicles. Instead of launching a fully assembled heavy spacecraft from Earth, missions can send modular parts into space, where they are pieced together to create the necessary structures. Mission planning and trajectory optimization also play vital roles in improving efficiency. With the vast distances between planets, it's crucial to have the most effective travel route possible, minimizing the time and energy required for the journey. Small improvements in these areas could lead to enormous reductions in cost, time, and risk, making Mars missions more viable for future generations. Ensuring the success of permanent human habitation on Mars will be a delicate balance of technology, psychology, and innovation. Each step of the way, from propulsion technology to resource management to spacecraft design, will need to be carefully calculated, constantly tested, and iteratively improved. This is a monumental effort that will require the best of humanity's scientific minds, collaborative spirit, and resilience. Only by overcoming these monumental challenges can we hope to make Mars the next home for human civilization. In the vastness of space, interplanetary travel is no longer just a dream of science fiction, but a growing reality. Utilizing gravitational assists from other planets can propel spacecraft to extraordinary speeds, requiring no additional fuel. This technique, often referred to as a slingshot maneuver, takes advantage of the gravitational pull of celestial bodies, allowing for rapid acceleration. With the help of advanced software algorithms, precise trajectories can be calculated to minimize both travel time and fuel consumption, turning the unpredictable vastness of space into a navigable, fuel-efficient route. But the journey doesn't stop at efficient propulsion. Artificial intelligence, AI, and automation are revolutionizing mission operations, ensuring that space missions not only become more efficient, but also more autonomous. With AI on board, spacecraft can make real-time decisions, adapt to changing conditions, and navigate autonomously without relying solely on Earth-based control. This reduces the dependency on ground stations and ensures that spacecraft can respond to unforeseen challenges far quicker, improving the chances of mission success and minimizing risk. Moreover, international collaboration is playing a pivotal role in accelerating space exploration. Agencies such as NASA, ESA, Roscosmos, alongside private companies like SpaceX and Blue Origin, are pooling resources and knowledge to create a more sustainable framework for interplanetary travel. By distributing the immense costs and technical demands of deep space exploration, these collaborative efforts are setting the stage for a future where space travel becomes more cost-effective, efficient, and secure. The integration of AI, automation, and international cooperation is paving the way for humanity's ambitious expansion into the solar system and beyond. A significant aspect of this future involves asteroid mining, a frontier that holds immense promise, but also presents substantial technological hurdles. Mining asteroids for valuable resources such as rare metals, water, and other essential materials could support long-term space settlements, enabling humanity to live and thrive beyond Earth. To make this vision a reality, an array of advanced technologies is required to address the unique challenges of locating, accessing, and extracting these resources from space. The first step in asteroid mining is prospecting, which involves precise reconnaissance to identify asteroids that contain the most valuable materials. This task relies on sophisticated space telescopes such as NASA's NEOCAM or the European Space Agency's Hera mission, which survey and catalog asteroids, providing vital data on their composition, structure, and potential resource value. Once potential targets are identified, spacecraft equipped with spectrometers and radar instruments can gather detailed information about the surface and subsurface characteristics of these celestial bodies, guiding future missions. Once an asteroid is selected, the next challenge is developing spacecraft capable of reaching and docking with these small, irregularly shaped bodies. This requires advanced propulsion systems like ion thrusters or nuclear thermal propulsion, which can efficiently travel to and maneuver in the unique gravitational environments of asteroids. To safely capture and anchor onto these bodies, spacecraft must be equipped with specialized mechanisms such as robotic arms or harpoons designed to latch onto the asteroid's rough surface. The process of mining itself poses even greater challenges. The low gravity of asteroids makes it difficult to use traditional mining techniques. Therefore, autonomous robots and drills capable of operating in microgravity must be designed to excavate surface and subsurface materials. One promising approach is regolith heating, where solar energy or microwave technology is used to heat the asteroid material, releasing volatile compounds like water, which could be vital for sustaining human life or fueling spacecraft. Another technique involves mechanical excavation with specialized drills and cutters designed for the unique conditions of space. The final step in asteroid mining is processing the materials. In situ resource utilization, ISRU, technologies are key to converting raw materials into usable forms directly in space. Extracted water, for instance, could be split into hydrogen and oxygen through electrolysis, providing essential resources for life support systems or rocket fuel for further space missions. Metals and other valuable materials can also be refined and processed using solar furnaces or other space-based facilities, enabling space manufacturing and construction without the need to transport raw materials back to Earth. Yet there are still significant challenges in transporting these mined resources. Storing and moving mined materials across the vast expanse of space require cutting-edge technologies to ensure that valuable resources remain safe, intact, and ready for use when they reach their destinations. With these advancements, asteroid mining could soon provide the materials necessary to support long-term space exploration, paving the way for humanity's settlement beyond Earth. Through the fusion of AI, international cooperation, advanced space technology, and asteroid mining, the next chapter in human space exploration is within reach. Each breakthrough brings us closer to becoming a spacefaring civilization, where travel, resource acquisition, and habitation across the solar system are no longer just a fantasy, but a tangible reality. The stakes have never been higher, and the possibilities never greater. This is just the beginning of our journey beyond the stars. In the pursuit of unlocking the full potential of space, technologies must be developed to safely contain and transport volatile materials in space. These systems need to withstand the unique challenges posed by space's microgravity and vacuum, while also ensuring that materials are protected from contamination or loss. Efficient spacecraft capable of ferrying these precious materials back to Earth or to other destinations within our solar system must also be developed. These vehicles should incorporate reliable re-entry systems, ensuring safe return journeys to Earth. But it doesn't end with transportation. Advanced automation, robotics, and artificial intelligence, AI, will play pivotal roles throughout the asteroid mining process. Autonomous systems will operate with minimal human intervention, reducing the need for crewed missions while ensuring continuous operation in the unforgiving environment of space. With the help of AI, resource extraction and processing could be optimized, allowing for the management of unforeseen challenges. As technology advances, these autonomous systems will become more efficient, supporting sustainable operations on an unprecedented scale. Equally important, regulatory and legal frameworks must be established to govern asteroid mining activities. International agreements and guidelines will be essential to ensure the responsible and equitable use of resources. Instead of fueling competition, these frameworks will foster cooperation, allowing for the fair distribution of wealth and knowledge as humanity takes its next step into the cosmos. Addressing the technological, logistical, and legal challenges will bring us closer to realizing the dream of mining asteroids, opening new horizons for both resource acquisition and the future of space exploration. Turning our attention to the future of space colonization, developing sustainable life support systems is key. These systems must integrate closed-loop ecosystems capable of replicating Earth's resources over extended periods. At the heart of these systems will be reliable methods for air purification, water recycling, and food production. Scientists are already exploring bioregenerative systems where plants play a dual role, not only providing food, but also generating oxygen and absorbing carbon dioxide. Imagine a greenhouse module equipped with carefully selected crops that could convert human-generated carbon dioxide into oxygen through photosynthesis, all while providing fresh nutrition. This process would require meticulous planning. Approximately 750 grams of plant biomass per person each day would be needed to maintain oxygen levels similar to those on Earth. Water recycling within space colonies is equally crucial. To reduce the need for costly resupply missions from Earth, advanced filtration and purification technologies must be employed. Techniques like forward osmosis and distillation can transform wastewater back into clean, drinkable water, achieving up to 95% recovery from all available sources, including urine. Furthermore, integrating microbial life in bioreactors could enhance the decomposition of waste, turning it back into usable resources. These efforts to optimize efficiency are critical to maintaining space habitats that can thrive independently with minimal external support. Finally, the concept of space-based solar power is gaining traction as technological advancements and economic considerations align. This ambitious initiative involves deploying large arrays of solar panels in orbit around Earth, capturing solar energy without the interference of weather patterns or the day-night cycle. The energy harvested would then be transmitted back to Earth via microwave or laser beams, where it could be converted into electricity. One of the most compelling advantages of space-based solar power is its potential for continuous, uninterrupted energy generation. A single square meter of solar panels in space could theoretically produce up to 13 times more energy than the same area on Earth due to the absence of atmospheric interference. However, significant challenges remain. The cost of launching and assembling these massive structures in orbit must be reduced to make space-based solar power a reality. The development of reusable rockets, like those pioneered by SpaceX, is a step in the right direction, offering a solution to this obstacle. Lower launch costs will make the deployment of large-scale solar arrays much more feasible, opening the door to a future where space-based solar power could meet much of humanity's energy needs. Through continuous innovation and cooperation, humanity is on the brink of expanding its reach beyond Earth. From asteroid mining to space colonization and solar power, the future of space exploration is rapidly becoming a tangible reality. The dream of living and thriving in space is within our grasp. An exciting new chapter in human history is unfolding before our eyes. Moreover, advancements in materials science are propelling the development of lighter, more efficient solar panels that promise to dramatically enhance the energy return on investment. These innovations are essential for tackling the long-term goals of sustainable energy. Yet, despite these exciting advancements, there are still significant obstacles, particularly in the areas of energy transmission back to Earth and the safety and reliability of space-based systems. While practical deployment of space-based solar power may remain a few decades away, current research and prototypes show promise. Space-based solar power could one day provide a substantial portion of the world's energy needs, playing a crucial role in achieving a more sustainable and carbon-neutral future. In parallel, improving long-distance space communication faces formidable technical challenges, especially when dealing with the vast distances and signal degradation that occurs over time. One promising solution lies in the development of laser-based communication systems, which have demonstrated significant advantages over traditional radio frequency methods. Lasers can transmit data at speeds up to 100 times faster than radio waves, and they also allow for a narrower, more focused communication beam, which reduces signal dispersion. NASA's Laser Communications Relay demonstration aims to validate this cutting-edge technology with the goal of enabling efficient data transfer from distant spacecraft back to Earth with lower latency and higher efficiency. This advancement could revolutionize the way we handle communication in deep space exploration. Another transformative leap in space communication involves the exploration of quantum communication networks. Quantum entanglement, often referred to as spooky action at a distance by Einstein, could pave the way for instantaneous data transmission. In theory, quantum communication would allow real-time communication across vast interstellar distances by leveraging entangled particles. These particles maintain a direct connection regardless of the space between them. Changing the state of one particle instantaneously alters the state of the other. Though still in experimental phases, quantum communication could potentially overcome the limitations of the speed of light, allowing for faster-than-light communication and enabling seamless communication across the cosmos. To support these monumental technological advancements, a complete overhaul of infrastructure may be required. This could include the establishment of relay stations on the Moon, Mars, and other strategic locations throughout the solar system. These relay stations would serve as interstellar waypoints, ensuring consistent and reliable data transfer across immense distances. Combining these advanced communication techniques with a robust, strategically placed infrastructure could transform our ability to operate and explore not just our solar system, but potentially even interstellar space, ushering in a new era of cosmic communications. Looking ahead, the next generation of propulsion technologies will be essential for enabling deep space exploration and reducing travel times, all while increasing spacecraft efficiency. Ion propulsion is one of the leading candidates. Already demonstrated in NASA's Dawn spacecraft mission, ion propulsion uses electric fields to accelerate ions, providing steady and efficient thrust over extended periods. Unlike traditional chemical rockets, which produce a brief, powerful burst of thrust, ion engines offer continuous low-thrust propulsion that can accelerate a spacecraft to higher speeds over time. This technology could open the door for missions to distant asteroids, Mars, and beyond, all while utilizing significantly less fuel. In addition, nuclear thermal propulsion is gaining renewed attention as a powerful method for deep space travel. This technology uses nuclear reactions to heat a propellant, typically hydrogen, to high temperatures. The heated propellant then expands and is expelled to create thrust. Compared to chemical rockets, nuclear thermal propulsion could provide a significant boost in efficiency, offering twice the specific impulse. Agencies like NASA and DARPA are actively working on projects to demonstrate the feasibility and safety of nuclear thermal propulsion, with the potential to enable crewed missions to Mars and beyond in the near future. Such propulsion technologies could dramatically reduce travel time to Mars and other distant destinations, making long-term missions more viable and safer for human explorers. These advancements in solar power, communication systems, and propulsion technologies represent a fundamental shift in humanity's ability to explore and harness the resources of space. While we are still in the early stages of these endeavors, the potential for transforming space exploration and ultimately human existence is greater than ever. As we continue to overcome the technical challenges and build the necessary infrastructure, the stars themselves may one day be within our reach. The concept of harnessing solar sails is advancing rapidly, pushing the boundaries of space exploration. Solar sails leverage the pressure of photons from the sun's rays to propel spacecraft, creating an innovative form of propulsion that does not rely on traditional onboard fuel. The Japanese Space Agency's Icaros mission has already demonstrated the viability of this technology, showing that spacecraft can be powered solely by the constant, albeit weak, force exerted by sunlight. This breakthrough opens up the possibility of missions extending far beyond Earth's orbit, potentially even reaching the outer planets and beyond into interstellar space. To further enhance this propulsion method, laser systems based on Earth could provide an initial boost by beaming focused light onto the sails. As we look to the future, the development of solar sails and other next-generation propulsion technologies brings us ever closer to the dream of more efficient and faster space exploration. The possibilities for uncovering new frontiers in human exploration and scientific discovery seem limitless. These advancements could fundamentally alter our understanding of space travel, enabling us to venture deeper into the cosmos with greater speed and reduced reliance on conventional fuel sources. In parallel, the threat of potentially hazardous near-Earth objects, NEOs, looms large, necessitating an advanced approach to planetary defense. Detecting and deflecting these objects is crucial to avoid catastrophic impacts on Earth. Advanced telescopic surveys play a vital role in identifying NEOs, with ground-based observatories now equipped with wide-field cameras that continuously scan the skies for potential threats. Notably, NASA's Near-Earth Object Wide-Field Infrared Survey Explorer, NEOWISE, has been a leader in the effort, successfully identifying and characterizing these objects, even those as small as 30 meters in diameter, by capturing their infrared signatures. These infrared readings often provide more detailed information than visible light observations, giving scientists a clearer picture of the object's size, composition, and potential risks. Once a NEO is detected, precise tracking and orbital modeling are employed to predict its trajectory and assess the likelihood of a collision with Earth. If an object is deemed a significant threat, planetary defense strategies come into play. One of the most promising techniques for deflecting an NEO is the kinetic impactor method, in which a spacecraft is intentionally crashed into the object to change its course. NASA's Double Asteroid Redirection Test, DART mission, for example, aims to demonstrate this approach by impacting the smaller body of a binary asteroid system called Didymos. Another potential method involves the use of gravity tractors, where a spacecraft is positioned near a NEO and its gravitational pull gradually alters the object's path. This technique offers a non-invasive and controllable way to change a NEO's course over time. More advanced concepts, though still theoretical, include deploying solar sails on asteroids to use photon pressure for course correction, or employing concentrated solar energy to vaporize parts of an NEO's surface, creating a reactive thrust to redirect its trajectory. The development of these detection and deflection methods, combined with advancing technology, forms a comprehensive strategy to protect our planet from the risks posed by NEOs. As we refine these techniques, we move closer to the ability to predict and, if necessary, prevent potentially catastrophic impacts, ensuring that humanity is prepared for whatever threats may arise from the cosmos. Building large structures in space presents its own set of challenges, mainly due to the extreme environment and the constraints of operating in microgravity. One of the most significant hurdles is transporting materials from Earth, as traditional rockets have limited payload capacities. This means that construction materials must be lightweight, yet strong enough to withstand the harsh conditions of space. Innovations in materials like carbon fiber composites and advanced alloys are key to overcoming this challenge. However, the high cost of transporting materials remains a significant barrier. To reduce costs, future space construction efforts may rely on in-situ resources, such as regolith from the moon or asteroids, which could be processed into building materials using 3D printing technology. Microgravity complicates construction in space even further. Traditional assembly techniques that work on Earth, such as welding or bolting, can be problematic in the weightless environment, where materials are prone to floating away. Engineers are exploring robotic systems that can perform assembly tasks autonomously or semi-autonomously, overcoming the difficulties of a lack of stable ground. The European Space Agency's Cosmic Kiss mission is one such initiative, testing a remote welding robot that could join metal pieces together in space, ensuring that large space structures can be securely assembled and maintained. As technology continues to evolve, these challenges are being addressed with innovative solutions, from advanced materials to robotic systems. The future of space exploration holds exciting potential, where the construction of vast structures and the ability to defend our planet from cosmic threats may soon become a reality. NASA's ambitious Aeronaut project is pushing the boundaries of space exploration by aiming to build and deploy large structures in orbit using robotic arms. These robotic arms are equipped with advanced additive manufacturing capabilities, allowing them to both fabricate and assemble parts in space. This innovation drastically reduces the need for risky and resource-intensive human spacewalks, which have historically been a significant challenge for space missions. By leveraging automation and robotic precision, NASA is making substantial strides in the development of space construction technologies. However, space construction comes with its own unique set of challenges. The first and most critical hurdle is ensuring the structural integrity and durability of space structures. In the harsh environment of space, structures must endure extreme temperature variations, intense radiation, and potential impacts from micrometeoroids. To address this, NASA is advancing the development of high-performance materials such as multi-layer insulation and radiation-hardened composites. These materials will provide the necessary protection for space structures, ensuring that they remain intact even in the most hostile conditions. Furthermore, the creation of livable habitats in space presents additional obstacles. Effective shielding from space radiation, reliable life support systems, and the ability to manage the accumulated stress from long-term space exposure are all essential components of sustainable space habitats. As technology advances, the possibility of constructing large, habitable, and self-sustaining structures in space becomes more achievable. These structures could range from sophisticated telescopes and space stations to future human habitats on the Moon or Mars, paving the way for humanity's long-term presence in space. Beyond space construction, the search for life within our solar system continues to captivate scientists. The primary focus of this search is identifying bodies that possess, or once possessed, the essential elements for supporting life as we understand it: liquid water, an energy source, and the right chemical ingredients. Among the most promising targets in this quest is Europa, one of Jupiter's moons. Europa is particularly intriguing because it harbors a vast subsurface ocean beneath an ice crust several kilometers thick. Data gathered from the Galileo spacecraft and Hubble Space Telescope suggests that this hidden ocean could contain the necessary conditions to support life, particularly around hydrothermal vents on the ocean floor, where chemical reactions could provide the energy needed to sustain microbial life. Another moon that captures significant scientific attention is Enceladus, Saturn's icy moon. Enceladus is remarkable for its geysers, which eject water vapor and organic molecules into space from a subsurface ocean. The Cassini spacecraft detected these plumes and analyzed their composition, finding salts and simple organic compounds that suggest hydrothermal activity on the ocean floor. Such environments, rich in energy, could harbor microbial life. The discovery of these geysers makes Enceladus an attractive target for future missions aimed at sampling the ejected materials, offering the possibility of detecting biological activity without needing to drill through its thick ice shell. Mars remains one of the most compelling locations in the search for past or present life. The red planet once had a more Earth-like environment, with evidence of ancient river valleys, lake beds, and potentially even an ocean. Rover missions, such as Curiosity and Perseverance, are actively exploring ancient Martian sediments and clay deposits, which may contain signs of microbial life or fossilized remains. Mars also holds the tantalizing possibility of still habitable environments in its subsurface, where liquid water could exist in the form of salty lakes, increasing the potential for microbial life to survive below the surface. Equally exciting, though more speculative, is the potential for life on Titan, Saturn's largest moon. Titan is unique in that its thick atmosphere and surface liquids, primarily composed of methane and ethane, offer a radically different chemistry for life. While any organisms on Titan would be fundamentally different from those on Earth, the richness and complexity of Titan's chemical processes make it an intriguing candidate for exploration. The idea that life could exist in a hydrocarbon-based environment challenges our understanding of biology, offering an entirely new perspective on the potential for life beyond Earth. These celestial bodies, each with their own unique set of conditions, continue to drive humanity's quest for life beyond Earth. Their exploration is guiding the design and focus of future missions, each one bringing us closer to answering the profound question: are we alone in the universe? In parallel, the search for biosignatures on exoplanets is a key aspect of this quest. Biosignatures refer to specific chemical compounds, patterns, or phenomena that can indicate the presence of life. These can range from simple molecules like molecular oxygen and methane to more complex organic compounds such as amino acids and proteins. One of the most promising biosignatures is the simultaneous presence of oxygen and methane in a planet's atmosphere. On Earth, these gases are produced by living organisms, and their co-presence would indicate ongoing biological activity. This is because oxygen and methane are highly reactive and would not naturally coexist in the atmosphere without a continuous biological source replenishing them. As we venture further into the cosmos, these discoveries push the boundaries of our understanding of life, challenging us to think beyond Earth's biosphere and consider new, previously unimagined forms of life. The pursuit of knowledge about life in space continues, fueled by both the promise of discovery and the drive to answer humanity's oldest question: what is our place in the universe? In the vastness of space, detecting life, especially microbial life, on distant exoplanets is one of the most exciting and challenging scientific endeavors. To do this, advanced telescopes and cutting-edge spectroscopic techniques play a pivotal role. Instruments like the James Webb Space Telescope, JWST, and ground-based observatories, equipped with high-resolution spectrometers, analyze the light spectrum from distant planets as it passes through or reflects off their atmospheres. This light can be dissected into its various wavelengths, revealing absorption lines that correspond to specific chemicals in the planet's atmosphere. For instance, the absorption lines for oxygen appear at distinct points on the spectrum, enabling scientists to infer the presence and concentration of this vital element. The upcoming European Extremely Large Telescope, ELT, with its unparalleled light-gathering capacity, promises to push these abilities even further. It will enable us to detect and study the faintest signals from exoplanets, offering a deeper insight into their atmospheres and chemical compositions. However, interpreting these signals is far from straightforward. Some of the biosignature gases that we detect, such as methane, can be produced not just by life forms, but also by geological processes like volcanic activity. Ultraviolet radiation can also break apart water molecules, releasing hydrogen and oxygen. So, while the presence of certain chemicals may suggest the potential for life, we must be cautious and evaluate the context of the planet's geological and atmospheric processes. The key to reliable detection lies in multi-signature investigations. By detecting a combination of potential biosignatures, scientists can build stronger evidence for biological activity. For example, if we detect methane alongside oxygen, it would be more convincing than finding just one of those molecules on its own. In addition to biosignatures, the search for technosignatures, indicators of advanced technological activity, has gained attention. These can include specific radio signals or laser emissions that might suggest intelligent life elsewhere in the universe. Ultimately, while detecting a single potential biosignature is intriguing, it is the combination of multiple lines of evidence analyzed through various observational platforms and theoretical models that will offer the most compelling case for the existence of life on distant exoplanets. These interdisciplinary efforts, spanning astronomy, biology, chemistry, and planetary science, are essential for decoding the complexities of life's potential beyond Earth. However, despite technological advancements, the task of detecting microbial life remains daunting. One of the biggest challenges lies in the difficulty of directly accessing environments where life could exist. Subsurface biospheres, such as those that might exist on Mars or the ice-covered oceans of moons like Europa and Enceladus, are incredibly difficult to reach. Drilling through kilometers of ice or rock to obtain pristine samples without contaminating them with Earth-based organisms is no small feat. The technology to deploy autonomous drilling and sampling equipment capable of functioning in these extreme conditions is still in its infancy, limiting our ability to gather the necessary samples. Even if we could overcome these physical barriers, the task of detecting the chemical signatures of microbial life is equally challenging. Many of the chemical signatures associated with life are subtle and can be easily confused with non-biological chemical reactions. For example, methane can be produced through geological processes like serpentinization, where water interacts with certain types of rock. To confidently attribute such molecules to biological activity, we need a deep understanding of the planet's geological processes, as well as highly advanced analytical instruments capable of distinguishing between biotic and abiotic origins. Rovers like Perseverance, which is currently exploring Mars, carry sophisticated suites of instruments designed to analyze soil and rock samples. But interpreting the results of these analyses often requires complex models that take into account the planet's entire chemical context. Furthermore, the limitations of remote sensing technology add another layer of complexity. While spacecraft can conduct in-situ measurements, the sensitivity and specificity needed to detect microbial life from millions or even billions of kilometers away are currently beyond our technological reach. The remote detection of microbial life on exoplanets, especially through instruments like spectrometers, remains a monumental challenge. Detecting faint biosignatures from such vast distances requires instruments with extremely high sensitivity. And while we are making strides in this area, we are still far from achieving the level of precision needed to identify life on distant worlds. The journey to discovering life beyond Earth is long and full of challenges, but the potential rewards, unlocking the secrets of the cosmos and perhaps finding that we are not alone, are immeasurable. The search for microbial life beyond Earth presents an array of scientific and technical challenges, many of which are far from straightforward. One of the most profound obstacles is the possibility that extraterrestrial microbes may not share the same biochemical makeup as life on our planet. Earth-based life, after all, is founded upon carbon-based biochemistry, utilizing molecules like DNA, RNA, and proteins to carry out the complex processes that sustain life. But who is to say that alien life forms must follow this same framework? There's a chance that life elsewhere in the cosmos might tap into entirely foreign biochemical pathways, ones we've yet to even imagine. This starkly contrasts with our Earth-centric methods of searching for signs of life, complicating the tools and strategies we currently employ. These challenges underscore the need for a paradigm shift in how we search for life, requiring us to broaden our understanding of what constitutes life and how it might manifest on alien worlds. As if this weren't enough, contamination remains an ever-present concern in the quest for alien life. Introducing even the smallest trace of terrestrial microbes into extraterrestrial environments could easily skew results and lead to false positives. To counter this, strict planetary protection protocols, such as those employed by NASA and the European Space Agency, ESA, are in place to ensure that Earth's microbes do not inadvertently taint samples. Yet, the unpredictable nature of space exploration and the complexities of maintaining complete sterilization in space missions make it a daunting task to ensure absolute cleanliness. To succeed, we must constantly innovate, refining our technologies and methodologies while carefully designing missions to maximize the likelihood of detecting genuine signs of extraterrestrial microbial life. At the same time, we must work tirelessly to mitigate the risks of contamination and the misinterpretation of the results, ensuring that any evidence found is as reliable as possible. Consider a planet orbiting a red dwarf star, a unique environment that could give rise to remarkable life forms. Red dwarfs, which are smaller and cooler than our Sun, produce far less light and heat. As a result, the habitable zones around these stars, regions where liquid water could exist, are much closer to the star itself. This proximity, however, brings with it a set of challenges, including higher levels of stellar activity. Red dwarfs are prone to emitting intense solar flares and more ultraviolet radiation than our Sun, which could pose a serious threat to any potential life. For organisms to survive under such conditions, they would need to evolve specialized protection mechanisms. These could include thicker atmospheres rich in ozone or other protective gases, or the organisms might find refuge underground or underwater where they could shield themselves from the harmful radiation. Additionally, the lower energy output of red dwarfs would mean that planets in these systems would receive less sunlight, which could create a difficult environment for photosynthetic organisms. Life forms dependent on photosynthesis would need to adapt to these lower light levels, perhaps evolving the ability to harness a broader spectrum of light, including infrared radiation, which is more abundant in red dwarf systems. Terrestrial algae and bacteria on Earth already show the ability to capture light across various wavelengths, using different pigments to maximize energy capture. Alien life could likely develop similar pigments, or perhaps even novel forms, to thrive in the dim light of a red dwarf system. However, there's another consideration. Many planets orbiting red dwarfs could be tidally locked. This means that one side of the planet would always face the star, while the other remains in perpetual darkness. Such extreme environmental conditions could give rise to unique adaptations, with life thriving in the stable twilight zones where the conditions are neither too hot nor too cold. Red dwarf stars are long-lived, often burning steadily for tens to hundreds of billions of years, far longer than our sun will. This prolonged stability could offer life ample time to evolve and develop complexity, potentially leading to advanced forms of intelligence and civilization. Yet, there are trade-offs. The frequent stellar flares of younger red dwarfs could strip away a planet's atmosphere or create erratic environmental conditions. Life might evolve rapidly to adapt, developing symbiotic relationships or other strategies for survival. Alternatively, if the flares are too violent, life might only survive in subsurface environments where it would be shielded from the worst of the radiation. Despite the difficulties posed by red dwarf environments, the evolutionary potential for life is fascinating. Life forms could develop extraordinary resilience to radiation, evolve diverse forms of photosynthesis, and find ingenious ways to cope with extreme conditions, painting a picture of life's remarkable adaptability in the universe. Beyond the realm of stellar environments, impacts from celestial bodies have also played a significant and paradoxical role in shaping life. While impacts are often seen as destructive events, wiping out species, altering ecosystems, and triggering mass extinctions, they can also be creative forces driving evolutionary change. One of the most famous examples is the asteroid impact that occurred around 66 million years ago. This impact triggered the extinction of the dinosaurs, but it also set the stage for mammals, and eventually humans, to dominate the planet. This event, known as the Cretaceous-Paleogene (KPG) extinction, led to massive global wildfires, a nuclear winter, and acid rain, which dramatically altered Earth's ecosystems and forced rapid evolutionary responses. Interestingly, some theories suggest that impacts could have played a role in the origin of life itself. During the early years of the solar system, it was a chaotic and violent place, with frequent collisions such as the Late Heavy Bombardment. These impacts may have delivered key organic compounds to Earth, including amino acids and nucleotides, which are the building blocks of life. Some even hypothesize that the precursor molecules for life formed in the harsh conditions of space and were transported to Earth by comets and meteorites. This idea, known as panspermia, is supported by evidence like the discovery of organic molecules in extraterrestrial objects, such as the Murchison meteorite. In this sense, impacts may have been integral not only in shaping the evolution of life, but also in the very origins of life on Earth. It's a testament to the interconnectedness of cosmic events, and the delicate balance of forces that have shaped the life we know. The intense heat and pressure from collisions in space can create hydrothermal systems similar to those found at Earth's deep ocean vents today, places where life may have first emerged. These systems offer rich chemical environments and abundant energy sources in the form of thermal gradients and mineral-rich fluids. They could potentially provide the perfect crucible for life to take shape, offering an ideal environment for prebiotic chemistry to flourish. In addition to this, craters left by cosmic impacts can fill with warm water, forming basins that provide stable environments for life to evolve. These water-filled basins could have offered shelter where complex chemical processes might have occurred, moving towards the origins of life. In evolutionary terms, impacts act as catalysts for change, disrupting existing ecosystems and creating bottlenecks where only the most adaptable species survive. This kind of disruption leads to bursts of diversification and the emergence of new species, reshaping ecosystems. The post-impact world, often drastically altered, becomes a fertile ground for evolutionary experimentation, fostering innovation and new life forms. One of the most notable examples of this is seen following the KT extinction event, when mammals underwent an adaptive radiation that led to a remarkable diversification of species. This transformation filled ecological niches that were once dominated by dinosaurs, revealing how impacts, though destructive, are also integral to life's progression. Their dual role as both destroyers and facilitators highlights the complexity of life's journey, providing crucial opportunities for the emergence of new species, while also forcing the adaptation of existing ones to new, ever-changing environments. This intricate relationship between destruction and creation doesn't just shape life on Earth, it also offers valuable insights into how life might evolve on other planets. The search for extraterrestrial life has expanded beyond biological markers to include the quest for technosignatures, indicators of advanced extraterrestrial technologies. These signatures open a new frontier in the search for alien life, expanding our understanding of what constitutes a potential civilization. One primary method employed in this search is radio astronomy, which has been used for decades. Famous projects like the Search for Extraterrestrial Intelligence, SETI, use radio telescopes to scan vast sections of the sky for non-random narrowband radio signals. These signals could indicate artificial origins, such as interstellar beacons. Natural astrophysical processes typically produce broad-spectrum noise, so a narrowband signal stands out as a potential technosignature. With advancements in technology, the ability to detect these signals has improved, allowing for the monitoring of millions of frequencies across large sections of the sky. The Breakthrough Listen Initiative, for example, is a contemporary effort using state-of-the-art equipment to listen for these signals across a broader range of frequencies and a larger number of star systems. Another fascinating approach to identifying technosignatures involves detecting laser emissions. Lasers produce highly detectable, coherent light beams that could be used by advanced civilizations for communication or as part of spacecraft propulsion systems. High-resolution optical telescopes can be adapted to search for these concentrated light pulses, particularly those in the invisible or infrared spectra. These lasers would appear as strong monochromatic signals against the natural backdrop of starlight, making them easier to spot with the right equipment. The search for technosignatures also includes the possibility of detecting large-scale alterations to planetary environments. For instance, the detection of megastructures such as Dyson spheres, hypothetical constructs that completely encapsulate a star to harness its energy, could be a sign of advanced technological capabilities. Observational strategies may look for unusual stellar dimming patterns or analyze the infrared signatures that such structures might emit. The anomalous dimming of the star Tabby's star, KY 84628552, has raised speculation about the presence of such large-scale engineering projects in space, sparking renewed interest in this possibility. These efforts to detect technosignatures continue to expand our understanding of life beyond Earth, offering new avenues for exploration that might one day reveal whether we are truly alone in the cosmos. Whether through the study of hydrothermal systems on distant planets or the search for signs of advanced civilizations, the quest to understand the forces that shape life both here and across the universe, is only just beginning. Although natural explanations have been proposed, we must also consider the possibility of pollution as a technosignature, offering a new perspective in the search for extraterrestrial civilizations. Advanced civilizations, if they exist, might produce industrial pollutants detectable in their planetary atmospheres, molecules not typically found in natural processes. For instance, certain chlorofluorocarbons, CFCs, widely used in Earth's industrial activities, could potentially be detected through spectroscopic analysis of exoplanetary atmospheres. This method, although promising, requires incredibly sensitive instruments, and with the rise of powerful space-based observatories such as the James Webb Space Telescope, it is now an area of increasing interest. Additionally, artificial satellites or space debris orbiting distant planets might serve as another form of technosignature. High-resolution imaging of extrasolar systems could potentially reveal non-natural objects reflecting or emitting radiation in unique and characteristic ways. However, this approach demands instruments capable of discerning small, high-contrast objects near distant stars, a considerable technological challenge, but one that remains within the realm of future advancements. Together, these methods form a robust framework for the ongoing search for technosignatures, a field supported by increasing developments in telescopic capabilities, computational power for signal processing, and global collaborations. These advancements significantly increase the likelihood of detecting signs of advanced extraterrestrial civilizations if they exist and are emitting detectable technosignatures. The discovery of extraterrestrial microbial life would have profound implications across multiple domains, from science and philosophy to society and religion. Firstly, such a discovery would revolutionize our understanding of biology and the origins of life. If microbial life exists elsewhere in the universe, it would suggest that life is not a rare phenomenon unique to Earth, but rather something that could be common throughout the cosmos, dependent only on the right conditions. This realization would propel astrobiology forward, providing new models of biochemistry and possibly revealing entirely different forms of life that operate under environmental conditions far removed from those on Earth. Life could in fact thrive in environments that we previously considered inhospitable, offering alternate molecular building blocks that challenge everything we know about the basis of life. From a scientific standpoint, finding extraterrestrial microbial life would offer crucial insights into the adaptability and resilience of life forms. It would raise important questions about panspermia, the hypothesis that life can spread from one planet to another through space debris. If the biochemistry of these extraterrestrial microbes is strikingly similar to that of terrestrial organisms, it could point to a shared origin. On the other hand, radically different biochemical processes could suggest independent origins of life across the cosmos. The study of their genetic and metabolic pathways could lead to groundbreaking advancements in biotechnology, medicine, and even reshape our theories of life's evolution. Philosophically, the discovery of extraterrestrial life would challenge anthropocentric views of humanity's place in the universe. It would force us to reassess the notion of human uniqueness and reconsider our perception of life's purpose in the grander context of the cosmos. This shift could foster a more universal perspective, one that emphasizes the interconnectedness of life as a cosmic phenomenon, rather than seeing Earth as the singular cradle of existence. Religious and cultural implications would also be far-reaching. Different traditions may interpret this discovery in various ways. Some might view it as a harmonious affirmation of life's pervasiveness in the universe, while others may struggle to reconcile this knowledge with their existing worldviews. The potential for conflict, or for finding alignment, would likely depend on how these discoveries challenge the foundation of certain beliefs. Some may see it as proof of divine creativity on a cosmic scale, while others might interpret it as a challenge to their teachings. The societal impact would be equally profound. As humanity absorbs the realization that we are not alone in the universe, our perspectives on our environment and our relationships with each other could undergo significant transformations. Ethical considerations would come to the forefront, particularly concerning the protection and study of extraterrestrial life, ensuring that we do not contaminate other worlds with Earth-based organisms, or vice versa, would become an even more critical concern, raising the bar for planetary protection protocols. This would necessitate the establishment or revision of space exploration laws, policies, and ethical guidelines surrounding the treatment of alien biospheres, ensuring that the integrity of extraterrestrial ecosystems is preserved. This new frontier, though still distant, is fast approaching. As technology continues to evolve, humanity stands on the cusp of a monumental shift in its understanding of life itself and its place in the vastness of the universe. The implications, scientific, philosophical, religious, and ethical, are endless, and the search for technosignatures will likely redefine the course of human exploration and discovery for generations to come. Moreover, the discovery of extraterrestrial microbial life could have profound practical implications for the future of space exploration and colonization. Understanding how life survives and thrives in the extreme conditions of extraterrestrial environments would directly inform the search for habitable zones on distant planets. This knowledge could guide the design of future missions and possibly even shape the development of life support systems necessary for long-term human settlements on planets outside our solar system. This groundbreaking discovery might spark a surge in scientific interest and funding, igniting a new era of enthusiasm for space exploration and research. The mere idea of finding life beyond Earth, no matter how small or seemingly insignificant, would undoubtedly inspire awe and wonder, fueling our collective imagination about the possibilities of the universe. As a result, the implications of finding extraterrestrial microbial life reach far beyond science alone, touching every aspect of human thought and endeavor. Such a discovery would mark a monumental milestone in our quest to understand the cosmos and our place within it, potentially uniting humanity through a shared sense of curiosity and awe. Planetary habitability, however, is not a fixed characteristic. It is a dynamic and evolving quality, influenced by a range of astronomical, geological, and biological processes. One of the primary drivers of habitability is stellar evolution. As stars age, their luminosity and activity evolve, impacting the habitable zone, the region around a star where conditions are just right for liquid water to exist. For example, as our sun gradually ages, it becomes brighter and hotter over the course of billions of years, which will shift the habitable zone outward. Earth, currently within this habitable zone, will eventually face conditions that could make it uninhabitable, as rising surface temperatures lead to the evaporation of oceans. Another critical factor in planetary habitability is the planet's geology, particularly tectonic activity. Tectonics plays a crucial role in regulating a planet's climate over geological timescales, specifically through the carbon-silicate cycle. This cycle acts as a natural thermostat, controlling atmospheric carbon dioxide levels. The process involves the weathering of rocks, which removes carbon dioxide from the atmosphere, and volcanic activity, which releases it back. A planet without tectonic activity could face unstable atmospheric and climatic conditions, potentially leading to a freezing or overheating of the surface. Mars, for example, may have had conditions suitable for life in its past, when active volcanism and liquid water existed. However, as its interior cooled and tectonic activity ceased, the planet became a cold, dry wasteland. In addition, the presence and evolution of a planet's magnetic field significantly impact its habitability. A strong magnetic field acts as a protective shield, safeguarding the planet from harmful solar and cosmic radiation. Without this protection, radiation can strip away a planet's atmosphere and degrade its surface environment. Earth benefits from a robust magnetic field, which shields it from solar winds and radiation, creating a stable environment for life to flourish. In contrast, the loss of Mars's magnetic field is thought to have played a major role in the thinning of its atmosphere and the eventual loss of surface water, contributing to its inhospitable conditions. Lastly, biological activity itself can alter a planet's habitability. Life, particularly microorganisms, can significantly impact a planet's atmosphere and surface conditions. On Earth, the emergence of photosynthetic bacteria led to the Great Oxygenation Event around 2.4 billion years ago, dramatically increasing atmospheric oxygen and paving the way for the evolution of complex life. In a similar vein, methane-producing organisms elsewhere could influence atmospheric greenhouse gas levels, thus impacting a planet's surface temperature and overall habitability. This intricate interplay between biology and planetary conditions highlights the profound and often unpredictable relationship between life and its environment. Ultimately, the discovery of microbial life beyond Earth would be far more than a scientific achievement. It would be a step toward unraveling the mysteries of the universe and understanding the fundamental processes that govern life itself. Whether we find life on Mars, Europa, or an exoplanet in a distant star system, it will challenge our understanding of life's origins, its potential for survival in extreme environments, and its role in shaping the future of space exploration. The quest to understand how life thrives in the vastness of space is not just a scientific endeavor, but a reflection of humanity's endless curiosity and desire to explore the unknown. Catastrophic events, such as asteroid impacts, volcanic supereruptions, and nearby supernova explosions, have the power to drastically alter the habitability conditions of a planet in a very short span of time. These catastrophic occurrences can cause mass extinctions, significant climate shifts, and even the loss of entire atmospheres. A prime example of this occurred with the Chicxulub impact, which contributed to the extinction of the dinosaurs. This event didn't just end an era, it reset Earth's ecosystems, paving the way for mammals to thrive and dominate. This shift in dominance dramatically reshaped the course of evolution and the habitability of the planet, making it clear that a planet's habitability is far from static. Rather, it is the result of an intricate dance between astrophysical, geological, and biological factors that evolve over millions of years. Understanding these complex processes is essential not only for studying Earth's past, but also for guiding our search for habitable exoplanets. It gives us a lens through which to view the long-term potential of sustaining life, both here and beyond the confines of our solar system. The study of extremophiles, organisms that thrive in extreme conditions, has opened new frontiers in our understanding of life. These resilient life forms challenge previous assumptions about the limits of survival, demonstrating that life can exist in conditions that were once considered inhospitable. By studying extremophiles, scientists are developing hypotheses about the environments where life could exist beyond Earth and the biochemical adaptations that could support it. Take, for example, thermophiles and hyperthermophiles. These organisms flourish in environments where temperatures soar to extremes, such as hydrothermal vents deep on the ocean floor. Some of these life forms can survive at temperatures exceeding 100 degrees Celsius, with a few even enduring temperatures as high as 121 degrees Celsius. The remarkable stability of their protein structures and enzymes, which function flawlessly in such extreme heat, suggests that similar life forms could exist in the subsurface oceans of icy moons like Europa and Enceladus, where geothermal activity may offer similarly heated environments. On the other end of the temperature spectrum, psychrophiles prove that life is equally adaptable to freezing conditions. These organisms thrive in temperatures as low as -20 degrees Celsius or colder, using antifreeze proteins and specialized cell membranes to prevent ice crystal formation. Their resilience in such extreme cold strengthens the possibility of microbial life on Mars, especially beneath its polar ice caps or under the icy crust of Titan, Saturn's largest moon, where similar conditions could be found. Halophiles, organisms that thrive in highly saline environments, reveal how life could adapt to extreme salinity. These organisms regulate high salt concentrations within their cells through intricate osmotic mechanisms. Radar data suggesting the existence of briny subsurface lakes on Mars hints that such salt-loving life forms might exist there too. If life ever existed on Mars, it might have adapted to survive in these high salinity environments. Equally fascinating are acidophiles and alkalophiles, extremophiles that thrive in highly acidic or alkaline conditions. These organisms manage their internal pH levels through powerful proton pumps and other advanced cellular mechanisms, allowing them to survive in environments that would destroy most life forms. Their ability to adapt to extreme pH environments provides a useful model for life on planets or moons with similarly hostile conditions. Venus, with its acidic clouds, or ocean worlds with alkaline hydrothermal vents, could host life forms adapted to such extremes. Perhaps the most remarkable extremophiles are radio-resistant organisms, like Deinococcus radiodurans. These creatures can survive radiation levels that would obliterate most life. Their secret lies in extraordinary DNA repair mechanisms that allow them to thrive even in environments with intense cosmic radiation. This resilience suggests that life might be able to exist on planets and moons with thin atmospheres and high radiation exposure, such as Mars, or even within the icy crust of Europa, where radiation from Jupiter could penetrate. By studying these extremophiles, we gain profound insights into the biochemical diversity and adaptability of life. Their existence here on Earth opens our minds to the incredible possibilities for life in the vast, seemingly inhospitable expanses of the universe. Their resilience encourages us to consider that life may be far more widespread and varied than we ever imagined, thriving in ways we are only beginning to understand. In exploring the vast cosmos, the search for extraterrestrial life has become one of humanity's most profound quests. The insights we gain from extremophiles, organisms thriving in Earth's harshest environments, profoundly shape our approach to this search. These organisms' remarkable adaptability suggests that life could thrive in conditions we once thought hostile to existence. The possibility that life forms could exist in a multitude of environments far beyond the familiar landscapes of Earth challenges the very limits of our imagination and expands our understanding of what life can be. As we design experiments and instruments for space missions, these revelations guide our search for biomarkers and the assessment of habitability on distant planets and moons. Whether it's detecting traces of life on Mars, or identifying the potential for life in the subsurface oceans of moons like Europa, the search is now aimed at finding life in all its potential forms, in environments that range from the coldest, most barren places to the most extreme heat. But what about the challenge of communicating with intelligent extraterrestrial life, should we encounter it? This task presents complexities that stretch the boundaries of human creativity, technology, and patience. Initial contact, if it ever happens, will likely rely on the transmission of electromagnetic signals. Much like the search for extraterrestrial intelligence SETI programs, we would send and receive signals, radio or laser waves, hoping to detect something that indicates advanced civilization. When we first detect a signal, it will be crucial to establish whether it is indeed artificial. The key will lie in the pattern, a coherent, repetitive signal, or one that demonstrates a mathematical structure, would strongly suggest an intelligent origin. Mathematics, often referred to as the universal language, could form the basis of our communication. Simple mathematical sequences, such as prime numbers, the Fibonacci series, or even basic arithmetic, might serve as the initial foundation for establishing communication. These are patterns that could be universally recognized by any intelligent being. In 1974, the Arecibo message was transmitted to space as an attempt to communicate with potential extraterrestrial intelligence. It was a simple binary-coded message that conveyed information about human biology, our solar system, and the structure of DNA. This kind of message, featuring graphical representations, is an early example of how we might attempt to communicate with beings from distant stars. Once we've confirmed that the signal is indeed coming from intelligent life, the next step would involve deciphering and responding to it. This process, however, is far from simple. It requires creating a shared understanding of symbols and concepts, an enormous task considering the potential differences between civilizations. Visual or pictorial representations might help bridge the linguistic gaps. Basic images of stars, planets, or geometric shapes might serve as a common ground. These simple symbols could communicate universal concepts in ways words and numbers alone could not. For example, the development of a lingua cosmica, a universal language for cosmic communication, might involve starting with very basic ideas and gradually increasing complexity as both civilizations grow more familiar with each other's ways of thinking. This approach would be based on the assumption that intelligent beings across the universe would share some fundamental cognitive abilities, such as the capacity to understand simple patterns and symbols. However, creating a universal language doesn't end with the transmission of a few basic ideas. Over time, as communication deepens, we would need to tackle the issue of complexity. Building a language that both civilizations can learn and understand over time would require patience and foresight. As it stands, real-time interactive communication would likely be impossible due to the immense distances involved, meaning messages would take years or even decades to travel between civilizations. Thus, the process of communication would be slow, requiring sustained efforts and the willingness to learn and adapt from both sides. Each message and response would be carefully crafted to consider cultural differences, anticipating how the other civilization might interpret what we send. This approach would allow both parties to engage in a cooperative learning process, bridging cognitive and cultural divides that may span light years. Moreover, the ethical implications of such communication are significant. Deciding what to say, when to say it, and whether to respond at all requires careful thought and global collaboration. The consequences of making contact with extraterrestrial life could be far-reaching, affecting not just scientific understanding, but potentially the very course of human history. As we craft these messages, we must ensure that our intentions are clear. Messages should not convey hostility, imperialism, or misunderstanding. Such a monumental exchange could alter the course of civilization in ways we can only begin to imagine. As we continue to look outward, searching the cosmos for signs of life, one thing is certain: the process of communication with extraterrestrial intelligence will require not just advanced technology, but also the highest levels of wisdom, ethics, and foresight. Our future as a species might depend not only on our ability to find life beyond Earth, but on how we choose to engage with it. In our exploration of the cosmos, we must consider how diverse cultures and perspectives can shape our understanding of the universe and our communication with intelligent extraterrestrial life. Engaging with these new possibilities requires a multifaceted approach, one that includes the recognition of signals, the establishment of common languages and mathematical foundations, the development of structured messaging, and the deep ethical considerations of such an endeavor. As humanity approaches this unknown frontier, global cooperation is not just a necessity, but a responsibility. We must approach this challenge methodically, fostering an openness to learning from intelligence that may be vastly different from our own. The process would undoubtedly mark a profound milestone in our collective understanding, not just of the universe, but also of ourselves. Much like the exploration of otherworldly communication, the birth of stars unfolds in a manner that reflects the intricate and sometimes unexpected processes governing our universe. In the vast, cold regions of space, known as molecular clouds, new stars are born. These clouds are dense and cool, so much so that hydrogen atoms pair up, forming molecules. They stretch across vast expanses of space, often spanning light years, holding within them enough gas and dust to form thousands of new stars. Within these stellar nurseries, the formation of stars begins when certain conditions disrupt the equilibrium of the cloud, causing parts of it to collapse under its own gravity. Imagine the calm of a foggy morning, suddenly disturbed by a gust of wind. In much the same way, external forces, such as shockwaves from nearby supernovae or the gravitational pull of passing celestial bodies, compress sections of the molecular cloud, triggering the collapse. As the collapsing gas and dust accumulate, they form a protostar. The temperature in this collapsing region rises due to the conversion of gravitational potential energy into heat, driven by the principles of thermodynamics and gravity. Over millions of years, this increasingly hot and dense core begins to gather mass. When it reaches a temperature high enough, several million degrees, nuclear fusion ignites. The hydrogen atoms in the core begin fusing into helium, releasing an immense amount of energy and signaling the birth of a new star. This transformation from a cold, inert mass of gas and dust to a blazing stellar beacon is one of the most awe-inspiring phenomena in the universe, governed by the laws of physics that connect the cosmic scale to the atomic scale. As stars age, their journey continues through increasingly complex stages. The spectacular shapes and vivid colors observed in planetary nebulae are a dramatic and beautiful encore to the lives of dying stars like our Sun. Imagine an aging actor stepping away from the stage, leaving behind a legacy full of emotions and stories. Similarly, as a star exhausts the nuclear fuel in its core, it becomes unstable, eventually expelling its outer layers into space. This ejected material forms the nebula, a glowing shell of gas and dust. These nebulae often showcase intricate and mesmerizing shapes, rings, spirals, or even symmetrical patterns that resemble cosmic flowers. Stellar winds, streams of charged particles emitted by the dying star, sculpt these clouds into breathtaking forms. Magnetic fields and the presence of nearby binary stars further contribute to the symmetry and complexity of these celestial works of art. The dazzling colors that define planetary nebulae arise from the interaction between ionized gases and ultraviolet radiation from the hot core of the dying star. Each element within the nebula emits light at specific wavelengths when ionized, creating the rich array of colors we observe. For example, ionized hydrogen shines with a deep red, while oxygen ions emit a striking greenish-blue hue. But these radiant gases are more than just a spectacle. They offer us a rich tapestry of information about the composition, dynamics, and history of the dying star. The way these elements interact, shaped by the star's mass, chemical makeup, and the influence of nearby companions, results in the captivating and diverse structures we see through telescopes. These nebulae, though they mark the end of one star's life, also serve as a fertile ground for new beginnings. The expelled material will eventually come together to form new stars, planets, and potentially even life, continuing the infinite cycle of cosmic evolution. Beyond the stunning beauty of these cosmic phenomena lies a deeper story, one of destruction and creation, death and rebirth. The remnants of a supernova, another of the universe's most powerful events, serve as a spectacular reminder of the constant cycles of transformation. This cycle of birth, death, and renewal is not only written in the stars, but in the very fabric of existence itself. As we continue to observe and study these events, we unlock deeper insights into the forces that shape our universe, and perhaps we gain a greater understanding of our place within it. In the vast cosmic tapestry, the involvement of diverse cultures and perspectives can help shape our understanding, ensuring that as we venture into the unknown, we do so with humility, wisdom, and a sense of responsibility toward the broader universe. In the vastness of space, there exists a phenomenon of unimaginable power, the explosive death of a massive star. When a star, at least 8 times the mass of our sun, exhausts its nuclear fuel, its core succumbs to the crushing force of gravity. This collapse triggers a cataclysmic supernova explosion, an event so intense that it can outshine an entire galaxy, albeit briefly. The force of this explosion hurls the star's outer layers into space, traveling at speeds that can reach up to 30,000 kilometers per second. What remains is a supernova remnant, a complex and dynamic region where the remnants of the explosion interact with the interstellar medium, the sparse mixture of gas and dust that fills the vast expanses between stars. Immediately following the explosion, the shockwave from the supernova sweeps outward, compressing surrounding material and driving it to unimaginable temperatures and densities. This shockwave is not just a destructive force, it is a cosmic seed for new beginnings. By compressing nearby molecular clouds, it can trigger the formation of new stars, essentially creating stellar nurseries in the aftermath of a violent end. Over thousands of years, the material ejected by the star begins to slow down and cool, but the energetic processes continue to unfold, enriching the interstellar medium with heavy elements like iron, oxygen, and silicon, elements that originated deep within the star's core. These elements are crucial for life as we know it. They are the building blocks for planets and the organic molecules that form the foundation for life itself. The supernova remnants, therefore, play a pivotal role in cosmic evolution, shaping the creation of new stars and influencing the chemical makeup of future solar systems. Through their dynamic, far-reaching interactions, these remnants weave a narrative of destruction and renewal, reminding us that even in the most catastrophic events, there is the potential for rebirth. In the grand tapestry of the cosmos, seemingly insignificant particles, interstellar dust, are among the most important agents of planetary formation. These tiny grains, composed of silicates, carbon compounds, and ice, serve as the foundational building blocks of planetary systems. Picture a vast cosmic bakery, where these dust grains are the flour from which the planets are eventually baked. Within molecular clouds, these dust particles become crucial raw materials, aiding in the cooling processes necessary for the collapse of gas clouds to form stars and their accompanying protoplanetary disks. As a new star begins to take shape, the surrounding disk, composed of both gas and interstellar dust, undergoes a remarkable transformation. Dust grains within the protoplanetary disk collide and stick together through electrostatic forces, slowly merging into larger particles. Over time, these particles clump together to form planetesimals, the seeds of future planets. It's a process akin to snowballing, where these planetesimals grow in size, their gravitational pull increasing and attracting more material. Eventually, this leads to the creation of protoplanets, which, through further accumulation and gravitational processes, can become fully formed planets, moons, and other celestial bodies within a solar system. But the role of interstellar dust doesn't end there. These grains are also catalysts for chemical reactions vital for life. They provide surfaces on which molecules can form and grow, including organic compounds that are the precursors to life. Moreover, dust shields these chemical processes from harmful stellar radiation by absorbing and scattering light. In doing so, they create a protective environment within the cold, dark regions of space, fostering the development of complex chemistry that may eventually give rise to life as we know it. Thus, interstellar dust is far from a passive bystander in the cosmic drama. It is an active participant in the creation of planetary systems and the very chemistry that could lead to the emergence of life. Without it, the intricacies of planetary formation and the possibilities for life in our galaxy would be impossible. And then there are the cosmic rays, high-energy particles that streak through space at nearly the speed of light. These invisible threads of energy, primarily protons, along with heavier atomic nuclei and electrons, originate from powerful and energetic processes like supernova explosions and the activity of supermassive black holes in distant galactic centers. When these cosmic rays collide with interstellar gas and dust, their incredible energy triggers a cascade of interactions. These interactions ignite a rich tapestry of astrophysical processes that shape the galaxy's physical, chemical, and magnetic properties. Cosmic rays, therefore, are not just a byproduct of stellar and galactic phenomena. They are a driving force behind the evolution of the interstellar medium and, by extension, the very structure of our galaxy. In the grand design of the universe, every star's death, every grain of dust, and every cosmic ray contributes to the continuous cycle of creation and destruction that shapes the cosmos. From the explosive deaths of stars to the birth of new planetary systems, from the catalytic actions of dust to the far-reaching influence of cosmic rays, these cosmic processes work together in a beautiful and complex dance. In this endless cycle of transformation, the universe reveals its intricate and awe-inspiring nature, where even the smallest particle can have a monumental impact on the future of everything. In the vastness of the universe, cosmic rays play a crucial and often overlooked role in shaping the very fabric of our cosmic surroundings. These high-energy particles, traveling at nearly the speed of light, penetrate deep into the interstellar medium, triggering processes that are fundamental to the evolution of galaxies, stars, and the intergalactic medium itself. One of the most significant contributions of cosmic rays is their influence on the ionization of the interstellar medium, particularly hydrogen atoms. When a cosmic ray collides with a hydrogen atom, it knocks off an electron, creating a positively charged ion. This ionization process doesn't just alter the chemical composition of the medium, but also plays a pivotal role in the broader dynamics of star formation. In fact, cosmic rays serve as a catalyst for complex chemical reactions, including the formation of molecular hydrogen, a molecule essential for the birth of new stars. The ionization effects from cosmic rays speed up the process of molecular hydrogen creation, which in turn accelerates the cooling rates and dynamical evolution of molecular clouds. These clouds, the birthplaces of stars, are heavily influenced by the ionization process, determining where and when stars will form. But the impact of cosmic rays doesn't end with chemical reactions. These particles contribute to the thermal pressure within interstellar clouds. As cosmic rays penetrate deeper into the clouds, they release energy, heating the gas inside. This heating effect is vital as it helps balance gravitational collapse and prevents the cloud from cooling too rapidly. Without this thermal regulation, clouds could collapse prematurely, disrupting the delicate balance required for star formation. In essence, cosmic rays help maintain the temperature of the interstellar medium, ensuring that it remains in a stable state for star formation to occur over millions of years. In addition to their thermal influence, cosmic rays also affect the magnetic fields that permeate the galaxy. As these energetic particles spiral along magnetic field lines, they exert a force that can amplify and stabilize these fields. This magnetic interplay is crucial for maintaining the overall structure of the interstellar medium and ensuring the stability of the galaxy itself. Through their dynamic interactions, cosmic rays essentially sculpt the shape of the galaxy, playing an understated yet vital role in its ongoing evolution. Meanwhile, the intergalactic medium, IgM, which spans the vast space between galaxies, acts as the backbone of the cosmic structure. Occupying more than half of the universe's visible matter, the IgM is composed primarily of ionized hydrogen, which exists as individual protons and electrons. This medium is far from uniform. Instead, it forms a complex web of filaments and voids, often referred to as the cosmic web. This web reflects the large-scale structure of the universe and serves as a framework for galaxy formation and evolution. Within this intricate network, dense regions known as nodes mark the intersections of filaments where galaxy clusters are found. These nodes harbor vast amounts of gas, which can cool and condense to form new galaxies, a process vital for the ongoing evolution of the cosmos. In the more tenuous regions, the filaments act as highways for both gas and dark matter, linking the nodes and fueling the growth of cosmic structures. Observations from powerful instruments, such as the Hubble Space Telescope and the Chandra X-ray Observatory, have revealed that the temperature within these filaments can reach extremes, ranging from thousands to millions of degrees Kelvin. Hotter regions are often linked to shock waves produced by gravitational interactions and the formation of new structures. These shock waves are the universe's way of managing the immense forces at play in the formation of galaxies and stars. The IgM is not a passive entity, but an active participant in the cosmic cycle. It serves as a reservoir from which galaxies draw material to sustain star formation. Additionally, it acts as a conduit for energy and matter expelled by galaxies through winds and supernovae. The ongoing interaction between galaxies and the IgM forms a continuous feedback loop, with energy and matter cycling between them, influencing galaxy evolution over vast stretches of time. An intriguing feature of the IgM is the presence of heavier elements, such as carbon, oxygen, and nitrogen. These elements serve as a reminder of the explosive supernova events that have occurred over billions of years. These stellar explosions spread elements forged within stars into the IgM, enriching the medium and contributing to the ongoing process of galaxy formation and evolution. The composition and structure of the IgM are critical not only for understanding the distribution of matter across the universe, but also for unraveling the intricate evolutionary pathways of galaxies. One of the most visually captivating aspects of galaxy formation is the presence of high regions, glowing clouds of ionized hydrogen surrounding newborn stars. These regions, often referred to as stellar nurseries, play an essential role in shaping the formation and regulation of stars. The intense ultraviolet radiation emitted by young, massive stars ionizes the surrounding hydrogen gas, creating luminous nebulae that radiate light and heat. These stunning, vibrant regions are not just aesthetic marvels. They are the fundamental sites where stars are born, providing the necessary environment for star formation to thrive. In the grand tapestry of the universe, cosmic rays, the intergalactic medium, and HII regions form an interconnected system that influences the birth, life, and death of stars and galaxies. Through their dynamic interactions, they shape the structure of the universe, sculpting the cosmos in ways both beautiful and essential to its ongoing evolution. These forces, although invisible to the naked eye, are at the heart of the universe's constant transformation. In the vast expanses of the universe, the birth of new stars is a spectacular and complex process influenced by a variety of factors. One of the most intriguing and multifaceted influences on star formation comes from H2 regions, vast clouds of gas ionized by the intense radiation of young hot stars. The impact these regions have on their surroundings is profound, shaping the environment where new stars are born. First, the young stars at the heart of H2 regions are powerful cosmic engines. Their intense radiation heats the surrounding gas, causing it to ionize. This creates a high-pressure environment that pushes against nearby molecular clouds, compressing them. This compression triggers the gravitational collapse of the gas, a critical step in the formation of new stars. In this way, young stars effectively act as cosmic catalysts, setting off a chain reaction of star birth. This process, known as triggered star formation, can send waves of new stars rippling across the galaxy. Each new generation of stars ignites the creation of the next, ensuring that star formation continues in a dynamic cycle. However, the role of H2 regions is not simply to nurture new stars. They also act as feedback mechanisms that can disrupt this process. The powerful stellar winds and radiation released by massive stars within these regions can blow away the surrounding gas, dispersing the very material necessary for new stars to form. This disruption creates cavities or bubbles in the surrounding interstellar medium, limiting the material available for further star formation. In this sense, H2 regions play a dual role, both stimulating and inhibiting star birth. The balance between these two opposing forces determines the overall rate of star formation in a galaxy and shapes its long-term evolution. H2 regions are central to the complex interplay that governs the rhythm of star formation in galaxies. Their influence extends far beyond their immediate surroundings, affecting the broader interstellar medium and setting the stage for future generations of stars. The energy they release creates an ever-changing dynamic where stars are continually being born, but also continually being displaced and disrupted. This feedback loop ensures that galaxies remain vibrant, evolving systems, constantly shifting between cycles of star birth, growth, and decay. As we turn our gaze to the intricate beauty of nebulae, we are met with a breathtaking display of cosmic dynamics. The filamentary structure of some nebulae is a remarkable testament to the forces shaping our universe. These thread-like patterns are the result of a combination of physical processes that interact within the interstellar medium. One of the primary factors responsible for the formation of these filaments is the interaction of stellar winds and shock waves. Massive stars in particular emit strong winds that sweep through the surrounding gas, compressing it into elongated shapes. Imagine the effect of a powerful gust of wind sweeping across a sandy beach, creating ripples in the sand. Similarly, these stellar winds carve out delicate filaments within the gas of the nebula, shaping the cosmic landscape. Supernova explosions also play a critical role in forming filaments. When a massive star reaches the end of its life and undergoes a supernova, it releases an enormous amount of energy. This explosion sends shock waves rippling through the surrounding gas, compressing and heating it. As the shock waves travel outward, they create regions of high pressure that condense into long, stretched filaments. These shock waves can continue to propagate through the interstellar medium for thousands of years, creating new filaments in their wake. This dynamic process is particularly evident in supernova remnants, where the expanding shock wave perpetuates the formation of these intricate structures. Magnetic fields also contribute to the stunning filamentary patterns observed in nebulae. The interstellar medium is threaded with magnetic fields, which exert a subtle yet powerful influence on the movement of charged particles. As gas and dust particles interact with these magnetic fields, they align themselves along the field lines, creating elongated structures that resemble filaments. The behavior of these magnetic fields is similar to the way iron filings align along the lines of a magnetic field on Earth, organizing the gas and dust into intricate, thread-like patterns. Additionally, gravitational interactions and turbulence within molecular clouds further enhance the formation of filaments. As regions of these clouds collapse under the force of gravity to form new stars, the surrounding material is drawn into elongated structures. At the same time, turbulent motions within the clouds stretch and twist the gas, creating complex, twisted filamentary patterns. These forces, stellar winds, shock waves, magnetic fields, gravity, and turbulence, combine to create the breathtaking and dynamic filamentary structures we observe in nebulae, offering a vivid glimpse into the processes that shape the universe. Beyond their visual beauty, interstellar magnetic fields play a critical role in shaping the behavior of gas and dust within galaxies. These fields exert a hidden yet powerful influence on the movement and structure of cosmic matter, guiding the flow of material and helping to organize the chaotic motions within the interstellar medium. Their effect on the evolution of galaxies cannot be overstated, as they are fundamental in sculpting the cosmic structures that define the universe. In the grand tapestry of the cosmos, H2 regions, stellar winds, shock waves, and magnetic fields all work together to create the stunning filaments we observe in nebulae, painting a dynamic and ever-changing picture of the universe's evolution. The intricate interplay between these forces ensures that the universe remains a place of constant motion and transformation, with new stars and structures emerging in a continuous cycle of cosmic creation. Imagine, if you will, the invisible scaffolding that quietly directs the dance of particles across the vast expanse of the universe. These fields, magnetic fields, though often weak compared to other cosmic forces, wield an undeniable influence over the dynamics of the interstellar medium. It is through these fields that gas and dust, dispersed throughout galaxies, find their order. The dance of particles, largely charged ions and electrons, is no longer free to move in any direction. Instead, the magnetic fields impose a kind of structure, guiding the motion of these particles as they spiral along the lines of force. The result? The gas is constricted, forced to follow paths that are aligned with the magnetic field, preventing it from freely dispersing in perpendicular directions. This motion creates elongated structures, vast tendrils, stretching through the void, adhering to the invisible lines of magnetic influence. But their influence goes far beyond mere motion. Magnetic fields play a pivotal role in the formation of stars, especially within the molecular clouds that serve as stellar nurseries. Within these dense, dark clouds of gas and dust, stars are born. However, the process is not as simple as gravity pulling everything together. Magnetic fields can act as a counterforce, slowing the collapse of the gas and creating a delicate balance with the gravitational pull. This balance is key. If gravity were allowed to act unchecked, all the gas would collapse too quickly, potentially leading to chaotic star formation. The magnetic fields, however, provide support, preventing such a runaway collapse. This regulated tension ensures that star formation occurs at a steady pace, allowing new stars to emerge over extended periods rather than in sudden bursts. Furthermore, magnetic fields influence the turbulence within these molecular clouds. Turbulence, caused by forces like gravity and the shock waves from exploding stars, creates a chaotic, erratic motion in the gas. But where there's magnetic influence, there's organization. The magnetic fields help to channel and dampen the turbulence, creating well-defined filamentary structures within the clouds. These filaments, often the sites where new stars will form, provide a cosmic blueprint, shaping the formation of future generations of stars. And, as if that weren't enough, magnetic fields also interact with dust grains, causing them to align with the field lines. This alignment affects the polarization of light passing through the dust, providing astronomers with a wealth of information about the direction and strength of magnetic fields in the interstellar medium. Magnetic fields, therefore, are not just subtle players in the cosmos. They are fundamental forces, shaping the movement of gas and dust, regulating star formation, and providing the structure that supports the vast, intricate architecture of galaxies. Their role in the universe is as invisible as it is crucial, forming an intricate backbone that holds the cosmic tapestry together. Now, zooming in even further on the grand spectacle of stellar life, the nebulae in the universe serve as the backdrop for the stories of stars. These glowing gas clouds are not just beautiful, they are the archives of stellar evolution. Each type of nebula represents a different chapter in the life cycle of stars, offering insights into their birth, evolution, and eventual demise. Think of each nebula as a cosmic chapter, revealing the underlying physical processes that govern the universe's most fundamental objects. For example, H2 regions and emission nebulae are like the birth certificates of stars. These regions, rich in gas and dust, are home to young, hot stars that ionize surrounding hydrogen, causing the gas to glow brightly. The study of these stellar nurseries reveals how stars are born, how they influence their surroundings through their powerful winds and radiation, and how they can trigger the formation of new stars in the surrounding gas clouds. By understanding these regions, astronomers can uncover the secrets of triggered star formation and learn how conditions in different parts of galaxies influence the birth of new stars. On the opposite end of a star's life, we have planetary nebulae and supernova remnants, both offering profound insights into the final chapters of stellar evolution. When low to intermediate mass stars reach the end of their lives, they shed their outer layers, creating the glowing shells of ionized gas we call planetary nebulae. These nebulae not only help us understand the processes occurring as a star dies, but they also play a critical role in returning material to the interstellar medium. This material enriches future generations of stars and planets. Studying planetary nebulae allows astronomers to peer into the stars' lifetimes, learning about nucleosynthesis, the process by which new elements are created inside stars. Supernova remnants, on the other hand, represent the explosive deaths of massive stars. When these stars go supernova, the shock waves from the explosion spread through space, heating and compressing the surrounding material. This can trigger new waves of star formation in its wake. Supernovae also create the heavy elements that are scattered throughout the universe, such as iron, gold, and uranium. These explosions generate cosmic rays, high-energy particles that travel through space, affecting everything in their path. By studying supernova remnants, astronomers gain a deeper understanding of the most violent processes in the universe and the way in which elements necessary for life are forged and dispersed across galaxies. Through the study of nebula, whether they are stellar nurseries or remnants of explosive stellar deaths, we uncover the intricate interconnected processes that shape stars and, in turn, the galaxies they inhabit. These phenomena, governed by magnetic fields and the forces of gravity, wind, and radiation, offer an ever-expanding narrative of stellar evolution, one that continues to unfold across the universe. Nebulae and dark nebulae are essential components in our understanding of the cosmos, playing key roles in revealing how stars interact with their surroundings. Reflection nebulae, which shine by scattering the light of nearby stars, provide astronomers with valuable insights into the properties of interstellar dust. They help us explore how light behaves as it travels through the vastness of space. Meanwhile, dark nebulae, which obscure light from distant stars, offer a glimpse into the densest regions of interstellar clouds. These regions often serve as the birthplaces of new stars. By studying these distinct types of nebulae, scientists can piece together a comprehensive picture of stellar evolution, tracing the journey of stars from their formation in dense molecular clouds to their eventual fate as planetary nebulae or supernova remnants. This intricate tapestry of stellar life cycles deepens our understanding of the universe's history. It contributes to our knowledge of galaxy evolution, star formation rates, and the cosmic enrichment of elements essential for life itself. The study of nebulae not only reveals the birth and death of stars, but also uncovers the processes that shape the evolution of galaxies. Understanding the interaction between stars, dust, and gas in these regions provides critical insights into the mechanics of star systems and the broader dynamics of our galaxy. Another fascinating structure in the universe is the spiral arms of galaxies, whose formation is primarily attributed to the density wave theory. This theory suggests that the spiral arms aren't made up of a permanent group of stars, but are instead regions of higher density that move through the galaxy. Think of it as a traffic jam on a highway. As stars, gas, and dust enter these denser regions, they slow down and become more tightly packed. This accumulation of matter lights up the spiral arms, creating the brilliant, shining paths we observe from Earth. The movement of these density waves also triggers star formation, giving birth to the bright young stars that illuminate the spiral arms. This process helps these arms maintain their distinct luminous appearance. Without the density wave mechanism, the spiral arms would wind up and lose their shape relatively quickly, as the galaxy's inner regions rotate faster than the outer ones. However, the persistent gravitational effects and the interactions between stars, gas, and dust, combined with the density waves, help preserve the arm's stability over cosmic timescales. Additionally, gravitational influences from nearby galaxies or galactic bars can stimulate and regulate these spiral formations, ensuring the arms retain their majestic and recognizable shape for billions of years. Within these spiral arms, stellar populations are constantly being refreshed. As new stars are born, they keep the arms bright and distinct. These young, hot stars continue to shine, making the spiral arms one of the most captivating features in the universe. The interplay between star formation, gravitational interactions, and density waves creates a dynamic system that shapes the structure of galaxies, allowing them to evolve over time. At the heart of many galaxies, particularly in spiral galaxies lies another intriguing feature: galactic bars. These elongated structures are found at the center of about two-thirds of all spiral galaxies. Their formation is linked to gravitational instabilities within the galaxy's rotating disk. When stars and gas move through the disk, small perturbations can develop due to gravitational interactions. Over time, these small disturbances can grow and stretch into the elongated bar-like shapes we recognize. Galactic bars are regions of higher star and interstellar matter density. Their presence significantly affects the dynamics of a galaxy. For instance, they act as mechanisms for channeling gas from the outer regions toward the center of the galaxy. This influx of gas can fuel star formation and even contribute to the growth of a central supermassive black hole. Studies have shown that bars play a crucial role in driving the galaxy's spiral structure, redistributing angular momentum within the galactic disk. Interestingly, the development of a galactic bar is a relatively rapid process in cosmic terms, sometimes occurring in just a few 100 million years. Over longer time frames, interactions with neighboring galaxies can trigger or enhance bar formation through gravitational tidal forces. These dynamic processes demonstrate that galaxies are not static entities. Rather, they are constantly evolving, reshaping themselves over time. The life cycles of stars, the movement of gas, and the interplay of gravitational forces all contribute to the ongoing transformation of galaxies, making them ever-changing and complex structures. In summary, nebula, spiral arms, and galactic bars are not just beautiful features in the night sky. They are vital components of a broader cosmic narrative, telling the story of star birth, galaxy evolution, and the dynamic nature of the universe. Through the study of these phenomena, astronomers gain valuable insights into the complex processes that shape the cosmos, allowing us to better understand our place in this vast and ever-changing universe. Galactic interactions and mergers are some of the most dramatic and influential events in the universe. These extraordinary cosmic collisions begin far before the galaxies actually merge, often triggered by the powerful gravitational forces that pull them closer together. As galaxies approach one another, their mutual gravitational attraction warps and distorts their shapes, initiating the formation of tidal tails, long, sweeping strands of stars and gas pulled away from their galactic bodies. These celestial features are more than just a spectacle. They carry crucial information about the forces at play in these encounters. As the galaxies move closer, the gravitational forces compress the gas within, triggering explosive bursts of star formation, phenomena known as starbursts. These intense episodes of stellar creation play a crucial role in the evolution of the galaxies involved. Eventually, the galaxies will collide and their cores will merge, leading to the formation of a new, often unexpected structure. The consequences of such a merger can be profound, resulting in the birth of elliptical galaxies, particularly when two large spiral galaxies collide. The chaotic nature of these collisions drives gas toward the centers of the merging galaxies, feeding supermassive black holes and potentially activating their nuclei. This can lead to the creation of an active galactic nucleus, AGN, a temporary but powerful entity that can outshine the entire galaxy. The energy released during this merger process can heat up the surrounding gas, preventing it from cooling and condensing into new stars for an extended period. This is why many elliptical galaxies, the product of such cosmic crashes, contain older stellar populations with minimal new star formation. Over millions to billions of years, the remnants of these galactic mergers eventually settle into a new equilibrium. However, the marks of their turbulent past remain evident, often preserved in unusual stellar distributions, altered morphologies, and the presence of stellar streams, cosmic remnants of a dramatic and dynamic history. These colossal events serve as vivid reminders of the dynamic and ever-changing nature of the universe. Alongside these mergers, galactic winds and outflows play a significant role in shaping the evolution of galaxies. Driven primarily by intense star formation and the energetic processes of supermassive black holes within active galactic nuclei, these winds are some of the universe's most powerful phenomena. In regions where rapid star formation occurs, massive stars and supernovae release tremendous amounts of energy, pushing vast amounts of gas and material out of the galaxy. These stellar winds are not only visually spectacular, but they also regulate the amount of gas available for future star formation, acting as a feedback mechanism that prevents galaxies from turning all their gas into stars too quickly. The role of active galactic nuclei, AGN, in driving these galactic winds cannot be overstated. When matter falls into a supermassive black hole, the process of accretion generates an immense amount of energy in the form of jets and radiation. These energetic outputs can sweep up surrounding gas and push it far beyond the galactic boundaries, reaching velocities of several thousand kilometers per second. This process can have far-reaching consequences. It can quench star formation by blowing away the gas needed for new stars and alter the intergalactic medium in ways that affect the surrounding cosmic environment. Through these feedback processes, active galactic nuclei ensure that galaxies do not consume all their gas too rapidly, maintaining a delicate balance in their evolution and allowing them to sustain star formation over much longer timescales. The interplay between stellar-driven winds and AGN activity is a self-regulating mechanism crucial for the life cycle of galaxies. These powerful processes help maintain the equilibrium necessary for galaxies to grow and evolve over cosmic timescales. Supermassive black holes, located at the centers of most large galaxies, profoundly influence the development of their host galaxies. Through their immense gravitational pull and energetic feedback, these black holes can regulate star formation rates by controlling the availability of cold gas needed for new stars. They can also expel gas from their host galaxies, halting the creation of new stars and altering the galactic structure in profound ways. In essence, supermassive black holes are not just passive structures at the heart of galaxies. They are active participants in their evolution. Through the processes of accretion, radiation, and the creation of galactic winds, they can influence the very fabric of their galaxies, guiding their growth and shaping their future for billions of years. The dynamic interactions between these massive cosmic entities and their surrounding environments underscore the complex and interconnected nature of the universe. As galaxies collide, merge, and evolve, the balance between star formation and galactic feedback remains one of the most fascinating and critical aspects of cosmic evolution. In the vast expanse of the cosmos, one profound consequence of active galactic nucleus AGN feedback is the regulation of star formation. Without this crucial feedback, galaxies would swiftly deplete their gas reserves, consuming them at an unsustainable rate and churning out stars in an explosive burst. However, AGN outflows, propelled by the immense power of supermassive black holes, can push this gas out to the outer regions of galaxies, or even expel it into the void of interstellar space. This process maintains a delicate equilibrium, allowing galaxies to form stars over much longer periods, instead of exhausting their resources too soon. Additionally, the energy released by AGNs heats the surrounding gas, making it difficult for it to cool and condense into new stars. This process is most commonly observed in massive elliptical galaxies, where star formation has essentially ceased, leaving only older, redder stars. The interaction between AGN jets, winds, and the surrounding gas can create powerful shock waves and turbulence, influencing how gas is distributed and how it behaves within the galaxy. Essentially, supermassive black holes act as cosmic regulators, ensuring that galactic processes remain balanced and that the galaxy evolves at a controlled pace. By shaping the structure and future of galaxies, AGN feedback plays an integral role in their cosmic evolution. Galaxies that have stopped forming stars, often referred to as red and dead, undergo profound transformations. These transformations result from a variety of internal and external forces that expel, compress, or heat the gas necessary for star formation. The feedback from AGNs is one of the primary mechanisms behind this cessation of star birth. When a supermassive black hole at the center of a galaxy consumes matter, it releases vast amounts of energy in the form of radiation and powerful jets. This AGN feedback heats the surrounding gas to such extreme temperatures that it can no longer cool down and condense into new stars. In some cases, the gas is even ejected entirely from the galaxy, depleting its star-forming material. Beyond internal forces, external environmental effects also play a significant role in the quenching of star formation. In dense regions of the universe, like galaxy clusters, galaxies are subjected to extreme conditions. Ram pressure stripping, for example, occurs when the hot, dense intercluster medium sweeps away a galaxy's gas as it moves through the cluster. Gravitational interactions with other galaxies, such as mergers or tidal forces, can trigger starbursts which rapidly consume the available gas. However, after these bursts, the remaining gas may be too hot or too dispersed to efficiently condense into new stars. Over time, the galaxy exhausts its gas reservoir and the process of star formation grinds to a halt. The existing stars continue to age, and the once vibrant galaxy is dominated by long-lived, redder stars, earning it the characteristic red and dead appearance. The balance between internal mechanisms, like AGN activity, and external environmental influences serves as a powerful force guiding galaxies toward a quieter, more quiescent phase in their evolutionary journey. On a smaller scale, dwarf galaxies, those humble, less luminous cousins of larger galaxies, form and evolve in a distinctly different manner. Typically having lower masses and weaker gravitational fields, dwarf galaxies are more vulnerable to external forces. Their formation often traces back to the early universe, nearly 13 billion years ago, when small fluctuations in the primordial gas began to collapse under gravity, forming the first dwarf galaxies. These early galaxies consisted of dark matter halos, gas, and newly formed stars, but their limited gravitational pull often led to inefficient star formation, leaving them with large gas reservoirs relative to their stellar populations. As dwarf galaxies orbit larger galaxies, they are profoundly influenced by tidal forces. These forces distort the structure of the dwarf galaxy, often leading to tidal stripping, where stars and gas are pulled away from the galaxy, creating elongated streams that are absorbed into the larger galaxy's halo. Furthermore, as dwarf galaxies pass through the hot, diffuse gas in galaxy clusters or within the halos of larger galaxies, they can experience ram pressure stripping, which sweeps away their interstellar medium and halts their ability to form new stars. In essence, the evolution of dwarf galaxies is deeply entwined with the fate of their larger counterparts, as external forces gradually alter their structure and star-forming capabilities. These forces, both internal and external, guide the galaxy toward a quieter existence, with star formation ceasing and their once vibrant stars aging into the distant future. Thus, whether through the immense power of AGN feedback or the tidal and pressure-induced transformations from their larger neighbors, galaxies, big or small, undergo significant changes. These cosmic forces serve as regulators of the galactic life cycle, ensuring that star formation continues, halts, or evolves in a way that shapes the future of the galaxy itself. However, these interactions are not purely destructive. In fact, they can serve as the catalyst for bursts of star formation as they compress the gas within dwarf galaxies. Over time, many of these smaller galaxies can be completely assimilated by their larger counterparts. This process contributes both stars and gas to the halos and disks of the more massive galaxies. Stellar streams and remnants observed around the Milky Way, as well as other giant galaxies, provide concrete evidence of this phenomenon. This complex and dynamic dance of interactions helps shape both the dwarf galaxies and their larger companions, influencing the broader structure and evolutionary trajectory of the cosmic landscape. High-velocity clouds, HVCs, are another captivating feature of the galactic halo. They travel at speeds that significantly differ from the normal rotation of their host galaxies. The origins and nature of these clouds are multifaceted and cater to a range of astrophysical phenomena. One prominent hypothesis suggests that HVCs are remnants of the primordial gas from which galaxies formed. These ancient clouds of gas may have remained relatively unchanged over billions of years, serving as reservoirs of primordial hydrogen. Another theory proposes that these high-velocity clouds are the result of gas stripped from satellite galaxies during their interactions with a more massive galaxy. Tidal forces from these interactions pull gas out of the smaller galaxies, creating streams or clouds of gas that travel through the galactic halo. Additionally, HVCs can originate from a process known as galactic fountains. Intense stellar activity, such as supernova explosions and strong stellar winds, can expel gas from the galactic disk into the halo. As the gas cools, it slows down and eventually falls back towards the disk, creating a cyclic flow of material. This expelled gas, enriched with heavy elements from stellar processes, contributes to the chemical evolution of the galaxy when it reintegrates into the disk. The study of high-velocity clouds provides invaluable insights into the life cycle of baryonic matter within galaxies. These clouds can serve as fuel for new star formation as they deliver fresh gas back into the galactic disk. Observations made using radio telescopes, particularly those focused on the 21-centimeter line of hydrogen, yield crucial data on the velocities, compositions, and distributions of these clouds. Their interaction with the interstellar medium, as well as their potential role in galactic evolution, makes them vital to understanding the broader dynamics of galaxies. Galaxies acquire and retain their gas over cosmic time through an intricate interplay of cosmic accretion, intergalactic interactions, and internal recycling processes. The initial supply of gas for a galaxy typically originates from the accretion of intergalactic material in the early universe. As cosmic structures began to form from the primordial soup of hydrogen and helium, gravity coalesced the gas to create the first generation of stars and galaxies. Cold gas from the cosmic web continuously feeds into these galaxies, providing the fuel necessary for ongoing star formation. This constant inflow of gas is essential for the growth and sustainability of galaxies across billions of years. However, retaining this gas presents its own set of challenges. Internal processes like star formation and supernova explosions generate enormous amounts of energy, which can heat the gas and even expel it from the galaxy. Furthermore, supermassive black holes at the centers of galaxies can have a profound impact on their host galaxies through active galactic nucleus (AGN) feedback. This feedback can either heat the gas to prevent it from cooling and forming new stars, or eject it entirely. Despite these challenges, galaxies are able to recycle gas through processes like galactic fountains. During these events, supernova explosions and stellar winds blow gas from the galactic disk into the halo, where it cools and eventually falls back into the disk. This process can potentially trigger new star formation, thus perpetuating the cycle of cosmic renewal. In this grand cosmic ballet, the interplay between galaxies and the gas they interact with shapes not only their individual fates, but the very structure of the universe itself. Each interaction, whether violent or nurturing, leaves an indelible mark on the galaxy's evolution, contributing to the ongoing story of the cosmos. In the vast expanse of the universe, galaxies are not isolated entities, but are intricately connected to the cosmic web of gas, dark matter, and other galaxies. The intergalactic medium, a vast expanse of gas and dust that stretches between galaxies, plays a pivotal role in shaping their evolution. Minor mergers with smaller galaxies, often overlooked in their subtlety, inject fresh supplies of gas into larger galaxies, triggering renewed star formation. However, in the dense environments of galaxy clusters, galaxies face a harsh challenge. As they move through these regions, they are subjected to a phenomenon known as ram pressure stripping, where the intergalactic medium sweeps away their gas. Despite these challenges, the dynamic interactions between gas inflows, recycling, and the complex dance of intergalactic forces ensure that galaxies can adapt, evolve, and sustain themselves in a universe that is in a perpetual state of flux. At the heart of each galaxy lies a story written in its very structure, its morphology. From the elegant spiral galaxies with their stunning arms stretched like cosmic ribbons, to the more solid amorphous ellipticals, every shape and form is the result of a combination of factors: their initial conditions, evolutionary journey, and interactions with neighboring galaxies and the broader intergalactic environment. The conditions present during the formation of a galaxy, such as the distribution of dark matter, the surrounding environmental density, and the dynamics of gas accretion, all play foundational roles in determining its shape and structure. Take, for example, spiral galaxies. They typically form in less dense regions of the universe, where gas has the space to settle into large rotating disks. These disks, swirling with activity, fuel ongoing star formation that illuminates the galaxy, producing the striking spiral arms we associate with these galaxies. The less crowded environment allows for the slow and steady creation of new stars, ensuring that these spirals remain vibrant and continuously evolving. On the other side of the spectrum, elliptical galaxies are born from more violent and chaotic processes. One of the most widely accepted theories for their formation is the major merger hypothesis. When two or more spiral galaxies collide and merge, the gravitational forces at play create a chaotic environment. Stars are often stripped from their regular orbits, resulting in the random, spheroidal distribution characteristic of elliptical galaxies. These cosmic collisions can also compress the gas within the galaxies, triggering bursts of intense star formation. However, this newly formed gas is often quickly consumed or expelled due to powerful supernova explosions and the feedback from active galactic nuclei, AGN. The aftermath is a galaxy populated by older, redder stars and little cold gas left to fuel further star creation. This lack of fresh fuel gives elliptical galaxies their smooth, reddish appearance, distinguishing them from their spiral counterparts. The environment in which a galaxy resides also influences its morphology. In densely packed regions like galaxy clusters, interactions and mergers are more frequent. These frequent cosmic collisions lead to a higher proportion of elliptical and lenticular galaxies, as these galaxies often form through mergers or the gravitational stripping of gas. In contrast, in less crowded areas of the universe, spiral and irregular galaxies are more common, their formations less disrupted by external forces. Smaller galaxies, particularly irregular galaxies, often owe their chaotic shapes to gravitational interactions with nearby galaxies or the accretion of gas clouds of various sizes. These forces disrupt their form, leaving them with less defined shapes compared to their larger counterparts. Dwarf galaxies, a category all their own, can exhibit any of these morphologies depending on their unique histories and the interactions they've experienced throughout their existence. In the grand tapestry of the cosmos, a galaxy's journey is not only shaped by its internal dynamics, such as the way its gas is recycled and star formation is regulated, but also by the external forces that shape its evolution. The interplay between galaxies and their environment orchestrates a vast variety of galactic forms, from the magnificent spirals to the serene ellipticals. This cosmic evolution reveals a universe in constant flux, where each galaxy is a living testament to the forces at play in the great cosmic dance.